Hey Sayed, how are you? Can you hear me?
Hi, yeah, I can hear you.
Hi Riku.
Hi, Julian.
So I see Professor Ishikawa is here.
Yes, yeah, we will start in 10 minutes.
I'm here. I'm Masatoshi Ishikawa.
Good morning, Professor Ishikawa. Is it morning? Is that right?
No, evening.
Evening, okay.
4 p.m.
Okay, I see. Okay.
Yeah, so I think, yeah, it's right after midnight for you, Julian, and it's 3 a.m. for me, 8 a.m. for Riku. So it's all over the world.
Professor, is there something you want me to mention for your introduction in? Professor Ishikawa, is there something you would want me to mention for your introduction?
Yeah.
In particular, something you have at heart that we don't have in your biography.
Okay. Please say very briefly.
Okay, very good. I can do that.
Okay, I don't have any music or anything prepared. Otherwise, we could have played something so that the time arrives. But I don't play anything as well, so.
So it's already streaming on YouTube?
Yes, yeah, it is being streamed on YouTube, yes.
Perfect.
Have you tried sharing your screen? Is everything fine?
Okay, I will try. So I will share my screen. Can you see my presentation file? No.
We cannot, but I guess
I think yeah, I have to. That's a good one. Let's. I have to change the settings. Just give me a second.
Okay, fantastic.
Okay.
So
Yeah.
great.
You see my vision chip here?
Yeah.
Yeah, looks pretty nice. Oh, great.
Okay, once I cut my.
Right, great. So I'm gonna start sharing my presentations. It's going to be only 5 minutes. So everything is set. That's good. So I think now I can start recording. Everything looks okay. So these talks will be available later on for other viewers to see them on YouTube. So hello, everyone. Thank you very much. Andy just joined. Hi, Andy. Hello. Thank you, everyone, for joining this workshop. This is a workshop on near sensor vision processing. I'd like to thank the organizers, especially Julian, Riku, Paul, and Edward, who helped this workshop by organizing it. And special thanks to program committee who helped us with reviewing the papers. So the objective of this workshop is to bring researchers from academia and industry together across multiple disciplines, including hardware design, compiler, software algorithm design, and holistic solution design. We would like to demonstrate the power of unconventional sensors in robotics. These sensors have applications in a variety of solutions and problems, such as estimation, recognition, tracking, including STAM visual odometry, as you will see them in some of the demos today. The solutions offer low latency, high frame rate, and low power consumption. And we would like to see that how we can use them in robotics even more. We have great talks organized, 10 talks from universities, academia, and industry. I hope you enjoy the talks. All of them will be recorded and will be available later offline on YouTube. We also have great demos. We have arranged 5 demos. That includes almost all of the demos are with Scamp 5, a focal plane sensor processor, which has been designed and developed at Manchester University. So these are great demos. I'd like to thank the people who helped us to these demos to be organized and to present them. And finally, you can find all the links and everything on the website of the workshop. There's tinyurl.com, and simply you can type ONSVP-ICRA, or you can Google ONSVP workshop. In addition to those, I'd like to thank the sponsor of the workshop, Wiley, who basically sponsored the awards for the best presentation and best poster. During the break sessions, GatherTown is available. You can just simply go to the link of the GatherTown and see the posters, videos, and also demos. So we're going to have 4 break sessions, and in all of them, posters and the demos will be available. So I think that would be basically the basic introduction. And now we will start the first session, which we will have 3 invited talks. Julian Martel from Stanford will chair this session. Thank you, Julian.
Thanks a lot, Sayat, for the introduction. And we will have 3 talks by Professor Ishikawa, Professor Mahoney, and Professor Davison. And to kick off this session, it's really a great pleasure and honor to welcome Professor Ishikawa. And Professor Ishikawa started his career as a researcher at the Industrial Products Research Institute in Tsukuba, Japan. And since 1989, he has been professor at the University of Tokyo in different disciplines, in mathematical engineering, information physics, and computing. And he also held various executive roles at the University of Tokyo, executive advisor to the president, vice president, and executive vice president. And his research interests are in high-speed, massively parallel vision sensors, high-speed intelligent robots. And I think your research really greatly fits this workshop. And I've been looking forward for a long time to actually hearing your talk. So it's a great pleasure to listen to you, Professor.
Okay, thank you very much. So it is a great honor for me to make a presentation this workshop. So I'd like to express sincere thanks for the committee member, organizers, for your preparation of this workshop. Today, title of my talk is a high-speed parallel processing vision chip and its application in dynamic intelligence systems. So I'm a researcher of device, system, architecture, and application systems. So my talk is very wide range, has a wide range. So maybe you can enjoy my talk by using through my a lot of videos. So the last of my talk, I will show you a lot of videos. Maybe you can enjoy. So CMOS imager is now developing. So almost all researchers on CMOS imager are pursuing the space resolutions. So this smartphone camera and so on requires a space resolution and low noise type of specification. So we are pursuing the time resolutions. High speed capability will change the intelligent systems. So we want to open the new dynamic intelligent systems using the high speed vision. So for example, these areas, high speed robot, high speed factory automation, high speed vehicle control, high speed 3D security, biomedical human interface. All of this area requires a high speed image processing system to control the high speed target. So we are making a basic design concept for such systems. So the target, environmental target is here. So the sensor, processing, and actuator or display will be fed back to the environment target. Environment and target have their own dynamics. So this dynamics cannot be changed, but artificial module, sensors, parallel process, that is the computers and actuator display. These devices can be designed by ourselves. So these devices have to cover the target dynamics. That is the sampling theorem. So we have to make a big effort to the high dynamic range, high dynamics sensor, the high dynamics parallel processing, high dynamics actuator displays. We call this type of design concept as dynamics matching. We have to make a dynamics matching systems. And also the user intelligence system has this type of architecture, hierarchical parallel distributed system with module structures. So the sensor data is up to the judgment and down to the actuators. In this type of hierarchical parallel processing system has several issues for developing. One is the real-time parallel processing. One is the task decompositions. Usually we are proposing the parallel decompositions, and also the enough bandwidth will be should be realized without bottleneck. So this area, vision and some early vision processing have to be integrated into one chip. So this type of system, we call this type of system as vision chip. So vision chip output will be fed back to the actuators through the low level, high speed, real-time, low level feedback path, and also the high level feedback path. Once data will go up to the judgment, high level recognition, and back down to the actuators, and also the data will be go to the other systems. So this type of intelligent system requires many design concepts. Some person says smart sensing, edge computing, parallel processing, synchronized network, and so on. So in our laboratories, so we are concentrating the vision chip systems and also the high speed vision. If you can throw the 150 km/h per hour ball. So if you use the video rate cameras, you can get every 1.4 meter data of the ball positioned. However, if you use the 1,000 frame per second high-speed vision, in that case, you can get the 4.2 centimeter data of the ball trajectory. That means that this type of system can keep the sampling cell, but this type of system cannot keep the sampling cell. That is very important thing. So our human is about 100 kilometer vehicle, train is 300 kilometer per hour, and flying object 900 kilometer or more. So we want to control the type of high-speed target. So we have to use the high-speed vision to control this type of system. Usual image processing system using the 30 frame per second or the 60 frame per second, but high space resolution 1,000 by 1,000 or 4,000 by 4,000 or more. However, our first vision chip is here, very low space resolution, 64 by 64. However, very high time resolution, high frame rate, 1,000 frame per second. So finally, we want to pursue this area, high frame rate and high resolution. So now we are here 1,000 by 1,000 and 1,000 frame per second. Of course, we are pursuing the more resolution, space resolution. So generally speaking, image processing is consists of the imager and the computers. However, usually computer is very slow, so we want to introduce a high performance computing system for the high speed image processing. However, this transmission line is still bit rate, so the total performance, total speed is still slow. So we want to change this type of architecture to the one package, one module of vision chip. So in this case, there is no bottleneck between the CMOS imager and the parallel processing arrays. So this type of system in future, we want to make all of the system will be integrated in one modules. So to make a vision chip, there are several architectures. One is a pixel parallel, fully parallel processing system type of system. One pixel has a photo detector and the processing element. And the clamp parallel type of system, low direction, we want to introduce a scanning architecture. So some interface, just like a camera link, introduce a high-speed interface between the PDR and the PE array. So this view graph is a history of a vision chip. A very old time, 1992, we make a big size vision chip, big size, 1 meter by 1 meter chip, not a chip. 1 meter chip has a 64 by 60 pixels and the same number of the processing element. 6 years later, 1999, we made a one chip version of this big size system. The 8.7 meter by 8.7 meter chip can have a 64 by 64 pixels, 4,000 pixels. And then 4 years later, we changed some architectures. This is a reconfigured programming type of the system, general purpose type of the system. So the other direction is a special purpose vision chip, special purpose digital vision chip. So the mainly target tracking and target tracking algorithm requires the moment extraction. So the moment extraction included into the one chip, integrated into one chip. So this chip can make center position detection with moment extraction circuit. And this research is very, very old, around 2000 or 2009. Recently, 2017, we developed a stacked type clamp parallel vision chip with Sony Corporation. Maybe you know Sony is a top maker of the CMOS imagers. We developed a processing element array. So the second layer is our architectures. So the first layer and the second layer stacked each other, and we can use a very, very high level processing semiconductor technology. First, I want to explain the pixel parallel type of system, 1999. So this case, one pixel including consists of this type of the processing element. 1 bit LU and local memory, and A to D converter is designed into the 1 pixels. So in this case, we introduce bit CR architecture. So if you want to n bit operation, in that case you can make a n iteration operation. N iteration operation can make a n bit, 4 bit operation, 8 bit, 16 bit operation can be. And also the compact A to D converter is here. So including all of circuit, we realize this type of the general purpose processing element, only 400 transistors. Only 400 plus. This is a very, very compact PE. So that's why we can integrate it 64 by 64 by using 350 nanometer, very, very old, very old technologies. So you can see the photo detector, analog circuit, A to D converter, and 24-bit memories. And recent our research is a clamp parallel, stacked type clamp parallel vision chip. First layer is a usual CMOS images like this. Sony Corporation has a very high level technology for high speed, high sensitivity CMOS images. Second layer is a parallel processing layers. So for this parallel processing, our architecture is used, making a very, very compact type of the parallel processing system. So in these second layers, we introduce a 4-bit clamp parallel 4-bit processing element, more than 1,000 processing element, and 1-bit processing element here. So these two types of the processing element has a clamp parallel processing architectures. So finally, we have this chip specifications, 90 nanometer CMOS image technology and 49 nanometer logic technology. Two stack type of technology is very, very easy to implement because by using a different first layer, second layer, different type of technology can be used. So that is very easy to combine the different technologies. So more than 1,000 by about 1,000 pixels. So the important specification is a high-speed image processing system. 1,000 about 1,000 by 1,000, 500 frames per second for 4-bit operation, and half quarter of this full pixel. So the 1,000 frames per second for 4-bit operation. And one more important specification is the power consumptions. Top speed case, only the 300 milliwatt. That is very small, low power consumptions. This type of system developed by a collaboration between the Sony Corporation and our laboratories. Now this chip is commercialized. A modified version of this chip is commercialized. You can use this chip. You can buy this chip from Sony Corporation. And also the development kit is a software and hardware development kit is also developed. So this is a development kit. So we are making the target chip, target camera system. This camera includes the high performance parallel processing system, vision chip, and CPU, and so on, all in one package. And the high performance 1,000 frames per second image processing can do in this chip, in these cameras. And software will be changed. So the high frame rate vision, if we use the high frame vision, target cannot move quickly. So the target will only within several pixels. So we can set the self window around the target. So the target move only within this self windows. So the algorithm is very, very easy. So the only AND operation can detect the next target and also the next self windows. So I want to say a high frame rate makes algorithm so simple. So this simple algorithm can make a high speed image processing. And from now, I will show you the application, many videos. So the first application is the high-speed 3D shape measurement system. Simple or the encoded structured light can display on the object. After that, one high-speed vision system can take such type. So this is a very, very simple structured light case. We can get every three-dimensional shape, 32 by 32 three-dimensional shape every 1 millisecond. 1 millisecond is enough for us to get the 3D shape recognition system. This case, very high speed shape change can be observed by our system. So the three-dimensional shape, high-speed obtained by our system. And in this system, we use a Sony chip type, stack type system. And by using high-speed shape recognition system, we get the book scanning system. So we know the shape of the book, and also that we can get the high resolution book images, so that we can easily reconstructing flat type of image in real time. So the 250 page can be scanned within 1 minute, 60 seconds. That is very high speed scanning can be realized. In the target tracking, the active vision system is used for the target tracking. We use this type of two actuator system. So the two actuator system can track the target. So the relative resolution will go up. So the high resolution, high speed tracking can be realized. And also we can introduce the galvanometer here to high speed galvanometer can track the velocity. In this case, we can use this optical axis. So the high speed camera, various optical measurement system, and also the high speed projector can use this optical axis. So the application of this type of system, target tracking system for ping pong ball. So this ping pong ball can be tracked by our high speed galvanometer system and high speed vision system. So this high speed vision data can be fed back to the two mirror system, so that we can get this type of system. Target is controlled at the center of the images. So even this ping pong ball is very, very high speed. This is high speed. Semi-professional person can hit the ball, but our system can track this type of ping pong ball. So this ping pong ball is tracked here. So many times I say a joke. So this system is a very important training system. So I want to sell this system only to the Japanese national team to win the Olympic game held in Tokyo. That is my joke. And also the projection mapping. Usually projection mapping target is a stationary non-moving object. But if the target is moving or changing, in that case, we have to use a high-speed 3D shape measurement system. That is every 1 millisecond we can get a high-speed shape measurement. So that data fed back to the display. So display can display this type of system. So you can see the very, very high-speed dynamic projection system. First is this ball is tracked by our system, and also every 1 millisecond we can get the position and the shape of the target. After that, 1,000 frames per second vision, a projector can project this pattern on the ball. So this case only ball, but this case we use a marker for the high-speed 3D shape measurement, so that we can get high-speed 3D shape and high-speed projector can make a movie on T-shirts. You can wear the movie on your T-shirts, and also in this case we use a marker. If we cannot use a marker. In that case, like a liquid. In that case, we use a different types of the tracking system like this. So on liquid and clothes, we can track and reconstructing the image and project on the target. And this type of dynamic projection mapping system is integrated into one package. A lot of devices will be integrated in small package by using the Sony chip. So this type of image vision chip can make a very compact target tracking the dynamical projection system, projection mapping system like this. So this system can track all of the system like this. And robot application. So the first application is the budding robot. So our budding robot has a 2-camera system, 1,000 frames per second. So the 2-camera system can take ball position every 1 millisecond. So the high-speed arm can hit the ball 100%. 100% we can hit the ball. So and also we developed a very high speed of hand system, very high speed hand. Unfortunately, today line bandwidth is not so wide, so you cannot see the high speed of our high speed hand system. So by using this hand, we can pick up the small pieces in the air. Can you see this video? So very small pieces can be taken by the tweezers, and also the dribbling. It's very high speed dribbling. So the camera system and this video is very slow. If you're interested in this video, would you please visit our YouTube? And also the low egg. Dropping low egg can be caught by our high-speed hand system, like this. Low egg dropping down, and hand system can track the egg and push the egg and breaking. And also the re-grasping, push up and catch. This push up and catch motion is controlled by 2-camera systems. 3-dimensional shape and recognition and model matching is done within 1 millisecond. And rock, paper, scissors game. In this case, our high-speed vision and the high-speed hand can win every time like this. And only 1 millisecond and 20 milliseconds is enough for us, but the human takes about 60 milliseconds. So every time our robot can win the human. And also the bike running robot. So even this type of system, also white marker is measured by high-speed vision and calculating the optimized running postures. And industrial robot, playback robot is very, very bad from the viewpoint of the accuracy. So in this case, local high-speed visual feedback system attached to the playback system. In this case, this type of robot system can controlled by local high-speed visual feedback system. In this case, this rough training camera can teach the very, very rough teaching, but the local feedback system can feedback to these actuators. So the performance is very, very high level, and the accuracy is very high. Even the table will moving, but we can make a top performance. And the vehicle and security, we have make a very high performance vehicle and security system. And our laboratory has device research and other application researches. We've developed many, many types of application system by using the vision chip or high-speed vision system. Lastly, I want to say one thing. for the future of the vision chip. High-speed image processing, 100 megapixel, more than 100 megapixel, and 1,000 frames per second, and high sensitivity, low noise. And feedback latency lower than 3 milliseconds is needed. And the perfect target tracking requires 3 pixel, under 3 pixel target tracking. And the functionality is compact PE, parallel processing without scanning, and so on. And the packaging is a very low power consumption, and the camera size is very small, 10 millimeter by 10 millimeter required. So lastly, I want to say vision chip and high-speed vision will create wide application field, as I showed today, and also the open new era of the dynamic intelligent system. So today I don't have a lot of time, but I speak a very high speed. If you have an interest, would you please visit our webpage and YouTube channels? Thank you very much for your attention.
Thanks a lot, Professor Ishikawa. I think your demos are really impressive. We're slightly over time, so we might not have time for a lot of questions. I'll take one of the questions we have on the chat, which is a high frame rate allows us to use simple algorithm for tracking, as you mentioned, but does this make the system more susceptible to failure when the object is temporarily occluded? And what can be done to solve this?
Many times I receive the occlusion problem question on okay. The occlusion problem. So in this case, of course, as you know, simple only one target is no problem. But if we have to operate a two target system, there is occlusion. In this case, this motion is perfectly controlled, perfectly recognized our system. So these type of occlusion, we can estimate this trajectory by a perfect measurement of the dynamics of the target. However, these type of occlusion, this type of dynamics is very difficult thing. We are now developing a new algorithm for adapting this type of occlusion or
I see.
Similar type of system.
So I think we have time maybe for one more question. So I'll ask, I'm really impressed. I think we're all very impressed by your demonstrations. There's nothing more convincing than this type of videos and demonstration, I have to say. And so what do you think, or what is the next cool demo that, is going to be the next thing you're gonna impress us with? Or what is the thing that, you think like, okay, I still want to do that?
We are now pursuing the high speed and high resolution type of system. Now 1,000 by 1,000 and 1,000 frames per second. So I want to pursuing the 1,000 frames per second and 2,000 by 2,000 or 4,000 or 4,000 parallel processing pixel type of system, which can realize very, very real projection mapping, just same as the real target, and also the very high resolution dynamics measurement system. For example, the 0.1 millimeter from 100 kilometer vehicle, 100 meter vehicle can go through, but 0.1 millimeter resolution of the environment can be taken. That is our next target.
Great. Thank you so much again for accepting to talk at our workshop. That was really nice. Thank you very much.
Thank you very much.
So we have our second speaker, who is Professor Robert Mahoney from the Australian National University. And I have only a very short bio, very short fact. So Robert, maybe you can add more if you want. So notably, Professor Mahoney is a fellow of the IEEE. And his research interests are in nonlinear system theory with application in robotics and robotic vision. And he's known for many things, but among these many things, he's known for his work in aerial robotics, robotic vision, and optimization on matrix manifold. Professor Mahoney, we are really looking forward to your talk. And I think you're going to talk about event-based systems. Is that correct, right?
Correct. Can you hear me?
Perfectly. Thank you very much.
Perfectly good. And you can see my slides. So
and we can perfectly see your slides.
Excellent. Good, good. No, that's good. All right. So, yeah, change things around a little bit. So I want to talk about event cameras and some of the things that, some of the processing that goes into it, and particularly this format of the stereo hybrid event frame format. So let me sort of jump in here. So hopefully pretty much everyone watching this would know what an event camera is. It's a camera that returns an event when there's a change in intensity at a specific pixel, rather than giving you an absolute intensity at every pixel at a particular time. And it returns the event with a timestamp, so at nanosecond resolution. So the properties of event cameras are quite well known, but let me go over these just to make this point again in the context of this particular talk. So on the left here, we have what an event camera is good at, right? It generates asynchronous events. So it generates temporally dense information. So if I take an event camera looking at a scene, and that's basically the red and blue dots are events, and I pick a specific time, then there's almost certainly an event happening somewhere in the image. So temporally, there's events, information happening all the time, even faster than a kilohertz after Masatoshi's talk. So it has the advantage then that you never get image blur, because that information is reported instantaneously. Because those events are relative changes in intensity, the way the circuit can be set up, it can actually measure very high dynamic range. So typical cameras these days are in the order of 120 dB. So quite good dynamic range, and cameras can be quite low power in the event cameras. So you compare that to a traditional frame-based camera, so that's synchronous. So what happens is every frame you get a whole bunch of information, but in between those frames, temporally, there's nothing. So it's very sparse temporally, but it's spatially dense. So when you get an image, you get information at every single pixel. So these are very complementary properties that come between those two. So a frame camera has adjustable exposure, so it can actually see quite well in the dark if you're willing to open the exposure for long enough. And it can see quite well in the very bright if you're willing to close the exposure long enough. However, it doesn't have high dynamic range, so you either see one or the other. And if you open the exposure quite long, of course, you start to get blur. So you start to get information spatially blurred across different things. Has the advantage that it images absolute intensity, which an event camera doesn't do, and it has the advantage that it images static scenes. And so these two formats, or these two data formats, are extremely complementary, right? So the information that an event camera requires is very complementary to that of a traditional frame camera. And so by fusing event and frame data, we should be able to get everything, right? We should be able to get images that are spatially and temporally dense. So the full image is available at any timestamp. So, you know, if you really want to know whether Germany scored that goal in 1966 and you had an event camera watching it, you'd be able to go back there and figure out exactly where that ball was at that particular instance. It should be able to image high dynamic range in absolute intensity scale, and it should be able to image both static scenes and highly dynamic scenes without blur. So perhaps not low power consumption, because you've got both the normal camera and an event camera going. So I've got a couple of examples here, and this talk isn't about the actual filters that we've been running lately, but I just wanted to bring these in to provide the context for the rest of the talk that I'm doing. And so this is from the DSEC dataset, this wonderful dataset that UTZ has recently generated, which contains prophecy event cameras along with a frame-based, traditional frame-based camera co-located. So they have the two of those on a driving rig, one on the left-hand side of the car co-located, one on the right-hand side of the car co-located. So we're using here just the left-hand side of the car co-located camera. So both the raw frame, which is on the top here, and I haven't shown the events because they're not so obvious. And so what we're doing here is we're fusing, we've registered the two sets of events, and then we're fusing the events with the raw frame to sort of extract more of this information. And so in particular, you can see in these areas where the standard frame is washed out due to high saturation, the event information is able to be fused in and actually extract out the road texture in an effective way and show what's going on. So another area that's interesting to look at in this particular one is the light pole here. And you can actually see that in the in E2 vid in particular, the light pole disappears a little bit. So the events in E2 vid are sort of not so effective at bringing it out. And even in the ECNN, which is a little bit more robust to different event formats, although it doesn't have the same performance as E2 vid, it doesn't image that light pole quite as effectively. So we're getting really quite impressive results of high dynamic range, which is a particular issue that's going on in these particular images from combining these two. This is another sequence from the DSEC data sequence where the car's going through a tunnel, and I brought this one in partly to show that this E2 vid and ECNN are machine learning algorithms, right? They're convolutional neural networks that work on aggregated event spatiotemporal frames. And clearly what's happened here in the right-hand side is that E2 vid, for some reason, and we don't know why, we just applied the standard algorithm, but it's failed for some reason, right? So the information here is not good. And we think probably what's happened is there's so many events associated with the bright field here that the spatiotemporal frame that E2 vid's used has not got good information in the rest of the image, and so it's blacked everything out. We think that's what's happened. We're not sure. But it shows one of the issues with machine learning algorithms in any algorithm where you put it, where it can at certain times have these major failure modes. And compared to that, the asynchronous Kalman filter we're doing, which is a stochastic data fusion algorithm, is doing a pretty good job. And actually, when we actually look here at the resolution of the car, we're actually pretty proud that you can see this is a quite good quality RGB camera, right? It's only the grayscale that we've used. But that's quite a good camera, and it's just unable to deal with the high dynamic range of the background here and the darkness inside at a reasonable exposure. And with the events, we're almost even to the point of being able to pick out the driver in the car. The reconstruction is so good, partly because of the quality of the data. So if you're interested in this algorithm, I'll be talking about that at the CVPR workshop in a couple of weeks that many of us will also be at. But for the moment, the rest of the talk is about stereo hybrid event frame disparity. This is just another example that I wanted to put on to just talk about temporal interpolation. So this is the shapes data set that many of us in event cameras know and love, again from UTZ. And here we can see two images super overlaid over each other. So the light blue here is one image, and then the next red is the following frame image. And so the reason that we've done this is to demonstrate the pixel displacement that's occurring here. And so what we're doing is we're interpolating an image in between those two by using the events. So we're effectively directly integrating forward the information from one image into an interframe information. But if you do the asynchronous Kalman filter, again, you can acquire that information and you get quite good looking results. And we put in here the double integral, the event-based double integral that was also developed here at ANU, just to show that effectively it's doing direct integration. It's the de-blurring algorithm combined with the direct integration, and it doesn't get as good a performance as a proper stochastic data fusion algorithm. So these results aren't quite as good as the DSEC results. DSEC doesn't have the fast motion in it, so I wasn't able to use those. And I'll talk a little bit about why that is in a moment. So hopefully I've made the argument that fusing events and frames is a really good thing to do. And I think there's an industry acceptance of this, and I know that there's a lot of projects within the industry towards building these hybrid event cameras. And sort of the early hybrid event camera that the research community at least has been using was based on this technology developed by the Innovation Corporation or a company and their Davis cameras. So these particular sequence of cameras that they've developed, and they really are fabulous cameras, and they've been wonderful for the industry. And again, I'm not a chip expert, but I've put the schematic of the early, I think it was a Davis 240 camera there, and you have a part of the schematic, the APS, which does the actual main image readout, and a part of the camera here, the DVS, which does events. And so that circuit is then integrated into every single pixel, which you can see a high res of that particular pixel, and then those readouts come out. And so we call this a monocular hybrid. So it's hybrid because it generates both events and frames, and it's a monocular camera because it uses a single lens and a single CCD array, call it a CCD array, to image, so that the events and the frames are inherently registered. You don't have to solve the disparity problem that I'm going to talk about for the rest of the talk. So why is it that this isn't the answer to all our problems? And there are a number of issues with hybrid event frame cameras and the Davis technology, specifically the fact that all of this circuitry is put on the same circuit board means that when you trigger a frame, then there are current surges within the circuitry. And again, I'm not an expert in this area, but what we've done in our group is we've actually logged data, and admittedly this is from an early Davis camera, and had a little bit of look at what that people call shutter noise. So this is a known problem in a Davis camera, but one that perhaps people haven't actually looked at carefully. So what I've done here, I've got two graphics that really show the shutter noise. So if you look firstly at this graphic up here in the middle of the scene, what you've got is a single row, so a single column 200 of the camera, and then I've plotted out the rows against time. So against the time is what's going on the bottom, and every time an event fires, I plot a little blue dot into the appropriate row column there. And what you can see here is I've also plotted onto that when the frame triggers. And so you can see that there's a burst of events at the point that the frame triggers. If you look carefully, you can see that there's a little gap where nothing happens immediately afterwards, while all of the capacitors in the comparators of the event circuits reset. And then there's a period of time after that when all of the data is garbage, right? So basically there's a sort of a fringe here that you can see, which doesn't look very sensible, okay? And the question is, how bad is that? So visually, just looking at that doesn't look too bad, but I've plotted it over here on the left where I've plotted it by event. So what I'm doing here is not time, but I'm simply plotting all of the events in the order that they're logged. So just event 1, event 2, event 3, and then I'm plotting the information that comes out of that data. And what you can see is that there's a lot of bad events, right? So every single event in here is associated with the shutter noise. And so there's a lot of events, on that period of time, during that period of time, there's probably about 15% of all of the events acquired are associated with shutter noise and not with the main system. That's particularly bad for the work I'm doing. So when I said that there was some problems with this particular issue, and we're still getting, if you look carefully, they're still getting quite a bit of noise in the actual data fusion that we're doing, it's because all of this data is bad, okay? It's actually outliers in a stochastic sense. So we're using Gaussian filter technology to build these data fusion algorithms. And when you get that many bad outliers, it significantly degrades the result. Compared to that, the earlier data that I was showing you here is using a separate prophecy camera from the FLIR camera, and consequently, you're not getting the shutter noise, and the quality of the event data is higher. And so as the quality of the event data gets higher, these data fusion algorithms that I've been working on start to come into their own. So we're interested in stereo hybrid event frame, and we went in this direction because we don't build cameras, we don't build camera chips, so we can't be clever and build a monocular hybrid event frame camera that doesn't have this problem. I believe there are some companies around the world that are looking at back illuminated technologies that might get over these issues. But I know that the existing technology, the technology that Davis is based on, and the original prophecy has these problems if you run them in the hybrid mode. So the idea we had is to study the question from a stereo point of view, and then this brought up a couple of really interesting points. So firstly, if you look at modern phones are sort of going in this direction where they're putting multiple cameras on the back of the phone. So the idea that they might want to put an event camera as one of their cameras and give them this extra modality when they're obviously solving all of these registration problems anyway is not an unreasonable idea. So we think that it's exciting from the point of view of a major consumer product that would be interested in this technology. And then the other thing is that although the registration problem is a challenge, it's also an opportunity because it allows you to do a little bit in terms of structure. So we think the stereo hybrid event frame sensor, the CHEF sensor as we call it, is an interesting sensor modality, and so we're going to talk about it. So it's essentially an event camera, a frame camera mounted side by side. We're going to assume that we know the extrinsic intrinsic parameters of the configuration to a high degree of accuracy, and we're going to assume that we've synchronized the image capture, and in particular that we know all the exposure times and information about the RGB camera synchronized with the event camera. So the challenge now is to fuse event and frame data from a CHEF sensor. We need to register the data. So in particular, events are spatially sparse but temporally dense, whereas images are spatially dense and temporally sparse. So the disparity problem, the registration problem that we run into is not a traditional registration problem. So we call it the asynchronous synchronous stereo event frame disparity problem. And the idea is that you need to using the image frame pixels as a reference grid. Each event needs to be registered to a pixel in the image associated with its inferred disparity that would be present, okay, should there be frame data at that particular time, understanding that there may not be frame data available. So I've got a couple of graphics here that Ziwei very kindly did for me today. So you imagine that you have a stereo camera. The left-hand camera is a frame-based camera, and the right-hand camera is an event camera. And this is drawn from the event data, at least, is drawn from the shapes data with the Davis 250C. So what we want to do is for each pixel in here, we want to register that pixel when it occurs at a frame, and then put that into a combined spatiotemporal block of data, which includes both the frame data and the event data. But we also want to be able to take an event which occurs in an interframe period and register it equally into the space, but occurring at a point that doesn't correspond to any frame data. So we need to somehow interpolate frame data and co-locate the event data with respect to that. And I think it's quite an interesting problem in general, especially if you get very fast-moving objects that the event data can pick up and the frame data might be blurring, but you're interested in finding information about disparity within that frame. So I think actually just formulating the problem in itself is an interesting problem. So that's the goal. So as far as we know, this is not a problem that's been well studied. We don't know really of anybody who's formulated that in the same way. Feel free to write us an email afterwards. So we thought the first stage was to get a decent data set that we could work with. So we mounted our CHEF camera on a UR5 robot that we have in our laboratory. and we did accurate calibration of all of the extrinsic and intrinsic parameters of all of the cameras and the system. And then we set up 3 physical environments, a simple boxes, a complex boxes, and a picnic environment, where the UR5 is quite close to all of these environments. So the disparity that we're going to be expecting for the baseline that we have on those cameras is in the order of 0. Well, 1 or 2 pixels is about the least disparity we get from the background. And when we're quite close to the objects, we're likely to get something up towards 50 pixels of disparity. So then what we did was we used the UR5 to move it to a whole sequence of positions. So you can see all of the reconstructed camera positions here, where we know the pose accurately of each one of those camera poses. And then we used the standard 3D Flow Zephyr software to reconstruct 3D mesh of the image. So that's how we generated our ground truth. And you can see it's done a very good job. There's a couple of points here in the image where things are a little bit haywire, but overall we're pretty happy with the quality of the ground truth. And then we collected a data set. And so the data sets we collected was moving the UR5, and we moved it through a series of different trajectories, a circle that was roughly the same distance from the area, and then 2 different complicated Lysigis curves. So I've shown you the most complicated Lysigis curve here that we collected data for. Each frame we computed the pose because we had it from the robot. We used ray tracing to convert the mesh into a 2D ground truth, and then we computed disparity from the stereo extrinsics. So we get disparity ground truth from that. So this is, to our knowledge, a fairly open problem. So what I'm presenting now is what we would call a first cut algorithm for stereo event frame disparity. It's not a particularly deep algorithm, so I can go over it very, very quickly. We only compute synchronous disparity, so we actually at the moment just consider the case where we compare at image frame time. So I still think there's a very interesting open problem to expand that into asynchronous in the interframe periods. And we also only compute disparity where the events provide information, right? So event data is spatially sparse, and so we also constrain ourselves to those points where there's event information. So you can see the limitations of the 2 sensors coming into play here to place constraints on what we're doing. So the general problem, I think, is really interesting. This is just a first hack at what we're doing. Apart from this, we do reasonably well, as I'll show you. So the idea for the algorithm is very simple. We just take the raw image on the top row here, and we do a binary edge map of the raw image. And so that's just using Sabel filters and a threshold. Then we take the event stream and we apply this high-pass filter. So those of you that know my work will know the complementary filter work of Cedric Shearlink and myself, and we're essentially just using that to generate a grayscale image, which we use a very high pass. So we don't acquire much information. So it's very non-direct integration, but it still picks up information along the edges quite well, right? With the little sort of response that you get out of the high frequency, the high pass filter. And then we do a thresholding of that as well to generate a second binary image, which looks very like an edge image because where the information in the events are is around edges. So then it's very simple, right? We take the left stereo image of the frame data and the right stereo image of the binary threshold of the high pass on event data, and we do a standard disparity matching on those images, which of course is very computationally quick, and one day hopefully could be put actually into on-chip computation if this was found to be useful. So to show you the results, because I know I'm a little bit over time and I'll zoom through the last couple of slides. So here you can see the results, the ground truth on the top and the actual Ceph disparity that we've computed on the bottom. And we're pretty proud of the results. They're basically pretty good. Couple of failure points. You can see a failure point over here where I think the epipolar line lined up with a lot of the edge information in the main image. So that sort of basically caused failure of the epipolar matching. A little bit of a failure mode down in the front here where I think the disparity got too big for the algorithm, and it sort of failed to actually pick up the disparity. But apart from that, we're doing pretty well. We're obviously losing information in a couple of areas and we're not getting matching, but where we're getting information, we're actually finding that this algorithm is doing a pretty good job. I'm low on time, so I'll skip through these. So we did, it's pretty hard to do much comparison of the quality because there aren't algorithms out there. So what we did to compare is we used a standard algorithm, the SNN image reconstruction algorithm that goes from events to images. And then we had two images, left and right images, that we reconstructed, and we did stereo disparity on those images and generated some disparity, and it works quite well as well. Although you can see, for example, in this area here, it's failing where we're succeeding reasonably well. And we did some statistics on that, and we see our bad pixels are around about 2 to 3 times as good, and our inlier ratios are much, much higher than you get out of the general algorithm. So what we're doing is working quite well. You can see here a 3D reconstruction built on the disparity that we've used, and it's looking reasonably good and should be good enough to do the data fusion that we want to do. Remember, part of the idea of this is to be able to solve the disparity problem well enough that we can then use the data fusion on platforms like mobile phones to do good quality video in low light conditions or in blurry conditions. So the conclusion is that hybrid event frame sensors are an important sensor modality. We should be studying them. I think they're exciting. I think they're very relevant to future commercial applications. Stereo hybrid frame sensors, where your two cameras are shifted by a known baseline, are both a challenge and an opportunity. So the challenge in the sense that they require you to solve this disparity problem, and an opportunity in the sense that that gives you some depth information which you can then use in other algorithms. So then I talked about the asynchronous synchronous stereo event frame disparity problem, which I think in itself is an interesting question and one that needs to be considered by the research community. And then we proposed this stereo event frame edge disparity algorithm based on the high frequency pass filter that we developed in earlier work. And we're pretty happy with the output. Here's another example of that output, again with a couple of failure modes up here, but generally doing pretty well. So thank you very much for your time, and I'd like to just mention again my team here at ANU that have been integral in all the work I've been doing.
Thank you very much, Robert. So I'll ask you a question because I'm not very familiar with this work. Can you tell us a bit more? When is computation happening with this event data? So I'm not so sure I understood. Is the event computation asynchronous? Is it binning events between all the frames? Can you say just more about this, about the setup of what's really the input of the algorithm and how it's binned or not binned, or yeah.
Yeah, so that's a really good question, and I was listening to Masatoshi's talk and realizing that some of the community won't be there. In fact, I'm giving a talk in CVPR where I'll go over the asynchronous Kalman filter and talk about it in detail. So the mathematics of what we're doing is inherently asynchronous. So what we're looking at doing is building algorithms that asynchronously, at least at the event field, every event that comes in updates an internal state of the algorithm.
Very good.
At the moment, we're implementing that in computers. We're a research organization. So systems theory and robotics is actually the group that we are. So we're not able to do FPGA development at the moment. And this particular algorithm, of course, has an additional complexity because you're cross-correlating that with frame data. And so frame data is inherently synchronous. And so actually, for this particular piece of work, at the moment it's theoretical, I haven't considered what the consequences on real-time asynchronous processing is. But the actual data fusion that goes behind it, that is designed to be asynchronous.
So is the point a pixel in the frame? Is it considered in it as well similar to an event as just a timestamp point that goes through your Kalman filter as an event does? Yeah, okay, great. Okay.
Exactly what happens, yeah. So when you're running the filter, you basically build a Kalman filter and then you quantize, you temporarily quantize all the information. So every time an event arrives, it's like a little packet of information that pumps an impulse into the Kalman filter. And when the actual main data arrives, it's like a little impulse, the camera data, the frame data, that pumps sort of a reference back into the system.
Oh, great.
If that makes sense.
Yeah. Okay, yeah, that makes sense to me. Then I think it really depends on how familiar people are with this. But thank you very much for expliciting this.
Sorry, I should have given a bit of a blurb on the AKF.
There's an interesting question here. I have two more questions. So actually, do you know if the problem of these triggered events, is it due to the fact the cameras are rolling shutter or global shutter, or does it make a difference whether you're using a rolling shutter or global shutter by this problem you presented in this Davis 240C? Or so maybe we're going too much into detail. So maybe a quick answer to this, but I think some people might be interested.
Yeah, look, it's a really interesting problem, and it's so I mean, I almost feel embarrassed putting the slide up because the innovation company has done fabulous work on their camera, and I think it's fundamentally a problem in all of these cameras. The fundamental reason is because all of the circuit is integrated, and I'm not an expert in this, but my understanding, because all of the circuit is integrated, when you actually trigger, and one of these, I think this one might be the trigger. When you trigger, you actually propagate potential back through the circuit, and you reset some of the capacitors that are going in here. And so the actual problem is associated with the fact that you're coupling the single photoreceptor into both the APS and the DVS. And so when you're triggering and reading one, you're actually doing horrible things to the other one, right? And I'm out of my depth. I really don't understand, but my understanding is it's really is associated with the fact that the same circuit is doing both bits.
Okay, so independent of the type of readout you're actually using, it happens just because you have the readout.
Yeah, exactly. If you build a circuit based on that old technology, you will get this problem. That's my understanding from talking to Innovation and Prophecy.
So we have another question, which is interesting, and I'll try to rephrase it. So how do you deal with synchronization of timestamping in these systems of hybrid event cameras and conventional cameras?
Yeah, so we worked with Prophecy on this, and what we actually have is here in the Prophecy camera, so the Prophecy is on the left here, we actually have a readout here which is running all the events. But then separately from that, what we've done is we've taken the trigger signal from the RGB camera. So it actually outputs a 5-volt signal when the exposure is open and closed. And we pass that into the Prophecy camera. So the Prophecy camera actually has an input that you can put. When it goes positive, it actually writes an event with the Prophecy timestamp on it. So inside our event stream, we get events which tell us when the FLIR camera has opened at exposure, and we get events which tell us when it's closed at exposure. So at the end of the day, all we have is events. And what we do need to do is synchronize the data capture between the camera and the event camera close enough that we can correspond the exposure events. So if you get more than 20, 50 milliseconds out, you're in strife. But as long as you're pretty switched on, it'll work pretty well.
Great. Well, thank you very much for all the precisions. That's very nice.
Pleasure.
Thanks a lot, Robert. And we'll go on. We will move on with our first speaker, who is Professor Andrew Davison, who is a professor of robot vision at the Imperial College London, and is a pioneer in self-localization and mapping. And I would say almost needs no introduction, but his main research interests are in improving the performance of SLAM systems in terms of time, dynamics, scale, detail level, efficiency, semantics to enable real-time 3D systems that enable spatial awareness. And he will tell us about representations and computational patterns for spatial AI. Thank you very much, Andrew, for accepting our invitation. And I'm also very much looking forward to your talk.
Yeah, pleasure. Great to be here. So can I just check my screen share is coming through okay and you can hear me well?
Yeah, perfectly.
Great. And can I also just check on the timing, Julien? So what?
So we have 30 minutes slot, and
Okay.
I would say 20 initially was 20 minutes a talk, 10 minutes question, but as you saw, I think this is pretty fluid.
Yeah, got it.
And
Yeah.
we have the coffee break after. I mean, coffee depending on where you are in the world. So yeah.
Yeah. Great. So, well, thank you very much for inviting me to the workshop. It's a pleasure to be here with so many excellent researchers, many of whom I know well. Of course, I enjoyed the last two talks very much. So I first visited, he probably doesn't remember, but I visited Professor Ishikawa's lab in Tokyo back when I was in Japan in the very late 90s. And I think probably saw a demo of his first 1000 hertz vision chip, which I found amazing and has been inspiring me ever since. So it's really great to see everything that he's been doing since. So I'm going to talk to you about representations and computational patterns for spatial AI. So this is rather broad. I'll explain what this means and why I'm excited about it. But just to give a bit of context to start with of what I'm interested in and really have been interested in through my whole career. So in particular, I've been working in SLAM, simultaneous localization and mapping, the fundamental ability of robots or other smart devices to understand the spaces that they are in, to understand their positions in that spaces, and to build useful representations or reconstructions or maps of those spaces that they can actually use to do intelligent things. And ultimately, what we want is for useful things to come out of that and products. And so it's been exciting for me, having worked in this area for over 20 years, to actually see products on the market now that do use vision-based SLAM. And here's a few examples. And interestingly, they are quite a range of different products that have quite similar capabilities in terms of SLAM and vision in robotics, in things that run on mobile phones, in headsets for AR and VR, and also in drones. A lot of these devices have quite advanced visual SLAM systems. I think it would be fair to say, though, that all of these are kind of fairly preliminary products. So what they get from their vision systems is generally they'll build a sparse SLAM map of a scene, which they can use for pretty accurate positioning. They'll have some level of dense and possibly semantic understanding of the scene around them that they can use for intelligent action. But I still think we have a long way to go. So just as a little bit of vision, imagine some of the products we might aim for in the longer term future. And I should just explain this term, spatial AI. So this is my kind of term I've been using recently to describe not what I think comes after SLAM, but what I think SLAM has always been trying to do and has always been kind of gradually evolving towards a much more sort of general spatial intelligent sense of the scene around you. So what might that enable once it gets better? So for instance, general purpose home robotics. And I should say that this picture here is just something from the internet that's certainly not representative of any real product being built by any real company. But imagine a robot that really could, tidy up a room in a general way. Now that product doesn't exist yet, and it's a really, really hard thing to build. And I think it's especially hard to build once it has to fit within the constraints of a real product of price, aesthetics, size, safety, power usage, and all of those things. And here's another product that doesn't exist yet. I know a lot of companies are working on this, but a really breakthrough augmented reality product that I think when it exists will completely change the world, and ultimately I think probably become the next major computing platform that may replace smartphones. So this would be the AR system that might provide a robust and accurate real-time overlay and spatial memory of all places, objects, and people that a person has ever seen. You could ask it intelligent questions, where did I leave my keys? And it would just tell you. But yeah, again, for this to become a breakthrough product, it has to fit very, severe constraints. It probably has to weigh not much more than a normal pair of glasses, and it would have to have all-day battery life. So really, the point I'd like to make in both of those areas, which interestingly, I think either in robotics or in augmented reality, whether there's a human in the loop or not in these systems, I think that the capabilities you need from a spatial AI system are actually really quite similar. They need to build these intelligent semantic geometric representations of the scene that can be used to ask questions. But we're still miles away, I think, from where we could possibly get to in this area. So there are some current products that do already exist. There are research prototypes, in places like my lab, in huge labs in companies, of course, and other universities. But then there's this big gap to full spatial AI. And I think especially when we want to get these really high capabilities, but also within the constraints of real products, so running especially on low power, on cheap hardware and all that kind of stuff. So we're going to be working on this for a long time. So I've been thinking about this quite generally, thinking about what the capabilities are that we would really want from this spatial AI system, and then how we might actually cross this gap to achieve these capabilities with efficiency. I've written some papers about this that you might be interested in. There's two of these future mapping papers, which are really sort of discussion position type of papers with some technical content, and they have some hypotheses. So in the future mapping 1 paper, we have the basic hypothesis that there's some commonality to a spatial AI system. So whatever the application is, whether it's a home robot, a drone, or an augmented reality system, it's going to be building some sort of metric geometry, combining that with semantics, and there's a sort of general set of things we're trying to achieve there. Of course, then subject to many different sort of performance measures and constraints depending on the different systems, but those number of parameters of different performance measures and constraints may be relatively few. So that's a hypothesis in that paper. So turning a little bit to where are we now in terms of the sort of systems we can build now, especially in university research labs. So we've been through this sequence of research in SLAM. We had early visual SLAM systems. So for instance, my mono-SLAM system, originally from about 2003, was one of the first real-time single camera SLAM systems that could actually work on a monocular camera and build a real-time 3D sparse map. We went through dense reconstruction about 10 years ago, systems like DTAM, Connect Fusion. And then more recently, we've been interested in adding this semantic layer. So for instance, I'll just show a very quick video here. So semantic fusion was a system that would combine a dense reconstruction system with a CNN-based network that would provide semantic labels for frames and try and fuse all of that together into a real-time dense semantic reconstruction of a scene. So that worked, somewhat reasonably well. But I think what I'd like to point out is both the results are, far from perfect and probably not yet really usable for anything useful. but also this. So this is a complicated and very heavyweight system. And in some senses, what we've been doing over the last 15, 20 years especially, has just been throwing more and more compute at these problems, and we're able to achieve more, like dense mapping, like semantics, but at the cost of this complicated heavyweight system. So don't worry about reading anything on this, but this is just a sort of rough sketch of the kind of system diagram of something like semantic fusion with computation blocks in yellow, with data in green, with all the data that's passed between these blocks. So semantic fusion ran, it was a CPU, GPU system. It was using a depth camera as input. It had rather large and expensive representations. So the representation of a room was using circles, I think 5 million circles or so representing a room. It had then, data going through CNNs, and it was pretty complicated. So, and using hundreds of watts of power, I think. So the main point is this is very far from something we could embed in a tiny, efficient device. So how are we going to attack this problem? And I think in our lab, we have two key lines of attack approaches that we're taking. One is to think about representation. So especially think about the blocks of data and the flows of data through a system like this. Can we do something more efficient than sending around, huge, images, 3D volumes and things like that? And in particular, machine learning is helping us a lot on that area of research. The second line of attack that I'll come to in a second, and is probably most relevant to this workshop, is hardware. But just to say something briefly about representation first, and a couple of the things that we're trying in our lab. So one kind of key one that we've been looking at for a long time is, rather than building up a map in terms of layers of sparse features, dense geometry, semantics, what if we kind of cut to the chase and directly make a map at the level of objects? And we've had several nice papers on that, but I think the most recent one that would be worth looking at is called Node Slam, where we essentially can build a map of a scene as a graph of objects that also have individually optimizable shape parameters. So when we detect objects in this scene, we can actually fit their shape based on prior knowledge of the kind of family of shapes that make up each of these particular object categories. And then those objects basically become our map. So this is in fact a very kind of efficient semantic representation of this scene. The other kind of recent work in representation, I'll quickly mention something we just very recently made public, a system called IMAP. So this is another system that kind of uses some deep learning in the loop of a SLAM estimation system. And it's using a general MLP network as a unique scene representation, and we actually optimize that network in real time against a sequence of input depth images in order to build a representation of the scene, which is actually quite efficient. So this is a scene represented by a neural network, which fits into about a is that right? About a megabyte of weight. So it's really a very efficient kind of map. And you'll see that after a bit of time, it optimizes into this smooth and pretty high quality representation of the scene, which has very nice properties like it fills in holes automatically. So I don't have much more time to talk about this now, but certainly have a look at the full video and paper online if you're interested. And just let this part of the video finish. Yeah, let's just go to here where we can see the full kind of reconstructed room. And in fact, something we're really investigating now is the properties of this reconstruction with regard to how the network has kind of compressed the scene. And what we're investigating now is how we can actually build semantics into this as well in a very efficient way. Okay, so that's work on representation, which is very much ongoing, but I'd like to talk about the other aspects here of how we're going to really improve on this, which is hardware. And this is something I've been interested in for a long time. So, you know, as I mentioned, inspired by things like Professor Ishikawa's work from a long time ago, this general kind of observation that we've been using hardware for vision and AI that wasn't really designed for vision and AI. It was designed for other things like, you know, video games have inspired a lot of things like GPUs and depth cameras like Kinect, for instance. But we're entering an era now much more where people will be designing hardware for AI. And in particular by hardware, I mean sensors and processors, and then also presumably the bringing together of those things that people in this workshop are particularly interested in. So when event cameras, well, not when they came out, but when I first heard about event cameras, I was immediately interested in that. I had previously been pretty interested in high frame rate vision, but had always come up against this issue of, unless you're kind of building the processor into the high frame rate vision system, then you've got this huge data flow, and that seems like a problem. So an event camera immediately gets over that by only sending you the differences. And back in 2014, we did some of the first work on showing that you could actually go from a real-time event stream to a pretty high quality, intensity reconstruction of the scene while simultaneously tracking the motion of a camera with respect to that. So this is some of the work I did with Hae Kim back in sort of the early days when event cameras were still not very well known and were only sort of starting to cut through into mainstream vision and robotics. So that was it, event cameras, that was very useful to me. And then the other kind of thing that was really important was a project that I was involved in, so involving several other people who are on the call here now, but a joint project with Imperial College and the universities of Manchester and Edinburgh, really trying to think about what was going on in processing hardware and how the algorithms we were using in SLAM relate to that. So in particular, we produced in this project tools like SlamBench, which is a SLAM benchmarking suite, but which is not just about accuracy, as most of our benchmarks are. It was also about computational performance, and we had sort of common algorithms that we could run on a range of processors, from a huge desktop GPU down to tiny embedded boards. And the idea was really to look at the algorithms we were using, figure out which parts of those algorithms were good or bad for particular sorts of processing hardware, you know, whether you were serial or parallel, for instance. And we learned a lot by doing that. And I think that's really got me, you know, into the frame of mind now of thinking about what are the right sorts of processors we should really be using for this sort of work. And if you look at what's out there now, there's CPUs and GPUs that we all know about pretty well, but now there are really interesting new things emerging. So in fact, this slide comes from the company in the UK called GraphCore, and they have a new processor, which they call an IPU, or an intelligence processing unit, which is a chip which is massively parallel like a GPU, but it has a very different sort of structure in that each of these parallel cores can be running a very different program. And then it has a very kind of high performance interconnect structure, so that pretty much all-to-all communication and message passing between the cores on a single chip is possible. And then it has a lot of memory actually on chip. So each of these individual cores has a significant amount of memory that it can use. So these sort of processors are suitable for, you know, sparse graph message passing type of algorithms. So this is a visualization from GraphCore. So their chip at the moment is being sold as a server chip with the application aim of accelerating deep learning in the cloud. This is one of their visualizations where they take a neural network and they look at the connectivity structure of all the computation that it does, and they map that basically down onto their hardware and figure out what's the best way to lay out all of this computation if you like, geographically on the chip. And this is just a, a cool visualization that gives you some idea of how that's done. So very much inspired by that, and this is something else discussed in the future mapping paper. I've been thinking about, what is the graph-like structure in the SLAM problems that we are interested in, and how might we therefore think of laying that out on hardware. And this has led to very kind of interesting thinking of thinking, well, where are the graphs in SLAM? A lot of the ways that we represent maps in SLAM have a graph-like structure, and there may be computation we can actually do in place within a map like this. So supposing, think of something like a loop closure operation, it's kind of an optimization on a graph. We have like real-time graphs similar to the thing I showed you in the semantic fusion picture of computation and how it's connected. And then thinking more generally, some of this processing might be embedded in a single chip, like a graph processor might store your map, but other parts of this graph, I think, can be much more spread out. So maybe among multiple processors and devices within a single unit, like a robot, it might have cameras, which could have processing built into them. It might have sensors and other actuators that might have processing built into them. And then this robot itself might be part of a larger network of multiple robots. But anyway, you can imagine a big graph connecting all of the processing and storage that a device like this wants to do. So what I've been really focused on in the last year or two is, how would we actually do all that processing in a general way? And processing on graphs in SLAM in especially is pretty well understood these days. And we have the factor graph formulation, which means you can lay down any probabilistic inference problem and draw it in the form of a graph where you have the variables that you're interested in, these white circles here, connected by factors, which basically represent your observations. And what you're trying to do in a factor graph is inference, so determine the most probable values of these variables given the observations that you have. So there's a very nice new review article about factor graphs from Frank Delert, who's been someone who's really pushed this formulation in robotics and vision. But have a look at this review article. But there are many algorithms for doing computation on factor graphs, and I've been interested in the ones that can actually have this distributed character. And in particular, there's this sort of algorithm called belief propagation, which you can do computation and inference on factor graphs in a completely distributed way with kind of node-based computation and message passing. And I think a lot of people have dismissed belief propagation for a long time, but we think it's a really good time to go back and look at it again. And especially the Gaussian belief propagation is a really, really general formulation. So the Future Mapping 2 paper is all about Gaussian belief propagation and how it could be the right tool for very general use. So I'm just going to show you something quickly here, which is, it's a kind of online article that we've actually been working on recently to illustrate Gaussian belief propagation. So this is work mainly led by Joe Ortiz, who's one of the PhD students from my lab. And this is hopefully something that we will be publishing soon. But we really want to give people a good feeling for the properties of Gaussian belief propagation. And we've got inside this various demonstrations. So here's the first kind of simple one. So what we're trying to do here is fit a set of points to a 1D set of height data. So imagine we've got these red observations, and we're trying to estimate the heights of a surface along a regular array of positions here. This is what the factor graph looks like. Actually, if I move down to this one, I can show you interactively. So I'm going to make a few clicks here to sort of lay down some data. And belief propagation can work, first of all, by passing messages sequentially from variable to variable. So you'll see that as we pass these messages along, we are improving our estimates of the height. So each of these height estimates also comes with a precision or a variance we can estimate. And that's therefore then the fitted line here. So where this is a factor graph where we both have data terms and smoothness terms. So we want the whole line to be close to the data, but also smooth. And we can click on this to show that this is actually the same result as we get by a sort of standard inference message. But what's really interesting, if I clear this all again, and let's put some more data down here, is all sorts of other sort of message passage patterns also work. And this is what really interests me in spatial AI. So here we're going to iterate a sort of fully parallel message passing. So this is as if each of these variables is stored on a different processor, and they can pass messages between themselves synchronously. So after a few iterations, we get to the same convergence, or we can even do something that's even more sort of ad hoc. So let's say I lay some data out here and then just start passing random messages. So this is now, every time I click this button, a random node will pass a message in a random direction. And if I do this enough times, which isn't necessarily that many times, we need to get lucky and for a message to get passed to that one that's down there. And there we go. But after not many iterations there, we're again pretty close to the true marginals. If I just do a couple of these iterations, we should converge. So this is the amazing property of belief propagation for me: convergent behavior with arbitrary computation patterns. I really think that's the sort of property we need. So I don't have too much more time, but just to show you a couple more examples that are in this paper. So that was a sort of just a 1D line fitting problem. This is a 2D kind of relative pose problem, which is pretty much like a pose graph problem that we have in robotics. So we've got a set of 2D nodes here with relative 2D observations between them. And then we're going to solve this by belief propagation, by passing messages between them. And you can see the blue estimates in belief propagation and the green estimates come from a more standard method. And belief propagation converges to the correct answer pretty quickly. We can also, achieve the same thing by random message passing in this example. It, obviously takes more messages. But this, remember, is processing that can be done in a completely distributed way. It can even be completely asynchronous. So it really has the right properties that we're after. So a couple of other things about Gaussian belief propagation that we've shown recently. One is that you can use nonlinear measurement models, no problem in this. You just have to linearize your constraints all the time. Another is that you can use robust cost functions. So we have this nice trick. So if you want to use, for instance, not just Gaussian factors, but factors with a Huber kernel, which can take into account the fact that some measurements are just wrong, we can also do this in Gaussian belief propagation, and this really works. So here's just a quick example of that. So going back to the 1D problem, so here we've got a set of points in a line, but with a couple of outliers. If I'm trying to fit a smooth line to this, so this is just going to run continuous belief propagation. This is with a standard Gaussian function that treats all the data equally. This line is really pulled out of place by these two outliers. But if I switch to a Huber kernel, it start to ignore those outliers much more, as anyone who's used to robust estimation will be used to. If I just try something else here, let's try a set of data with a step here. So if I run this with a standard Gaussian kernel, I get this smoothed out step, whereas when I run it with a Huber kernel, we can preserve the edge. So that's like edge preserving smoothing. And in fact, the last thing I'll quickly show you here is how we can use that for image processing. And now that this now gets very close to what we're interested in the workshop. So suppose we've got this noisy image here. Just find the right thing. So we've got a noisy image and we want to denoise it by removing the noise, we can do that by optimizing a factor graph that looks something like this. If we do that with a standard Gaussian function, we can remove the noise, but at the cost of blurring the whole data out. Whereas when we do it with a Huber kernel, we can remove the noise, but keep the edges in the scene. So I should say that this demo here is running in real time on my laptop. This is using WebGL behind the scenes, so it's running fast because we're actually using a GPU. And a GPU here works well because this is a computation pattern on a regular grid that fits very well with what GPUs do. But in fact, the talk after the coffee break from Raluca Scona from our lab, we'll be talking about a much more general use of belief propagation that includes not just neighborly factors here, but also some longer distance connections, and show how belief propagation is much more flexible than the sort of computations that we're normally used to, and may enable, you know, new sorts of competence. Okay, so let me just go back to the main slides and finish off. So yeah, so I'm very excited about belief propagation, and I really like this term factorized computation, which is from a paper from some of the later speakers. So Piotr Dudek, Julien Martel, for instance, were involved in this as a really good way of thinking about the sort of computation which I think is right for mapping onto hardware. The most kind of concrete thing that we've published so far with Gaussian belief propagation was showing that you can do bundle adjustment in this completely distributed way, and we implemented that on GraphCore's IPU and showed that it could be, you know, up to 30 times as fast as running Ceres for bundle adjustment on a CPU, which is a chip of kind of the same size. So, you know, one of the messages I want to get across is, you know, to get to full spatial AI, we need to map processing onto hardware, but we can't just map the easy processing onto hardware, things like feature detection, you know, image smoothing. We need to map the complicated loopy type of stuff that we would normally have to always do on a CPU, because you can't do bundle adjustment very well on a GPU. But if we think more generally about these things, the right sort of algorithms and the right sort of hardware, we might eventually be able to map the whole of that complicated processing that we have in something like a semantic fusion system onto new hardware that might be really efficient. Okay, so I think I need to finish up. So just to conclude, so spatial AI research, I think we're going to be doing it for a long time. It's about efficient 3D scene representations and systems for incremental scene understanding. We should be interested in co-design of processors, sensors, and algorithms. And especially I'm interested in integrated graph-based algorithms for estimation and machine learning. And just to quickly mention my affiliation, so academically I lead the Dyson Robotics Lab at Imperial College, which is an academic lab working together with Dyson, especially with interest in home robotics. And I'm also co-founder of SlamCore, which is a London-based startup working on applied spatial AI solutions. So thanks very much.
Thanks a lot, Andrew, for the talk, and again, like these little demos. So I saw you were running that locally, but are you gonna post that somewhere so that we can very quickly play with it? Okay,
so let me just stop my screen sharing. So we are planning to try and publish that imminently, but I don't yet have a time.
That looks fantastic. This is like the way you want to be taught this type of methods, because
I wish I'd had it, yeah, because it took me a long time to understand belief propagation.
Yeah. So, well, for the questions, I suggest the following. Given that there's a coffee break and we have a fantastic Gavertown, I would suggest that we all hop on Gavertown to have some simile human-to-human interaction. And I'll post the link on Slack, this is on Slack. I'll put it on the YouTube channel right now in the chat. here. I'll put it also for the speaker in the chat here. And so then we can continue the discussion, and we'll reconvene in 30 minutes approximately. So 2:30 a.m. for me, or whatever time it is, wherever you are in the world. And we'll have presentations of papers and more keynote speakers. Piotr will have the presentation of Raluca, and we all hope to see you there in 30 minutes. And till then, see you on Gavertown.
So the link is not yet in the YouTube chat. Shall I post it there?
So yeah, Raluca is in Zoom. So I think, yeah, she's here.
I said the GatherTown link is not yet in the YouTube chat.
Oh, yeah, sorry. It is, yeah. It is
Is it?
now. I can see it, yes. It's on the chat, yeah.
Oh, there it is. Yes, sorry, I'm being nosy.
Yes.
I'll see you in GatherTown.
Sorry, hi, I just stepped away a bit.
Luca, you there?
Hello. Yeah.
Hello. You ready?
Yeah.
You got like 5 minutes, but 3 minutes. But
Okay. I can share my screen already, or no?
I don't know if you can. If Sajat is still sharing his.
Oh, I see.
Well, how would you like to be introduced today?
Oh. Yeah. Can you hear me?
Yeah. Yes, that's good. Yeah, see an interesting one. Don't know if Stefan's arrived yet. Don't see him. Okay. Looks like Sajad's stopped sharing, so if you want to put your first slide up.
Okay.
Do you have?
Sorry, there was too many terminals to handle. I just got confused, and apologies.
Yeah. Can you hear my? Can you see my screen?
Yep, seeing the whole screen.
Okay, so let's just maybe in a minute. Start.
Sajad, do you want to use the spotlight thing in the other town to try and tell everyone that we're starting?
Sure, just give me a second.
And have you seen Stefan?
Sure, just give me a second.
Shall we get started then?
So hello everyone. The new session, the session number 2 is starting. Please, yeah. The speakers, yeah, are ready to start their talks. So we're going to start in a minute. it will be again streamed live on YouTube.
I'll get started now. Excellent. So yes, welcome to the second session. We've got 3 invited talks, which will be really interesting, and we have 2 papers, so 2 submitted papers that will be presented, and we also have the sponsor talk. So without further ado, I'd like to introduce Raluca Sconia. Raluca is a research fellow in the Dyson's Robotics Lab at Imperial, and we've heard a little hint of what I think she's presenting from Andy in the previous talk. So yeah, without further ado, it's really interesting. So Raluca.
Yeah, so hi everyone. Yeah, I'm Raluca. Thank you very much for the invitation to this talk. So yeah, I'm a Dyson Fellow at Imperial College with Professor Andrew Davison, and today I'm presenting a project on scene flow estimation with varying rigidity for a graph processor. So yeah, while this workshop is focusing on the Scamp and per pixel processing, I would be very interested to hear your opinions on how this work could relate to that kind of processing as well. So scene flow is a motion estimation problem. More often we encounter optical flow, which tracks the 2D displacement of every pixel in an image. For example, for the red patch in the top image, optical flow would estimate its displacement along the green and blue segments in the second image. Scene flow is the 3D equivalent of this problem, where we track the displacement of each 3D point between 2 time indices. On the right, the red and turquoise point clouds represent the input. The blue lines connecting them represent the motion estimate from the flow field. In scene flow, one can estimate a 3D translation vector per point, or can also include 3D rotation. These quantities are useful in real-time robotic applications. Scene flow could be fed into a motion segmentation system that would allow the robot to differentiate between different objects in the scene based on their motion. So even if a robot hasn't seen an object before, it will still use this information to detect it and avoid collisions with it. Scene flow could also be used to decide which portions of the scene are static and should be reconstructed, and which objects are moving and could be tracked in time. So scene flow is a nilpost problem, and the rigidity of the flow field can be specified depending on the application. For example, if the task is to estimate the motion of non-rigid objects, such as people, one could implement local regularization. This would enforce that neighboring pixels would have the same motion, which would result in a continuously deforming flow field. So in this example, flow vectors on the arms are allowed to be much larger than those on the torso, so to better capture the person's motion. This could also be useful when capturing the motions of other non-rigid objects, such as curtains flowing in the wind or pillows being squished. We can also implement piecewise rigidity if we have information that the scene is composed of multiple moving rigid objects. So for example, in a traffic situation, one could estimate a single 3D transformation for each car, as these are rigid objects. Finally, the most extreme case is when the scene itself is fully rigid. So this is equivalent to visual odometry, as in this particular case, one would aim to achieve a constant flow field, which represents the camera motion itself. So to tackle these situations, different formulations for visual odometry or scene flow were developed, which are not necessarily transferable between these different scenarios. So yeah, in our work, we explore if we can bridge the gap between continuously deforming scene flow and rigid visual odometry. We propose a factor graph formulation for RGBD scene flow based on pairwise Markov random fields, where the variables are per pixel flow values and with 2 types of factors. The unedited photometric factor warps 1 pixel from the first image towards the second to minimize the photometric error. We also impose 2 types of pairwise smoothing factors. Local smoothing is enforced between pairs of neighboring variables, while global smoothing is enforced for pairs of variables which are far from each other on the image plane. This is expensive to implement, but we leverage the IPU to process this in near real time. So the Graph Core Intelligent Processing Unit, or IPU, has 1,216 cores that are connected to an ultra-fast all-to-all communication fabric, which enables us to send data between these cores. So the main result of our work is that depending on how we set the configuration of the smoothing factors, the behavior of the algorithm can change significantly, meaning that the flow field will display different degrees of rigidity. So yeah, next I will describe the formulation. So we estimate a flow vector of 3D translation and 3D rotation for every pixel in an image. And there are 2 types of factors that we optimize for. One is a photometric alignment term, which warps a pixel with the estimated flow value and computes the photometric error between the two images. This means that if we had two images and a perfectly estimated flow field, we should be able to warp the first image towards the second one and have these two images agree almost perfectly. The second constraint we impose is pairwise smoothness. So on the bottom right, we show a diagram of our formulation. In orange, we show the variables that are estimated for each pixel. In red, we show the per pixel photometric factors. We also show green smoothness factors between neighboring variables and blue smoothness factors for variables that are far from each other on the image plane. So this particular diagram corresponds to an image with 2 rows of pixels. So in this particular example, the factor S1n would enforce smoothness between the variable in the top left corner and the variable in the bottom right corner of the image. So to go into a bit more detail about the formulation, we estimate a 6D motion for each pixel, composed of a 3D translation and a 3D rotation twist. To warp a point, we convert the twist to a rotation matrix, and then we apply this translation. We formulate a Gaussian photometric factor for a pixel with 2D coordinate xi. The measurement is the intensity value at location xi in image 0, and the measurement function warps the pixel from image 0 to image 1. We read the depth value at xi, unproject it to 3D, apply the warping, project it back to the image plane, and then read out the intensity value. So ideally, these values should be as identical as possible to indicate that the images are well aligned. Finally, in the smoothness factors, we just penalize for the difference between specified pairs of flow vectors. So we formulated everything using Gaussian terms, so we can solve this using maximum a posteriori estimation. So next I will describe our implementation. So to start, I will first describe the graph processor a bit. Yeah, so it consists of 1,216 cores, each with local memory and 6 threads. The cores are connected to an ultra-fast all-to-all communication fabric, so they can send data between each other. There are 3 phases to code execution. First, each core executes its local code using the data that it stores locally. Afterwards, all cores wait until execution has finished. Finally, data is copied between the cores through the data fabric. The IPU allows for increased flexibility in the computational structure of graphs. However, this structure has to be fixed at compile time. Therefore, we have to decide on the structure of the factor graph for our flow problem, fix it, potentially save it to file, and then we will be able to read it and reuse it as needed. So this processor is quite well designed for message passing systems. So we solve our factor graph using distributed optimization with Gaussian belief propagation. So this is an iterative solver, which consists of a few steps. First, the variables receive messages from the factors they are connected to and compute an estimate of their belief. Then they compute messages for their neighboring factors and send them. The factors receive these messages, they relinearize themselves around the current states of the variables and send messages back to the variables again. In GPB, we iterate over these steps for a fixed number of iterations. Finally, I will describe the structure of the factor graph itself. So we want to experiment with different kinds of regularization in this project. So in the first configuration, BP flow, we experiment with local regularization only, and each variable is connected via smoothing factors to its neighbors in the up, down, left, and right directions. We use this configuration to simulate deforming scene flow. In the second configuration, BPVO, we experiment with global smoothing only, and here each variable is connected to 6 others that are sampled uniformly at random on the image plane. With this configuration, we aim to simulate visual odometry. So I want to explain a bit why we chose this pattern in this particular case. One other option would be to have a hand-designed pattern where we could connect one variable to blocks of other variables. However, we found this induces unwanted symmetries in our flow field. So for example, if we were to connect the pixels in the top row with the pixels in the bottom row, and then continue with connecting the pixels in the second row with the pixels from the second row from the bottom and so on, we would observe that our flow field would show symmetries along the central row of pixels. And this is something we don't want. We want a flow field that is as smooth as possible. Another option would be to designate one variable as a visual odometry anchor and connect all the other variables to it. This would be inefficient as it would result in an all-to-one communication pattern. Instead, we find that uniform random sampling is a practical solution that produces a smooth and uniform flow field. So finally, in BPVR flow, which stands for varying rigidity flow, we combine both local and global regularization, and each variable is connected to 4 local and 6 global other variables. In this configuration, we assume we are provided with a segmentation mask of which portions are rigid and which are non-rigid, and that we can disable regularization in a particular region by sending empty messages between long-range factors in that region. So by sending these empty messages, we can maintain the computational structure of the problem fixed while allowing for varying rigidity in the scene. So this would be the structure of the graph for a 14 by 10 pixel image, where the orange circles are the variables. The green local factors are formulated over the whole image in the case of BP flow, and where each variable would also have global smoothing factors, as shown in blue. When mapping this graph to the IPU, we split the variables into patches and map each patch to a different tile. So in this example, the underlying grid represents the tile of a processor, and each patch of 2 by 2 variables would be mapped to a separate tile. With this, we minimize inter-tile communication, as local smoothing factors between neighboring variables can run all computation on the same tile. When distributing the smoothing factors, we split them equally between the variables they are connected to. Finally, as is commonly done in scene flow or visual odometry, we formulate our problem using a coarse-to-fine scheme. We solve for the motion field at the coarse level and use the solution to initialize flow values at the next level. So this is required to get more robustness to larger motion between images. So I will describe also how we evaluated our approach. So first, we evaluated BP flow, the configuration that only implements local regularization, and where each variable is only connected to its neighbors. So we compare it with the primal dual flow, which is an RGBD scene flow method that is similar in some aspects to our approach. So they solve for 3D translation vector for each pixel, while enforcing that neighboring pixels should have the same value. They also implement geometric alignment, while we only implement photometric, but our system could also be extended to implement geometric alignment. So on the left, we show an overlay of 2 consecutive images for which we want to estimate flow. In the next 2 images, we show the flow fields from the 2 approaches, which display some similarities. We also evaluated the 2 approaches on sequences of RGBD images. So it is rather difficult to evaluate RGBD scene flow based on photometric alignment, as we require that the motion between consecutive images is not too significant. For this, we used image pairs from other publications on RGBD scene flow, where the authors reported reprojection error results. So we replicate this by warping the second image towards the first, using the estimated flow field, and then reporting the per pixel errors. So from these numbers, it appears that the 2 methods are performing somewhat similarly, which is encouraging, as it means that our factor graph formulation could be a viable alternative to standard methods based on photometric error and local regularization. So I would like to show a qualitative result of a BP flow. So yeah, on the left is our input, which is a stream of 2 people moving sideways, where the motion of the camera is just very slight. And on the right, we show our flow estimation result. So next, we evaluate BPVO, which only implements global regularization, and where each variable is connected through smoothing factors to 6 other variables that are sampled uniformly at random on the image plane. So first, we do a qualitative comparison between BPVO and BP flow to understand the impact of the global regularization on the flow field. We warp a given image with a known motion of 2 centimeters to the left, and we assess how much of this motion we can recover with our rigid scene flow formulation, BPVO. So on the right, we show a histogram of the translational components of the flow field from BP flow, which contains local regularization only, and from BPVO, which contains global regularization. And in red, we show the ground truth motion. So these diagrams show that global smoothing collapses the flow field distribution into a much tighter distribution. So ideally, this would cause the flow field itself to collapse to a single value. But we think these are already quite promising preliminary results. So this distribution is also closer to the ground truth compared to the flow field from BP flow. And we think this happens because variables get access to more global information through the long-range factors, which helps the optimization to converge to a more globally consistent solution. We also think this is an interesting result, as it shows that we can recover global properties such as the camera motion through only local computations. The formulation, however, requires quite smooth motion of the camera. So this image shows the typical performance of the method if the camera is moved smoothly. So it is a sequence from the TUM dataset, where we also reproject the first 100 RGBD point clouds using motion vectors that we sample from the central pixel in our flow field. So this shows, again, a result of BPVO running on the TUM sequence, where the motion is slow in the forward, backward, and sideways direction. So we can see that if the camera motion is smooth and slow, our method can recover the trajectory quite well. However, we do see that on this particular example, we experience a slightly larger drift compared to dedicated visual odometry methods. So we also report trajectory error results on the TUM dataset. So we compare our method to two benchmark pure visual odometry approaches, namely DVO and VOSF. So both DVO and VOSF implement RGBD visual odometry based on photometric alignment, while VOSF also computes piecewise rigid flow estimates. So for our method, we report errors for motion estimates that are the average over the whole field, and for a sample flow estimate corresponding to the central pixel. So we can see that the sample flow estimate performs similarly to the average, which means that a representative motion estimate can simply be read out from the flow field without additional processing. However, our method is less accurate in this case compared to standard visual odometry methods, but we think there are things we could improve. So for example, the rotation parametrization could be improved to better mimic what is implemented in standard visual odometry methods. So standard VO normally estimate incremental motions, which they use to repeatedly warp one image towards the second and always relinearize their cost functions around 0. In our application, we are estimating the global rotation quantity directly, but we think replicating this repeated relinearization around 0 in GBP may improve accuracy and robustness to recovering large rotation estimates. Another idea we have is to vary the weight of smoothing factors depending on the stage of the optimization process. So here we will impose less smoothing at the start of the optimization to allow the solver to explore a larger part of the search space. Towards the end, we will increase the smoothness to force a globally consistent solution. Nevertheless, we think these results are promising, as they demonstrate we can capture global quantities, such as the camera motion, from only local computations. So finally, we also want to evaluate BP-VR flow, where we have both global and local smoothing in the same image. So in the top left, we show an overlay of the input images that we want to estimate flow for, and the flow fields estimated from BP flow and the primal dual flow system are also shown below. So for BP varying rigidity flow, we use a segmentation mask provided by Mask-R CNN to tell us which parts of the image are moving independently. And we use this knowledge to disable global connections between variables of different classes. So in this particular example, we would disable any global smoothing between linking pixels that belong to a person and those pixels that belong to a background. So this allows us to achieve a flow field where we have strong discontinuities between objects of different classes, and also where the motion for the background is smooth. We show again the distribution of the flow field from BP flow and BP-VR flow respectively. For BP flow, the histogram again is quite broad, while the BP flow field shows a strong peak, which corresponds to the camera motion, and the remaining broad distribution corresponds to the motion of the two people. So this is a qualitative comparison of BP-VR flow and BP flow. For BP-VR flow, we also take a segmentation mask, as I mentioned before, and disable global smoothing between the background and the people. So we can see the motion boundaries between the people and the background are much sharper in BP-VR flow compared to BP flow. The background motion, which corresponds to the camera motion, is also very smooth in this case. So regarding the runtime, the table reports how many milliseconds are required to run each level of our estimation pyramid. In total, we use 4 levels and run 10 iterations on each level. Overall, the runtimes for the algorithms are 17 Hertz for BP flow, 14 Hertz for BPVO, and 10 Hertz for BPVR flow, which requires the most data transition through the data fabric. So the graphs take a few minutes to compile, and afterwards they can be written to file. So reading them and uploading them to the processor takes around 1 second and is done once at the start. So to conclude, our contributions were a factor graph formulation for RGBD scene flow that we can run near real time on the IPU. The novel aspect is that we can implement global regularization through the long-range smoothing factors, which can also run near real time. We have demonstrated that we can capture global properties such as the camera motion from pure local computations. We have also investigated how the behavior of the algorithm changes when we change the configuration of the smoothing factors. So overall, we think this is a promising first step in the direction of distributed motion estimation. In future work, we are interested in improving BO through better rotation parametrization or by using motion priors. We are also interested in integrating motion segmentation itself in the optimization process, and also interested in methods for integrating temporal consistency, where flow estimation runs over several frames. So yeah, finally, as this is a Scamp workshop, I will also be keen to hear your opinions on this work and on any thoughts you have on how this type of method could be related to pixel-wise computation. So yeah, thank you for listening, and please let me know if you have any questions.
Excellent, thank you very much. Yes, please do put your questions in whichever chat is nearest to you. And I will start off with asking, so you're thinking of putting segmentation involved inside the process. I was wondering, do you think it's possible to have the segmentation mask as a probability, where you take your long connections and you include like a probability of the segmentation instead of like a ground truth assumed one? And wondering, would that improve the results, do you think, or would that just be extra computation that doesn't actually help?
I think that could help, because so in this particular project, we are using segmentation masks from mask CNN, which are not ground truth segmentation masks really, but they could be, we could use them as like an initial guess for what the mask is. So yeah, we could maybe formulate some type of prior, maybe on the class of each pixel that we initialize. We would initialize using the maybe mask CNN result and try to maybe refine this segmentation using our system.
Cool. Excellent. There's one from the chat. If one had flexibility to change the connectivity on IPU dynamically, would there be a benefit to doing so at runtime?
I think so, yeah, because so I will go back to one of the slides. Yeah, so in this particular, what can happen in this particular case is, let's say, so this particular variable here, is connected to these other 4 variables. But let's say this particular variable belongs to the background and all these other 4 are corresponding to differently moving objects. So yeah, in this particular case, we wouldn't really get any meaningful data from these 4 sort of neighbors. We would be relying on our local neighbors here to constrain our motion properly. So if we could change the configuration at every timestamp, I would probably change it to enforce that like every pixel that belongs to the background is connected to pixels that are also a part of the background. And yeah, this would minimize sort of the possibility that we send kind of information that's not useful.
Cool, thank you. There's another one. It seems there is something like a chicken and egg problem to solve, in which you'd like to know where to break the edges of the factor graph at some places, but to know which edge to break, knowing the flow a priori for motion segmentation would be helpful. Have you thought about some way the graph configuration, the edges, could be dynamically changed in a factor graph BP framework that usually assumes the edges are fixed?
So I agree, it's a chicken and egg problem, which makes the joint optimization, I think, really difficult. So I think, if the way I would work on it right now is I would, for sure, I would always use the local smoothing, because we do want that neighboring pixels have similar flow estimates, and we do have these kind of robust factors that Andy presented before. So where we do have, if there is a large difference between motions in neighboring pixels, we can still sort of have this kind of cutoff. And then I think what I would try first is to do some sort of region growing on the flow field, assuming that only the local smoothing is imposed first. So I would try maybe, at the start of the optimization, maybe, but this is a very difficult problem. But so every pixel could have a different class, and then as we run the local smoothing sort of version of the flow field, because we can say, okay, if pixels in a particular region have quite similar flow values, then we can collapse the class for these pixels. And as we grow those regions, if there are two pixels in a particular region and there is a long range smoothing factors between them, I would then enable this long range smoothing factor. But I agree, it's very difficult. I agree. So I think, the point that you had first, that maybe using an initial mask, that would be very helpful. I think that would probably lead to sort of more reliable and more robust results compared to trying to do it from scratch. But I think doing it from scratch is also interesting.
Yeah. Just a small question. When you have the segmentation marks, do you use that to send 0 messages for the local smoothing as well as the long range smoothing?
No, but we did experiment a bit with down weighting the smoothing. I'm just going to go here. So in this particular example, we experimented with down weighting the smoothing between the pixel belonging to the person and the neighboring pixels belonging to the background. But we didn't cut them off entirely.
Okay. And then, so would you think do you reckon there's a way to sort of do this asynchronously? So it sounds like at the moment, sort of, it's an all-to-all sort of everyone sends a message at the same time sort of process. Do you think there's an asynchronous sort of method to this, whereby every pixel just fires off to its neighbors as and when?
Yeah, I think that could be interesting to try. We haven't tried it ourselves. So as you say, it's exactly like that. First, just all the variables compute their beliefs, then all the variables send messages, then all the factors compute and all the factors send messages. But I think it will be quite interesting to send messages asynchronously. And this is something we could actually experiment on the graph processor itself. So it's something we could look into.
Yeah, if you don't mind me saying something quickly, I think there's nothing in the method that wouldn't work with an asynchronous processing resource. So if you'd imagine that the front end of this was even kind of event-like, such that each core was waiting for something to change and then would send out messages when it received something new, that could be very attractive, couldn't it? Such that when there's nothing much going on in the image, those processes kind of go to sleep and then they kind of wake up. So if you had something like an event camera front end with like a graph of processors sitting behind the pixels, which were able to kind of wake up and go to sleep, that could be a very, very efficient way of doing it. And I think that the method, would still, you wouldn't have to change very much in the method for that sort of setup.
Cool. Well, thank you again, Relika, for your excellent talk.
Thank you very much.
Now 11 o'clock, so I think it's time to move to Stefan Isler. If you'd like to share your screen. Oh, you sound muted there, Stefan.
Can you hear me now?
Yes.
Wonderful. Thanks a lot for having me.
So Stefan is the head of software at Sony Advanced Visual Sensing, where he's apparently mainly focusing on novel visual sensing solutions. So some interesting things to come out of that. We've heard, I think, a bit already about the collaborations between the University of Tokyo and Sony, some other processors. So I'm sure there's a lot more stuff hidden at Sony that they're working on.
It's a huge company, so there is a lot going on. Even us involved within Sony sometimes don't know all of the stuff that is actually happening within the company.
Nice.
Let's see. Can you see my slides?
Yep, your slides are good.
Wonderful, wonderful. So I'll be talking about how we at Sony Advanced Visual Sensing approach the design of our visual sensing systems. But let me start with an introduction of who we actually are first. Of course, Sony does not really need any introduction. You all likely know PlayStation, Sony Pictures, Sony Music, or our excellent cameras, TVs, speakers, or headphones. But what is much less known is that Sony is also world leading in image sensors. In fact, Sony Semiconductor Solutions is the world #1 in image sensor sales. And the portfolio of technologies of Sony Semiconductor Solution includes cutting-edge CMOS image sensors, depth sensors, event-based sensors, but also other related sensing technology. There are research centers spread across the world, and Sony Advanced Visual Sensing is one of these. So we are located near Zurich in Switzerland, and our focus is at the moment mostly on visual sensing systems that involve event-based cameras. And the reason for that is that our team has years of experience with event-based cameras. The majority of our team has previously worked at Untitled. If you remember us, this was a startup working both on event-based sensors, so on the hardware, and on event-based software targeted at applications such as collision avoidance, augmented reality, or virtual reality. If you're not familiar with event-based sensors, let me just give you a very quick explanation. For a more detailed and more broad explanation, I'll highly recommend the tutorial given by Davide Scaramuzza later today, if I'm not mistaken. But for now, the main property of event-based sensors is that each pixel reacts independently and only to changes in illumination. So what every pixel does, it tracks the amount of change in the infalling light since the last time that it has reacted, and it compares this change to fixed thresholds. Wherever the threshold is exceeded, a new reaction is triggered. And this reaction means that information is being sent out to the user, information that we typically call events, hence the name event-based sensors. So what we get as a user is a quasi-continuous stream of information where single pixels tell us that they have gotten brighter or darker and at which time. In this illustration, this animation here, we see a comparison of how a traditional CMOS imager perceives the scene and how an event-based sensor perceives the scene. The scene being this circle with a moving black dot, and many of you will have already seen that. It's a very famous example. And we can see that the traditional imager takes very familiar pictures at fixed frequency with certain exposure time. It will involve issues such as motion blur. If you want to increase the temporal resolution, it will involve a lot of data and a lot of power. And opposed to that, we have an event-based sensor which has a much higher temporal resolution, but it can only see the parts in the scene that are actually changing. So as this black dot is rotating, the pixels in the event-based sensor tell us they've gotten black, they've gotten white, and this is visualized as two dots here in the graph for data points where it has gotten brighter, and the red dots which has gotten darker. And high temporal resolution is one of the main advantages of event-based sensors, and related to this, the fact that there is almost no motion blur. Additionally, thanks to how the pixels are actually designed, what we get from event-based sensors is a very high dynamic range and very low power compared to traditional image sensors. Now, what you might wonder is if we have this sensor that only measures changes in the signal, what actually are the characteristics that we can get out of this sensor? What are the applications that we can use it for? To discuss this, let's have a look at this somewhat illustrative equation. What you want to visualize here are the different parts that make up the changes that are then being sent out by the sensor as events. On the one hand, just the presence of an event, the fact that the illumination has changed by a certain amount, is already very interesting information. It can be used as entropy cues and can be used downstream for things such as smart processing, smart triggering, and wake-up calls, as I will be discussing a bit later in the talk. If you look at the signal, on the other hand, we have, roughly speaking, 3 potential causes of the change of the illumination that falls on the pixel. One, straightforward, is that the light in the scene is changing. Another could be that the reflectance is changing. And then yet another, that there is motion in the scene. And due to the fact that the scene is textured, this actually causes a change in illumination falling on the different pixels. Now, with all of these parts in the signal, we can do different things. If we can control the light that illuminates the scene, we can do things such as active lighting, we can do structured light, we can do active marker tracking, we can do visual light communication. I'm not so sure what we could do by looking at reflectance changes, maybe tracking changes on the skin of a chameleon, but that's maybe not that relevant. More relevant likely is looking at the remaining part, which encodes spatial contrast together with optic flow with the information of motion per pixel. Now, using appropriate algorithms, we can indeed decouple these 2 components and estimate them just based on the events. So we can do things such as tracking, estimating the pose of the camera or of objects in the world, and we can reconstruct the scene as well. Now, what we're really interested in at Sony AVS actually is how can we combine our event-based sensors with the other sensors that are being designed within Sony, be that conventional cameras, be that depth sensors. How can we build the best system for any given application that can exploit the different advantages while balancing the challenges that all of these sensors actually bring, such as a lower temporal resolution for the camera or the depth sensor, or the fact that if the sensor and scene is not moving at all, event-based sensors don't see anything at all. Once we have figured out how to optimally combine these different modalities, the next step to building an actual system, an actual product, is to figure out how to map the different parts of our algorithm to the compute resources that are available. And here is an abstract diagram of typical compute resources found in, for instance, mobile products. So let's have a look at what capabilities and constraints these processing entities actually provide and what we can learn from that. This is only going to be a bit of a high-level discussion, but still I think it's very relevant to understanding how to design an overall system that is efficient and can sufficiently address the challenges present, especially in the real world. Nowadays, sensors can support more and more logic at a very low level, very close to the pixels, also in commercial products. But still, typically, they're accompanied and supported by dedicated, sophisticated, and specialized co-processing units that can do one thing only, but do this very, very well, such as image signal processing or running a neural network. And of course, typically, there's more than just one co-processor, and it does also not necessarily need to be separated, as in this figure, from the sensor. They could also be integrated together. Overall, the target typically is, if we have our algorithms, we would like to have as many blocks as possible to be running on these 2 components. Whatever is left needs to be pushed downstream to the general purpose application processor, which is typically a shared resource And we don't want to take resources away from user applications such as the apps running on a smartphone or another mobile device, be that a robot, drone, whatever it is. So overall, putting it very simply, what we can say that the closer to the sensor, the more simple, specific, and specialized operations would be. But at the same time, they're also typically more efficient and use less power. So clearly, if we have our algorithm that nicely fuses different modalities, what you'll want to do is to push as much of the processing upstream to sensor or co-processors, and also rethink different building blocks, how they're computing and whether they could actually potentially be computed on another cheaper, more specialized block. What we, however, further do to optimize our system is to rethink when each of these blocks does actually need to be computed. So the question that we pose is when to actually compute. And the typical paradigm in visual sensing is that this is all rate-based. We typically have rate-based sensors. We have cameras, we have ToF sensors running at fixed rate. We have IMUs running at fixed rate. They produce their data. It's being passed on to software building blocks. They process it, pass it further down. All of that happens at a fixed rate. And the whole system does not really care whether it's really necessary to run all of these computations. If we are tracking something, if we are doing pose estimation, why would we retrack and rerun the whole pipeline if the whole system is standing still? So clearly a more modern approach tries to minimize the amount of unnecessary processing using adaptive updates. And this can happen from both sides. So on the one hand, we can use the application processor and have it asking the sensing system for new updates. Why should there be a new update if the application processor, if the downstream application has no use for it? So we can achieve or target a somewhat optimal sampling at the output. And then opposite to that, the obvious other side is the sensor. If we have smart sensors at the input, they can actually make the whole system aware of relevant and interesting changes and basically create interrupts and trigger updates downstream. And thinking this further, it's not just the application running at the end or the sensing modality that is at the beginning of the whole pipeline. Every block within the pipeline can do the same thing. Every block that has data's input and data's output can decide if it receives new input data, whether it's the right time to now actually run its computations. And if it does run the computations, whether it's the right time to pass this data onwards downstream. And it can also figure out whether it is necessary to potentially ask the blocks upstream for new data. One example of that would, for instance, be if we have an estimate with an according uncertainty and the uncertainty is growing, we might ask the sensor to provide new data. So having mapped out these different considerations allows us to map our algorithms to hardware and pick appropriate designs. And you might have already figured that clearly fully reactive updates are a very nice fit, especially for event-based sensors. But let's have a look at two specific examples. One very prominent use case in computer vision is tracking. If we go back to our illustrative equation from earlier in the presentation, let's for now forget about changes in illumination or reflectance and just focus on this last term. What we need to figure out for tracking is, on the one hand, the gradients that are present in our scene, and on the other hand, the motions per pixel. And if you look at our modalities, we quickly realize that spatial contrast is very easy to figure out if we have an image. So it makes a lot of sense to use a CMOS imager to calculate spatial contrast. And at the same time, optical flow is something that causes motion, that causes change. So this is likely an interesting use case for event-based sensors. And indeed, if we throw a general purpose tracking algorithm, even just at a very simple task, such as what we have seen from the visualization at the beginning, but in reality, so a moving dot spinning, we can use that to visualize a bit better advantages of how these two modalities can complement each other. So in the left-hand side, you see it running roughly in real time. On the right-hand side, a bit another moment in the data in the video, but it's slowed down. And what we can see here is in the visualization, again, the events are displayed as red and blue data points for brightness changes in a more brighter and darker direction accordingly. And we can see the sparsity of this data and also the high temporal resolution that allows us to track these points. And at the same time, we also see that while the frames do not exhibit any severe motion blur, there's actually too much motion in between frames to properly allow to track these points just based on frames. So this is a clear example of where adding events actually enables the tracking, the proper and successful tracking in the first place. Of course, this also generalizes to other challenging scenes that are maybe more relevant in real scenarios. We see here two videos where event-based tracking based on both events and frames is successful, while a standard Lucas Canade approach here, the implementation from the OpenCV library, actually fails in shaky and very fast motions, but also if you try to track high frequency textures. And what is important to mention here is that the event-based tracking works without any need to co-estimate a camera pose, without the need for a motion model or motion priors, without any need to ensure certain spatial coherence in between features. It's really just the high temporal resolution of events that enables this. But thinking back about our design considerations, what might such a system actually look like if we map it to the processing that we have available? And again, remember what we try to do is to do as much of the processing as possible on sensor and co-processing. And at the same time, we want to run the different blocks that comprise the algorithm as few times as possible in order to minimize the power consumption and potentially improve latencies. Now, for feature tracking, it seems quite obvious that there's no and really absolutely no reason why we would update a feature track if nothing is changing. And the nice thing is that events directly tell us when something is changing. So it stands to reason that it makes a lot of sense to use the events to trigger updates at the times at which our feature positions are actually being computed. The grayscale or frame information, on the other hand, is only needed for gradients. So we don't need it at any other moment, but when we have need for new gradients that we are not yet that we have not yet computed. So in terms of processing, very low level, close to the sensor, what we might try to do is to do some basic noise filtering to ensure that only the necessary events are being propagated on. And then typically we have a stage where events are accumulated. And following this stage, we need to decide when we actually want to run the update. And now, given the fact that we do know the gradients for this feature, we can obviously figure out which events and how many events we indeed need in order to have all of the degrees of freedom of the transformation that we're using in the feature tracking constraint. And before having all of these events, it does not make any sense to run the update. Furthermore, we can push this even further down, such as to a decision that we would like to do the update every 1 pixel throw or every 2 pixel throws, just to kind of constrain the amount of compute that we will have to spend. And this nicely scales the compute as we will spend more compute if there's more motion, but no compute if there is no motion. So this is a very nice property. Now I'm going to run just a little bit over my 20 minutes. I hope this is okay. I would like to discuss just one more example. In this example, we have discussed sensor fusion of event-based sensors with a camera. What if we wanted to do fusion of a camera with a depth sensor, in this case, a time of flight? A time of flight has, similar to cameras, a comparably low temporal resolution, but it uses even more power because of the need to illuminate the scene. So clearly, the high temporal resolution and low power of event-based sensors look as if they are a very nice addition to such a system. So we could try to do two things. If we can use the events to predict depth, what we can do is to either boost the spatial resolution of our depth output, or we could save power by replacing depth measurements of the ITOF sensors with predictions of our events. And this actually can work. You can use a neural network. You can feed it with a depth frame, a starting point, and then with following events, and predict what the depth would actually look like. And this is what you can see in this video here. So on the left-hand side, we can see the events measured by the sensors. There's the ITOF frames in the middle, but only at the beginning, the ITOF frame is actually being fed into the neural network, and then the neural network uses the events to predict what the depth would actually look like. You can see that in this case, the temporal resolution here on the right-hand side is much higher compared to the temporal resolution of the ITOF sensor. And again, if we look at how we can match the different blocks that would be involved in such a systems to our processing, we get a similar picture. We can again use this reactive and adaptive sensing and update paradigm to optimize the compute that we actually need. And here it really depends on our requirements. If we have an application that needs a fixed rate depth output, then clearly the dominant triggering source would be the demand from the application. But on the other hand, if you were trying to save compute, then again, it makes sense to look at the number of events that are actually happening in the scene. And this is because if there are no events, there's likely no changes in the scene, so likely also no changes in depth. So why would we recompute any depth? And if there are only very few events, then likely the predictions based on these events would not be really good, and it makes more sense to just every once in a while capture a new time of flight frame. On the other hand, if you get a lot of events, this would mean that there's a lot of changes in the scene, and very likely the temporal resolution of the ITOF cannot sufficiently sample this motion anymore. And in such a case, it would make a lot of sense to use regular updates based on the events to boost the output of the depth, and hence overall, again, optimize the sensing system using this adaptive and reactive paradigm based on what we can do using event-based vision sensors. Now, with that, I'm at the end of my presentation. If you are interested, please follow us on LinkedIn, and we would also be delighted to see you in an interview and join us at Sony or even Sony Advanced Visual Sensing. So thank you very much, and I'll be ready for questions.
Excellent, thank you. Thank you for a great talk. As ever, please put your questions in the chat, and I'll kick us off with, so you're talking about using applications to sort of pull information from the coprocessor and lower systems, but would that add in latency to the whole pipeline? And would that present a problem in a lot of applications where actually you'd rather have the most up-to-date information, even if you sometimes throw it away?
Yes and no. I guess you could also try to have downstream in the end application an algorithm that is actually able to predict upfront that information will be needed. So in many cases, you would actually know the dynamics of your system, and through that, you could actually figure out at which point you would need new information. So not necessarily, but yes, if it's only reactive in the sense, oh, hey shit, I have too much uncertainty in my system, then it's probably already too late to ask for new information.
Yeah, interesting one. Second question I had was, how do we make event cameras and things sort of robust to sort of natural phenomena in lenses like lens flare or overexposure? Sort of what happens when we reach the limit? So, you know, you come out of a tunnel and everything goes, all the events happen at once because everything's bright for a second. Or is that something that is coped sort of implicitly by event cameras?
I believe the tunnel example is maybe not the best one, since basically there you would just have this bright dot that starts extending, and this is just like a high dynamic range scene that can be handled very well by event-based sensors, as can be seen in various videos in the literature in academia, but also in the industry. On the other hand, things such as lens flare are the same problem as on standard CMOS image sensors. So this is not really my field of expertise, but we have some of the best engineers in these areas within Sony. So I'm lucky to say that we can rely on that expertise to properly code lenses, to properly design the overall system, to at least limit the effect of these phenomena.
Cool. So where do you think the public is going to first see this sort of technology being used? I mean, is it the sort of thing that is going to be on you know, Sony cameras, or do you reckon it's going to be more in the sort of commercial robotics space?
I believe across the board, just if you look at the development of computer vision in the industry, a lot of is focusing on compute, on saving power with all of these mobile devices. And if you run a SLAM or pose estimation, they're just going to be out of power in no time at all. So whatever can be used to push down this power and at the same time even improve robustness, for instance, in the presence of fast motions, is very, very promising. So I really believe that we will be seeing event-based vision sensors entering products, and well, let's see.
Excellent. Oh, we have a question. What can you say about the short-term roadmap for event sensors? Are they going to be higher resolution? Are we going to go for small form factor or higher energy efficiency? Where are the priorities for the short-term goals?
I can not say too much, but if you look at what's been coming out, I think there are some tendencies that are typical also for other image sensors. We start to see higher and higher resolutions, and at the same time, pixel pitches are going down to a certain degree, enabling these higher resolutions in the first place. So these developments definitely happen, yes.
Is there room, do you think, for event cameras that they are often sort of pixel-based events? Do you reckon it's possible as the resolution gets higher, you're going to end up with lots of pixels near each other all firing, or having events? Is there room for more of a hierarchical approach where you have sort of larger events that can compress the information of a few pixels all into one update that can then even further reduce the data transmission out of the camera?
This is a very interesting question, especially it basically relates to how would you downsample event-based data. And it's maybe not as straightforward as for image sensors, since especially if you don't actually know what the absolute values in illumination are at every moment in time, the actual absolute change in illumination represented by events that are neighboring each other can differ quite a lot. So if you were to basically put them together in a at a higher level in a event-based image pyramid, it's not quite clear how to fuse that. I think this is a topic of research in both industry, but probably also academia, how to properly do that. And it's certainly interesting, though. you might have noticed if you have worked with event-based sensors that yes, they are power efficient. Yes, they do not produce a lot of data relative to the temporal resolution, but due to the high temporal resolution, if there's a lot of change, they actually produce high and really high spikes of data, which place quite a high burden on the processing downstream. So these sort of problems need to be tackled.
Awesome. Well, thank you again for your excellent talk. I think
thank you very much for having me.
Yeah, thank you for coming. We are now moving on to the sponsor talk from Wiley. So is that Babak? Is that you?
Yeah, hi. So let me share my screen first.
Please do.
Can you see my screen?
Yep, we can see your whole screen.
So okay, so hi everyone. Many thanks to the organizers for giving me this opportunity to present our journals to this community. My name is Babak Mustafasi, and I'm editor of a number of journals at Wiley, including Advanced Intelligent Systems and Advanced Materials. So you may already know Wiley. Wiley is one of the biggest scholarly publishers in the world. We publish almost 1,700 journals, and the company has several offices all around the world. The headquarters is in Hoboken in the US, and for instance, I'm working in an editorial office in Weinheim, Germany. Advanced Intelligent Systems, which is the main sponsor today, is a part of a very reputed group of journals. We call them Advanced Family of Journals. And they are mostly reputed, or they used to be mostly reputed in chemistry, physics, and material science communities. The top journal is Advanced Materials, and it's one of the most prestigious journals in natural sciences field. But in the last few years, we've started to expand the scope of our journals to other fields. Here in this picture, for example, you can see some of our sister journals. And as you can see, there are some titles whose scope go beyond material science, like Advanced Science or Advanced Theory and Simulations. So Advanced Intelligent Systems is one of our youngest journals. Its scope covers topics related to intelligent systems, including artificial intelligence and machine learning, robotics, automation and control, quantum computing, neuromorphic engineering, and so on. The journal, like other advanced titles, the journal enjoys an in-house editorial system, meaning that all of the editors are employees of Wiley. And in order to have a connection to our global readership or authorship, we have editors in different countries or continents, I may say. So the journal enjoys getting support from a very top editorial board, although the journal is very young. As a matter of fact, we recently celebrated the 2nd anniversary of the journal, but still, we've already published or planned many invited only special issues on interesting topics like soft robotics, space robotics, haptics, and so on. And one interesting feature of our journal is our recent collaboration with Autoria, enabling authors to publish interactive or smart content alongside their papers. And by interactive content, I mean data-driven figures, executable codes, Jupyter Notebook, for instance, or for example, 3D models. We always try to maximize the visibility of the papers published to our journals. For Advanced Intelligent Systems in particular, we have an editor's choice virtual issue showcasing the best papers published in the journal. And of course, all of these papers, they're getting highlighted on Wiley's social media channels. And then for each issue, we create some sort of video and highlight the best papers published in that issue. And as I mentioned earlier, also about smart supporting information, all of those papers with interactive content, they are getting highlighted on Wiley Online Library and also on Autoria website as a collection of papers. So I'm already close to finishing my talk. Before concluding my talk, I would like to draw your attention to another Wiley robotics related journal, which is Journal of Field Robotics. The journal has been out there for almost, I don't know, I guess a few decades, and it's quite well known in the community. So if you are interested in this journal, please refer to the journal page. And again, thank you very much to the organizers. Thank you very much for your attention. And if you have any question, please just email me or via Twitter, send me a message. Thank you so much.
Excellent. Excellent. Thank you, Kevin Wiley, for sponsoring the prizes for our submitted talks and papers, which we are having later, after our next invited talk by Piotr Dudek. So Piotr, if I'm pronouncing that correctly, which I never am, is a professor of the School of Electric and Electronic Engineering at Manchester University. He's one of the minds behind Scamp 5 processor, focal sense processor that a lot of us have been seeing and using. So yeah, without further ado, if you're ready to present, please go ahead.
Yes, thank you very much. Thank you for inviting me to give this talk, and thank you to organizers for organizing this workshop. Very nice. Okay, yes. So title: On Sensor Computer Vision with Pixel Power Processor Arrays. I'll just kind of give a brief perspective and motivation on kind of my view on the principles of where, why we're trying to do in pixel computation, and then tell you a little bit about the chips that we designed in Manchester with a bit of an overview of Scamp 5. I'll show you something about a new chip, Scamp 7, and show a few applications and demos. There are other demos in this workshops. They are using Scamp 5 device, so I'll focus mostly on that. But just generally, and we kind of all notice that vision is hard, and the algorithms are demanding computationally, and so it's not just due to large amount of pixels, but one of the reasons certainly is the amount of data that we have to process. And since this is a robotics conference, robotic applications are extremely challenging, right? We often have to process things in real time with high throughput and low latency, especially if the robots are moving fast or have to react fast. If these are embedded systems that we want small footprints and low power consumption as well. So it's as hardware designers, we're really motivated by these robotic applications because they do present some of the most challenging application scenarios. So it's a demanding performance, but severely constrained size and power. And so you really cannot, send all the data to the cloud, which is a lot of computer vision, works like that. You cannot use even large or power-hungry CPUs or GPUs. You cannot even process data in batches. That often helps you to process fast. But you do have to maintain throughput and low latency. So huge challenges. And the conventional pipelines are really not efficient at doing vision. Energy is wasted right from the very start. On an image sensor, you'll perform A to D conversion. You run an image sensor pipeline, which does your demosaicing and gamma correction and sophisticated noise removal, and really with the purpose of producing lots of pretty pictures that you will send somewhere else. So that's already perhaps not necessary for vision. But then, of course, you have some sort of hardware that you try to throw at the problem to compute, to get this data processed. And the key observation that I think has to be made, and is well appreciated by hardware designers, but maybe not for everybody, is that it's really not the kind of compute circuitry that takes power, it's moving data that takes power. So the power and speed is really limited because you have to move the data. Well, between the sensor and the processor, and then between maybe your processor and your co-processor, and within the system between the processor and the memory, or within your specialist hardware between your memory cells and your processing cells as well. So really, it's the movement of data that is limited. So what we're trying to do is to minimize that movement of data. And so that's what really costs time and energy. And the idea is, okay, well, we get rid of the conventional camera that sends pictures out and replace it with something smarter. We'll call it a vision sensor. And we'll try to squeeze all that processing into the sensor itself, which, of course, is very easy to do on a PowerPoint slide, a little bit harder when you actually have to build it. But that's our idea. So we'll put that hardware, processing hardware, into the sensor and output meaningful data, and so we can then get away with something much simpler, a microcontroller. And that's really, I mean, this is the picture for that we all can understand in this workshop. But I think the movement of data, that is really kind of important thing. So bringing processing to data is why this works. And of course, I mean, what you do is basically integrate that processing circuitry onto the sensor device itself, and you can put it right next to the sensor, and that's a good solution. And of course, most of the kind of data movements are very local then, and we've seen already some solutions that doing this. Our approach is that we're trying to take it to an extreme and put the processing within the pixel array. So the idea is really we very closely integrating sensing and processing so that we don't have to pass data between the sensor and the processor. And also processors integrate memory. So everything is kind of very, very close together. Now, I want to give you this, which the scale here is transistors. It's a bit of a timeline, but it's not really a history lesson, but it's a kind of, it's what you can do with in-pixel circuitry. So, you know, when the image sensor started, there was a zero transistor circuit because CCD devices essentially just had electrodes that were biasing the substrate that was gathering electrons, and then these were sort of bucket brigade pushed out of the chip. Now, with the advent of the CMOS-based image sensors, people could do a more sophisticated readout circuitry with about 3 transistors, and most of the image sensors that you get are 3 transistor sensors called active pixel sensors. We are seeing now the opportunity of integrating more and more transistors into that pixel space, partly because we have the availability of stacking technologies, and partly because the transistors are getting smaller and smaller. And so this is an example of a digital pixel sensor from Facebook Labs. Sony have sensors like this as well, where the entire A to D conversion, which is one of the initial steps in the sensing pipeline, is integrated into the pixels, and that costs you maybe about 80 transistors per pixel, and you can put them right next to pixels. What we're trying to do is to put entire microprocessor into a pixel. Okay, we can call it computational pixel sensor or pixel processor array. At about maybe 200 transistors, we can already build very simple but effective microprocessors, and that's really that is our approach. And just a disclaimer: I'm not claiming that we are the first people who are doing this. I mean, with so much pleasure have seen the Professor Ishikawa's presentation. It's a seminal work that, similarly to Andy's, inspired me a lot when I started working in this area. And so it was very influential, and it continues to impress. So that's the kind of there are people in academia who are trying to integrate the processors into pixels. There's a lot of other ideas that increased number of transistors in the pixel allows you to do useful things with time of flight sensors or single photon detectors, the photon counting sensors, with the dynamic vision sensors that we have seen in the previous presentation, and so on. So integrating more of the transistors into the pixel circuitry enables you to do more interesting things. And we are trying to do this in a very flexible way by putting a microprocessor into a pixel. So this is the general view, right? We will have this image sensor that responds not by sending out images, but sending out some information that it has extracted from the images themselves. And our approach is of integrating full processor into the pixel array. It's a challenge to do this. It's an interesting challenge, and you can see where the technology is going. We are capable of integrating more and more processing next to the pixels, and so we should exploit that opportunity. If you do this, then you can just write programs, right? So rather than having this sensor that does one particular thing, you can build a sensor that can do anything. That you can simply write one program to do some feature extractor, another program to do segmentation, another program to do key point extraction, and so on and so on. Challenge is how you're going to build your processor so that it fits into a pixel, and that's very much what we have been working on in Manchester, and that has gone on for a while. And we've explored various ways of doing this. We've built a lot of work on the concept of analog processor that I will outline in a bit more detail here. And this latest devices, Scamp 5 and the latest Scamp 7 are really largely based on this idea of analog computation. But we've also looked at bit serial digital computation, similar to the work in Tokyo. We've looked at integration, kind of from a technology point of view, how you can split this processing amongst not even one, but several silicon layers. So there's a whole family of pixel processor arrays that you can think about. But today I will tell you more about what I think is our best, the Scamp 5 sensor. This device is used in the community, and there are some demos in this workshop. Here we integrated 65,000 processors on a 256 pixel array. They are really slow if you think about a single processor, right? It's a 10 megahertz clock, but because there are so many of them, we are getting a pretty decent peak performance of sort of more than half a tera, again at a power consumption of about a watt peak. The more important number is this ratio of how much performance you can get per watt. And without going into details what a gigaop means, because that's also rather contentious, these are pretty good numbers, especially if you consider that we are actually using a technology that was commercially available 20 years ago. I mean, you understand how processors get faster and faster as the transistors on silicon chips shrink. We're actually using a very, very old technology and achieve performance which is state of the art. Okay, now I usually skip this bit about analog processor, but I thought it's actually quite interesting, and why not tell you a little bit more about it? So if you look at this processor here, the analog is actually a large part of the system, but the way we design analog processors is quite special. We actually design an architecture of a digital microprocessor. So you can think about this analog computing as essentially being a way of implementing a data path. So the processor here, so if you kind of think about the schematic diagram, it has the registers, it has a data bus, it has some kind of instruction set and execute software programs. It's like any microarchitecture of a processor. What is unique is that the data path is analog. So the analog arithmetics are actually done by computing on analog values, in this case on currents. The registers are analog memories, and this we think gives quite high efficiency and a small circuit area. So that allows us to build a complete microprocessor with less than 200 transistors. Another nice feature of this is that you can seamlessly integrate the sensing with the processing. We don't need to convert data from analog to digital to process it, because the analog representation is the native representation for this processor. And I'll show you this, which is actually how the processor works. I'm not going to talk about the details of the transistors, but it consists of registers, which are memory cells. And really, like in any other microprocessor, what you do is you just run through the micro instructions, and each micro instruction sets up a path for data to be loaded from somewhere and stored somewhere else, and perhaps processed in between. So we can execute an instruction of moving a piece of data from a pixel to the register. We can execute an instruction of moving that data again from one register to another register. Or we can take data stored in two registers and put it somewhere else and add those two numbers together. So from the point of view of the architecture, this is really a processor microarchitecture. From a point of view of the data path implementation, data representation is not bit serial, it's not 8-bit, it's not 16-bit, it's an analog data path. Okay, so that computation is done in analog. But it just runs a program by setting up all these different paths for loading and storing the data in between. It's not the only way of designing pixel processor arrays. Yeah, we find this interesting, but most importantly, we find it effective. So resulting in a compact and low power implementation of this data path. And the program flow control is actually under a conventional sequencer, or in our case, we actually use an ARM Cortex M0 processor to to run the sequence of instructions that will run on the processor. So if you look at the code, it looks quite familiar. It's basically C. We can compile the C into the instructions for the sequencer, and the analog operations, if you like, are encapsulated in processing kernels that you write essentially in assembler. And it means that the programmer does need to be, to some extent, aware that the computation is done in analog. Some of the peculiarities of this is that the computations are imprecise or noisy, but we do try to hide most of that complexity from the programmer, providing the libraries and tools that make the programming of the system very similar to that of programming a digital computer. So essentially, just write program in C, write the programming kernels in assembler, compile the code. You have to understand, there is some kind of microarchitecture of that processor that executes the kernels, but to a large extent, you can forget this computation is done in analog. Although, when you were looking at your computation results, you realize that there is a noise creeping out, and you may need to take that into account. We have spent quite considerable effort developing programming tools that allow the users to simulate the code and provide a debugging environment for developing applications, so we can actually simulate the whole system on a PC in a kind of emulated way and then run it on hardware. And that actually takes a lot of effort, and it's quite difficult to do in academic environments. So we've been quite lucky to have funding to do this sort of work. Okay, but that's in a way it's really essential that when you come up with this new and strange hardware architecture, that you do provide tools. Otherwise, no one can use your system, and you can write a couple papers about it, but that's just about it. Okay, Scamp 7 is our new chip. So I want to show you some examples, but just brief introduction to this new chip. It's quite similar actually, and almost backward compatible with Scamp 5. So there is not a great kind of technological leap here. We integrated some of the peripheral electronics that we had previously on a PCB onto the chip, just so that we can make a slightly smaller system. So actually, some of the biasing circuitry and all the periphery is now integrated somewhere there on the chip. We increased digital memory to 22 bits. So I talked to you about how analog compute is being used in the Scamp system. It's actually a mixed mode processor. It has two parallel data paths. It has this analog data path for manipulating, if you like, a continuous valued information. It also has a binary data path for manipulating binary data. And a lot of people like using binary registers, partly because it's a little harder to compute with analog, and you have to think about the noise effects, and so we find it quite useful to increase the amount of digital memory there. We improve things like digital conditional write that allows us to do things like say in pixel A to D conversion faster. We increase readout speeds. So there are some kind of incremental improvements over what Scamp 5 was. And these systems are, we've tested them in the lab, and we are planning to make them available to our collaborators and the community in general, as we did with Scamp 5. I'll show you this one thing on analog compute again, because people often question this. I run here a median filter on Scamp and just computing median filter from the input image in MATLAB, just so that kind of visually you can see what's the impact of this analog computation. If you look closely, you will see there's a little bit of noise creeping up here. So there is a level of imprecision or noise that is being introduced by analog compute. But if you think about what are we trying to achieve here, getting rid of this point noise, I mean both algorithms achieve that. So it's really a matter of adapting your expectations in terms of what is the goal here of the computation. Is it to have a perfect representation of what digital computation will achieve, or is it achieving a certain vision processing task? And if you think in that way, then you will find that this analog compute gives you an opportunity to do things fast and accurately enough many applications. Here I'm showing an optic flow implemented on the chip, and it's simple block matching algorithm where we just see how a block of 5 moves from a frame to a frame. There is a color map so the color codes for the direction and velocity of motion. We can run this on chip at about 0.4 milliseconds latency, so it's about 2,000 frames per second if you wanted to run it in this way. But often that would be just a first step in some longer algorithm. Here I'm showing a corner detector. We're running a fast corner detector, so a simple corner detector algorithm. In this first, this first video shows how the corners are extracted and tracked with a gray level image background. What typically you would do is not to output the gray level images, but only output the corners, right? So you're interested in how your features move from a frame to a frame. You're not really interested anymore in gray level image behind it. And if you do this, then you can run this at something like 2,000 frames per second. So we can retain maybe a few hundred coordinates of corners at 2,000 frames per second. So you can do, and then you can follow that up with whatever you want to compute with those features. So there is some kind of address event interface which allows you to output not only like images, but actually coordinates of the points of interest. Somewhat similar to what DVS type of sensors are doing, the event cameras that output the coordinates of pixels that change intensity. But here we can, in a way, program what kind of event we will be sensitive to. So here the event is an existence of a corner point. With capability of doing things very fast, we can do interesting things in computing during integrating light. So typically, if you want to do a high dynamic rate sensing, you will acquire images at different integration times, and then some kind of algorithm that stacks them together and figures out what is the optimal exposure in different points. We implemented a tone mapping algorithm that works during integration. Essentially, as we are acquiring light, we're looking at the images and deciding whether the pixel, what gray level of a pixel should be depending on its neighborhood. This work has been done by one of the co-organizers, Julien Martel, and it's a very nice algorithm that allows you to capture images with high dynamic range. Another thing also done by Julien was depth from focus, where we were processing thousands of frames per second while sweeping the focus of a lens. So we had a liquid lens that was sweeping the focus at something like 60 hertz, going from near to far focus. And at that time, we were computing local sharpness in the image. And from that measure of local sharpness, when it peaks, the time at which it peaks can tell you about the depth of the image at that particular point. So you can get a really nice depth maps, which you can output at 60 frames per second, but you have to process at 7,000 frames per second to get 128 levels of depth. This is the kind of implementation that you would never do with a conventional image sensor, because you would not be able to output, or you don't want to output 7,000 frames per second from a sensor. But if you compute right on the sensor, you can start doing those things. I'll show you this one more thing, which is a target tracking. This runs at 100,000 frames per second. And what we say, we're looking at the spinning disk, and we're picking out a point at the spinning disk here, which is an O, as opposed to all the C's. And then we output the coordinates of that point. So we cannot actually output frames at 100,000 frames per second, but we can output the computation result, the coordinate of the point of interest at 100,000 frames per second. And this is the kind of time space that shows you like this. So this is the image space, and this is the time. And we show how on this rotating disk, the location of our point of interest of our O moves. We can output one frame just to make sure. So we output one frame out of all this kind of capture to show that our tracking really goes through the O. But we cannot output so many frames. So we can only occasionally output a gray level frame. Here is actually a video of this, of a slightly different scenario, where we are tracking all the points now. So the O is the red track, and the C's are the blue tracks. And we're returning one frame. All the other frames are processed, but only coordinates of the points of interest are returned. So that was a really nice demo and showing potentially what you can do at extremely fast processing speeds if you can process on sensor. I have here the CNN demo. It's quite a complex algorithm, so we can implement quite complex things on the sensor. There is a demo. Laurie Bose has a demo in the poster session on this. So I'll skip this here. I'll show you some of the other things. Was again done at the University of Bristol by Laurie Bose. Where what we are doing is essentially from the motion of the image on the image plane, we are determining how the camera is moving. So it's a kind of inward, kind of in-out looking odometry. The two tracks here is the one that is coming from a Vicon system that tracks the camera. So that's a ground truth, and the red and the darker one is the one determined by our system. So again, here one of these tracks is the ground truth, and the other one is determined by the system. The application context here, it shows how we compute a whole number of features on sensor. And rather than outputting the feature maps, we just summarize those features, calculating some summary information on a feature in a larger receptive field, so that we compress all this different information from feature extractors into a vector of 40 numbers. And this is the 40 numbers that we are sending out to the processor. And then we train a neural network to do. So here we trained it to essentially replicate the behavior of a behavior of a proximity sensor. Oh, my video is not working. So that the car is driving around and is avoiding obstacles. It was just the neural network that looks at those features was trained with just ultrasonic proximity sensors. So it's a kind of trying to mimic behavior of that using purely vision. Finally, here there are some videos that show our drone racing attempt. This is probably the most ambitious things we did with robots. So we put a sensor, the Scamp system here on a flying drone, and the drone is flying through the gates. You can see what it sees. These are actually simulation results, but the idea is that from whatever the sensor sees, we will only extract the location and the position of the gates and use that info. So again, there's only a few bytes extracted per image frame, and only those have to be sent to the processor, and then we use that to control the drone. There is a few other demos in this workshop, so please have a look at other things that are being done with this sensor. This is just the summary of the talk. I will just quickly go to acknowledgements. There is a team in Manchester. A few key names are here. There were a few people over the years, students that worked on this, and our collaborators here that worked on the videos that I presented in this work. And that's all I have to say. Thank you very much.
Excellent. Thank you. Thank you for all of that. There's lots of really good information. We probably have time for a couple questions. So if anyone wants to put it in the chat, please go ahead. I'll start off by asking, what do you think? So you said that you're using a sort of 20-year-old technology for your process node. Do you think that moving to newer, smaller technologies is actually going to make the analog computation more noisy? And so sort of the latest, smallest technology actually would hurt in terms of accuracy and usability of the analog side of the device?
I mean, that's a valid point. The analog design gets harder as the transistors shrink, much harder than digital design shrinks in a pretty straightforward way. Analog is harder, but we definitely benefit from shrinking, from 180 nanometers to whatever 28 nanometers. people are designing comfortably analog circuits in 28 nanometers. So there's still a way to go in terms of scaling. But yes, the challenges are there. It's not as straightforward as scaling a digital 180 nanometer circuit into digital, 28 and also there is a limit. I think it's hard to imagine the same principles that we used for designing this processor with the switched current cells working in 5 nanometers. So there is certainly a limit to this approach.
Cool, interesting. Yeah, so in that, how do you see sort of the going forwards the process of designing next generation Scamp devices in terms of you can always make things more fixed function or add more sort of special operations to do particular things, or you can make it more general purpose, almost to the point of like almost a CPU or something. Obviously, you wouldn't go that far, but how do you go about deciding those things and working on where the compromises are to be made between what algorithms have to put up with in terms of weird or quirky novel instruction sets and yeah, what computation is possible?
Yeah, so I mean, so there are 2 points here. One is special purpose circuits, right? So obviously, if you know exactly what kind of functionality you want to achieve, then you may want to use a dedicated circuit that solves your problem. And sometimes it can be a good solution. So in some cases, like with say a DVS sensor, you are interested in capturing a lock intensity change beyond a certain threshold. If you know that's your function, you can try to implement optimized circuit for it. If you want to try to do more complex things, then actually this approach breaks down. For doing more complex things, you would need to build more complex and more complex circuits. And really that is not efficient. It's a lot more efficient to build a small circuit that is universal, that in a way reuses the hardware because it multiplexes the operations in time. So, I mean, a microprocessor is a really nice machine that can solve any problem because it has a very limited set of hardware operands that can be reused and reused and reused again according to the sequence of instructions you give it. And so you don't have to build bigger and bigger system to solve more and more complex problems. You only need to give it a bit more time. So actually that approach of fully programmable in-pixel circuitry is very efficient. It's not just that, it's not a compromise, it's actually the way to build very efficient circuits. Now where things are going, I mean, there is a little implication now already with our move from Scamp 5 and Scamp 7 and adding a little bit more digital memory. As we are trying to exploit finer and finer technologies, that boundary between what is done in analog and what is done in digital will be shifting. And we will be doing more things in digital. We will still, I'm pretty sure we still want to do quite a lot in analog because there is at this very, very early stage of processing, it's really very efficient to compute without having to digitize the information, without running an A to D converter first. So at that very early stage, there is a place for analog computation. And then as things get more complicated, you can do things more digital. And I guess a hierarchical designs where you start with this pixel level computation that is good for many things. And maybe, as I think Andrew Davison indicates, is good for more things that a lot of people imagine it's good for, the pixel level compute. But there is also a place for parallel compute that is more flexible in the architecture and that allows you to more flexibly communicate between the processors. So I guess for kind of practical systems, there will be a whole kind of on-sensor processing pipeline that will take you from analog compute at the sensory front end to digital compute near pixels to a digital compute somewhere which is still near a sensor array, but perhaps in a different topology or giving you more flexibility.
So
and it's I think it's a big research question on how that pipeline actually should be constructed.
We're running low on time. One more question, and if you can answer it in 2 or 3 words, what would you think is the most compelling demo or coolest next thing to show off with these capabilities?
I don't know.
Excellent. Well, thank you very much for your really interesting talk. Thank you for coming. We are now going to move on to the submitted papers. So if paper 1 is classification of motion directions with spiking neurons and continuous learning case by V. Ogel and J. Marinette. Are either of you here now to present?
Yeah, it's me.
Perfect. Piotr, if you could stop screen sharing and then we can switch over. Piotr?
The screen sharing is not functional for me.
I think it's because Piotr needs to stop. How do we stop him? Stop share.
Sajad, I think the Zoom is yours. Can you take control?
Oh, okay, right. I think yes, you should be able to share now.
Hi.
Excellent. Sorry for probably butchering your name. Yeah, so you have I think these are 15-minute sections, so there'll be about half and half presentation and questions if possible. Yeah, please take away.
Hello everyone, I'm Veysou Jalil, a third-year PhD student at the University of Lille. I will present my work on the classification of motion direction with a spiking neuron and continual learning. Embedded computer vision imposes a strong constraint in terms of adaptability to the environment and energy consumption. Spiking neural network can be a response for this constraint. Learning is unsupervised, fast, and continuous with local rules. It's possible to implement this model on low-power hardware implementation. The spike neural network is based on the biological model. The neuron emits a spike, and the learning rule is based on time correlation when a spike is emitted. They follow a principle observed in neuroscience and called spike timing-dependent plasticity (STDP). Continuous learning is the ability for the model to learn new classes incrementally without forgetting the old classes learned. The STDP is local learning method, thus the update of the weight can be targeted to a part of the network without changing the rest, that is compatible with the continuous learning context. On the other hand, this model is still complex to use, difficult in multi-layer encoding of data in Spike, for example. One way to overcome the data encoding problem is to use data acquired by event-based camera. It's a bio-inspired sensor that perceive the temporal contrast of the scene. In other words, they are sensitive to movement. Each pixel can detect a light variation, positive or negative, asynchronously, which trigger an event. This event can be easily associated a spike. Your objective is to identify a minimal network structure able to recognize to motion direction after unsupervised and continuous training. Overall, the goal is to develop a complete neural-inspired vision system. The lower figure corresponds to a complete overview of the experiment. To do this, we created a dataset and move in the 4 cardinal directions. We transform it into event data via your simulator. Once done, we train your SNN model in an unsupervised way via the STDP by introducing the classes progressively and by saving the state of the network at each new training. That we encoded the spike output of the SNN by test different encoding scheme. Finally, we use a multi-layer perceptron to classify and analyze the results. Regarding the network architecture, it's a feed-forward topology. There are no secret connections. The neuron model is the leaky integrate and fire model. It's a neuron model widely used in the SNN community. It's halfway between biological realism and computational performance. There is a lateral inhibition mechanism on the output layer. It's allowed to have a competition between neurons. When a neuron that spike will mute the other neuron for a certain time, that can be set each synapse to a delay with a random value, and the resolution of window is 12 by 12. Concerning the experimental protocol, the network weights are randomly initialized. Sequential training stages are performed with each class individually. During training stage, a sequence of 20 samples are presented to the network. After the training stage, synaptic weights are frozen and the test set containing all 4 classes is presented to the network with the output spike activity is recording. 5 recordings are collecting corresponding random initial states of the random initial state before train called BT, and the state after each training stage. After training 1 class called IT1, 2 class 82, and 84 is for 4 classes. Because of the random initialization, this protocol is repeated 10 times with a different seed value. Total spike sequence for analysis and classification is 80,000 sequence spike. And for the result before training versus after training, we show the distribution of the output spike change. And to go a step further, we plot a 2D projection of output data using T-distribution stochastic neighbor embedding, TSNE. It's a statistical method for visualizing high dimension data by giving each data point of a location in a 2 or 3 dimensional map. The result presented show that the output classes are better separatable after training than before training. Finally, the result of the MLP classification are much better after learning. Before training, the result is 0.65, and after training, it's 0.91. And for the continuous learning context, as remember, on the x-axis for the free plot, we have different states of the network. Each one corresponds to a step during the training of the SNN. Each step corresponds to the learning of a new class with keeping the state of the previous learning. The plot on the left shows the if1 score of each class, as well as the overall accuracy of a neural network classifier in a 2-class problem, 1 versus rest, where the 3 other classes are grouped into 1. The middle plot shows the result of a problem with 3 classes, 2 versus rest. Finally, the plot on the right shows the result on the complete classification task with 4 classes. This allows a fine analysis on the quality of the feature extracted by the SNN and their impact on the MLP classification. The main observation is that the introduction of a new class does not deteriorate the result of the class already learned. Moreover, when the network learns a new class, the result on this one increases. And finally, in this work, we have designed elementary network structure to detect motion direction that continuous and unsupervised learning. The results show the continuous learning capability of the model, and in the future work, we will remove the MLP part and replace with SNN-based supervised classification. And for the simulator, use a more realistic simulator. Example, video to event, and use a real-world data like dataset like DDD 70 and VSEC and etc. And use this minimal structure on more complex network. Thanks.
Thank you. That's some interesting stuff about yeah, how you actually do the self-learning classification. I was just wondering so you're using a simulator at the moment to run your spiking neural network. So I'm wondering what's stopping you actually using an event camera, and is there anything about sort of the setup or the hardware that needs to change to sort of make this more applicable to event cameras and running it sort of direct online?
Sorry, for the simulator, what
what's stopping you using an event camera and making you use a simulator instead? What could be change, or what would need to be implemented in hardware for you to port this to actually run on an event camera and hardware?
For the simulator, I use my simulator for control the data. Sorry for my English is complicated for me for expression, but the simulator I've used is it's on-craft simulator for little data set for my hand moved in 4 cardinal direction, and it's simply transformation simply for transformation for create the spike,
yeah.
but these methods allow you to create the minimal data for analyze the model
So why do you, in your future works, you want to move to a different simulator, or more precise, accurate simulator? What's not precise enough about the current one?
For the other simulator or the real data is more complex for this data. The number of spikes is many of my simulator. It's complex to analyze with this minimal structure, but
Okay.
But if we scale up the network, it's possible to address more complex data.
Yeah. Okay, cool. So yeah, bigger problems, bigger simulator. Excellent. Well, thank you so much for your talk.
Thanks.
I suggest everyone after this next talk, it will be the lunch break. So everyone should have their appropriate meals, whatever time of the day it is. And yeah, make sure you get on GatherTown to talk to all the people giving talks who are available. So if you would like to, yes, that's it. Right. So our next talk is a submitted paper from Yanan Lau.
Yeah.
Perfect. So yeah, thank you for submitting and coming along.
Okay.
You can share your screen.
Yeah. Can you see my screen?
Yeah, it's popped up. Excellent.
Okay.
Excellent. So yeah, thank you for submitting. I hope it'll be interesting. I really want to see this.
Okay. Shall I start?
Yes, please do.
Okay. Hi. Yeah. Hi, everyone. I'm Yanan Liu from the University of Bristol, a PhD student supervised by Professor Wataru. I'm going to talk about my accepted ICRA workshop papers. You may have already know the design principle of the pixel processor array introduced by Professor Dudek. The CNN inference in this work is wholly performed on the pixel processor array, and the servers can be controlled through the GPIO from the ARM M0 controller, and a maximum of 5 servers is supported to set up a more comprehensive sensory motor system. Yeah, as you can see, a servo motor is directly driven by the Scamp vision system without any additional intermediate hardware. With the machine vision computing results from the Scamp vision system, the servo can be instructed accordingly. We use our previously proposed binary convolutional neural network for this work. We train a binary neural network offline and implement image convolution, ReLU activation function, max pooling, and fully connected layer for this CNN inference. As you can see, each image here is either in an analog register or digital register, and all the binary weights for the convolution and fully connected layer are stored in digital register. With this architecture, the whole CNN can be performed using very simple and efficient operations, including addition, subtraction, bit operation, and shifting, enabling high-speed CNN inference. This is a demo for 3 hand gesture recognition and for English letter English letter classification using the servo motor as the indicator. For hand gesture recognition application, a stride 2 with a single convolutional layer and a fully connected layer is utilized to achieve a trade-off between the efficiency and the robustness. Our network can operate with a latency of 121 microseconds from image acquisition to classification result available in the microcontroller. Yeah, there's more. Yeah, this is the letter, 4-letter recognition example. And we also propose the semi-simulated platform by integrating the Scamp with the Compilation sim robot simulator. This platform takes advantage of the Scamp's parallel computation ability and the rich simulation scenes in the simulator, where applications can be exploited and validated virtually. Basically, the simulated sensor readings from the simulator can be transferred to the Scamp Python host through the remote API, and followed by another transmission through the USB to a real Scamp. After image processing in the real Scamp, the useful information can be sent back in the same way to the simulator, where those useful information can control the movement of a robot or simulated robot or something. The image at the bottom is the CNN architecture for localization and tracking application based on the Scamp. A shared convolutional layer is used for object 2D localization on the Scamp, where networks for labels indicating X and Y are using identical convolutional layer, but a different fully connected layer. The image on the left is the example robot simulation environment. The right image shows tracking trajectories with a drone. There are 3 passes. The first one is the preset rule trajectory as the ground truth, and then the drone tracking trajectory with the convolutional neural network on PyTorch guidance. Because on the PyTorch, we run convolutional neural network on PyTorch because there's no errors. And then the third one is the drone tracking trajectory with the guidance from the Scamp CNN inference for just for a comparison between the ground truth simulation in PyTorch and the real implementation on Scamp. Okay, I think that's all my presentation. And do you have any more questions?
Excellent. Thank you for presenting that. I'll kick it off with a question about the direct servo motors. I just wondered how do you go about actually running them from the device? Is the device already sort of a real-time system that allows you to do PWM, or is there a way we can sort of, do you reckon there's a way we can almost cut the middleman out and have more direct connection between the sensor processor and servos?
Actually, there's a library developed by University of Manchester in the M0 controller. Basically, we can use the results from CNN inference and use the library for PWM to control the motion of the servo motor.
Excellent.
And actually, if we can extend more servo motors, and in that case, we may need other power supply for more servos control because of the power. And in the Scamp, currently, we just use the GPIO as the power supply for servo.
Cool. Okay. So I guess you need to have it part of a bigger system if you wanted to be able to do more, right? It can't deliver enough power by itself. We have a question. How are the networks trained? Do they take into account the noise caused by the analog computation? Is there, what do you do anything, or what do you do to account for that in training?
Actually, we just train the network using binary connect. Actually, it's a little bit independent from implementation from the analog or digital stuff in the Scamp. We just train it separately and then implement our neural network on Scamp. And one thing we need to mention is that we introduce some noise as the data augmentation simulating some noise from the Scamp. Because when calculating with the analog registers, there's lots of calculation noise introduced. So we use those kind of stuff as data augmentation when we training our binary neural network.
Cool. And one more. How do you go from the original image to your image preprocessing step? So I mean,
Oh, you mean
you've clearly got a lot of data movement there across the sensor.
Yeah.
That become an efficient process to do.
Actually, we do it basically in parallel too. And for this step, basically we just resize this image into 64 by 64 and replicate it to fulfill all the processor. Yeah, this is I think this step costs a lot of time compared to other step. Yeah, especially if you want to implement something with 64 kernel filters. Currently we are using 16 kernel filter. But if we use 64, maybe we need to do more replication operation.
And is this so I mean, do you think you could say half the number and go for 8, for example, if you so it looks on your convolution step, you've got your weights there in the digital registers. If you had more digital registers, would you be able to store 2 sets of weights for every patch? And therefore you might have to do less pre-processing or more efficient pre-processing.
Sorry, you mean if we need more kernel filters or something?
So you'd be able to have the same number of kernel filters. But larger patches because you have more than one kernel filter per patch. Is that something that seems possible?
Actually, if we need more kernel filters, and basically, I think we have 2 plans for that operation with more kernel filters. One is to using a smaller images like 64. Currently the image size is 64 by 64. If we are using more kernel filters, we have to using a smaller image like 32 by 32. In that case, we can deploy 64 kernel filters. This is one solution. So another solution is to do convolution, combine sequential implementation and parallel implementation. For example, if we need 32 kernel filters, we can use this single image, but with 2 digital registers storing those kernel filters and perform convolution twice. In that case, we can get 32 filter maps.
Excellent. Thank you so much for the talk. It's really interesting to see where and what we can use Scamp for, and where the whole world of interacting with focal plane sensor processors all the way to physical actuators is going.
Okay. Thanks. Actually, we are developing the next generation CNNs, and I think we can make it public in the near future.
Awesome. Well, I think that brings us to the end of the second session of UNVSIP 2021. So now we have an hour-long break for lunch or whatever meal is appropriate, and we'll be in GatherTown for demos and posters. So please do jump onto GatherTown and have a chat with everyone that's here. And look at some incredible videos that these guys and lots of others have put together. We'll put the link in YouTube, so for the GatherTown, so you can join up. And if Sajad, if you're there, can you put up your slide again? If
yes,
Jan,
I will do that.
So you stop screen sharing, Jan?
Okay.
Excellent. So we'll see you all hopefully at 1:40 UK time, where we'll have a session 3 chaired by Riku Murray. Thank you.
Thank you, Jonan, and see you soon.
Hi guys, can you hear me?
Yeah, I can.
Hi,
Hi,
Davide.
Andrew.
Hi.
Are we streaming now? Or?
Yes, I think
Oh,
it's
okay,
being
yeah.
streamed.
Hi guys, can you hear me?
Hi, Davide.
Andrew.
How are you, Sajad?
Good, Andy. Good. How are you?
Yeah, fine, thank you. Yeah.
Good. It's nice to see you after almost.
Oh, I know. Yeah. Yeah.
Great.
Yeah, this is a very, very nice workshop.
Yeah, thanks for coming to the workshop. That's I really enjoyed your talk.
Oh no, of course, it's great.
Good. So I think we're starting in 2 minutes, right, Riku?
Yep.
Everything's on track. I think Davide is quite busy with his own workshop as well. So it's thanks for
Yes, I have
time.
to.
Oh yeah,
we are starting in 1 hour, indeed.
Oh, okay.
It looks pretty interesting, that one. I might try and stop in for some of the talks. And I'm speaking in another one later this afternoon as well, another different one.
Right. Yeah, quite busy. So are you going back to school in person anytime soon?
Oh, we don't have an imminent plan.
Okay.
You know, fingers crossed, but it's still a little unclear at the moment for us.
Right. I think it's the same for everyone. It's the same for us as well. So, Davide, have you tried sharing your screen? Does it work?
I didn't try. Yeah, I'm gonna do it in a moment. Yes.
Sure. Okay, so yeah, hello everyone. We'll start the third session. We have one invited talk and 2 papers. Riku will chair this session. Riku, all is yours.
Thank you. Well, I am delighted to have Professor Davide Scamp with us today, and thank you very much for joining us. I'm quite certain that he does not need too much introduction in this community, but he's a professor of robotics and perception at University of Zurich, and his research is at the intersection of robotics, computer vision, and machine learning, using both standard cameras and event cameras. And today, he'll be giving us a tutorial on event-based cameras and their applications. So if Davide, if you can share the screen.
Yes. Can you enable me to optimize for video clip? It tells me that it doesn't let me.
Optimize for video clip.
Meanwhile, I start sharing. But if you can allow that, that would be great. Okay, can you see my screen? Meanwhile, I start. And then if you can
see
find a
your
way.
screen, but I'm not sure if there's such an option to optimize. I don't see any option here.
Okay, that never mind then. Okay, so good morning, good afternoon, and good evening, everyone. So I want to give you a research update about the work that we are doing in my lab about event cameras. This presentation is a follow-up of a tutorial on event cameras that I gave as CVPR last year. So I will not focus on past research, but rather give you an update of what we have been doing in the last 12 months. So I want to start talking about autonomous driving. So at the moment, there are tons of data sets to train perception algorithms for detection tasks, SLAM, semantic understanding tasks, and so on. However, they've been recorded with standard cameras, usually rolling shutter or global shutter cameras that have a very low dynamic range. These are just a few sample images from the famous Waymo dataset, where you can see that in low exposure, you have a very dark environments. Here is another Waymo subset taken, for example, during the day or during the night. And you can see in the bottom row that when it's raining or when it's very low light, then standard cameras suffer from problems in detecting traffic lights, other cars, and so on. Again, another sample from Waymo, this one taken during daylight, and you can see that many pixels get washed out when the sun is in the field of view of the camera. And myself actually took a test drive at Waymo 2 years ago. It was at 7 p.m. during sunrise, and actually the car was stopped 3 times because of high dynamic range problems. Here is another data set from Newtonomy. It's called the New Scenes, that was released also 2 years ago. And these are some of the sample images that suffer from the same problems as Waymo. So very low dynamic range in low light and during daylight conditions. So this is to tell you that current data sets have problems with standard cameras. So motivated by this, we decided to collect a new data set for automotive scenarios. And we call this dataset DSEC. It's a stereo event camera dataset for driving scenarios. And here I want to show you some sample pictures. So we have a stereo event camera from Prophecy and a stereo standard camera from FLIR. We also have a LiDAR sensor from Velodyne. So the main feature of this dataset is that we use a high resolution event cameras. Now, for those who never heard of event cameras before, an event camera is a sensor that measures only motion in the scene. You see what I mean in the top right video. So there are smart pixels. Every time that a single pixel detects a change of intensity caused by motion, that pixel will trigger an event. The events can be either positive or negative, depending on whether the motion is moving in one direction or in the opposite direction. What you need to understand is that event cameras stream the information asynchronously. So basically, this is different from standard cameras instead, where every pixel outputs information all at the same time. The key advantages of event cameras is that they have a very low latency with resolution of microseconds, no motion blur, a very high dynamic range, and very low power consumption. The point is, the problem with these event cameras, though, is that because they are asynchronous, traditional vision algorithms cannot be used. So you need to adapt existing algorithms or you develop new ones. Who is selling event cameras? So there are at the moment 3 companies, and that all these companies are actually working with the big tech companies. So Prophecy has partnered with Sony, and they produce the 80 sensor. It's actually at the moment the only event camera company that provides up to 1 megapixel resolution sensors. Then there is Innovation that has partnered with Samsung. They provide VGA resolution sensors. And finally, there is Selex Pixel technology which has been bought last year by OmniVision. And they also provide up to 1 megapixel resolution sensors. However, as far as I know, they do not provide the polarity of the events. So you don't get negative and positive events, only that there has been an event. So why did we decide to use event cameras in this new data set? Because event cameras have especially very high dynamic range and also very low latency, which are very relevant for autonomous driving. Here you see some of the sample scenes taken by a FLIR camera on the right and the corresponding events on the left. You can see that, for example, events are not much affected by the sun in the field of view of the camera, or in general by abrupt changes of illumination, like, for example, when you exit the tunnel, when you have the sun in the field of view, or even in low light. So you can actually see a bit more than with standard cameras. So these are the key features of our setup. We collected this data set using a stereo event camera from Prophecy. We used a VGA resolution event camera rather than the 1 megapixel resolution one, simply because if you use the 1 megapixel Prophecy cameras, you get so many events that then logging them in real time is still an issue. So we decided to record them with the VGA resolution stereo event camera. However, this one is very good. It also features low noise and so on. We also added the stereo FLIR global shutter RGB camera. You can see here that the stereo baseline for RGB cameras is 51 centimeters, and the stereo baseline for the event cameras is 60 centimeters. And you see them here. So we have RGB event. Then we have here on the back an RTK GPS antenna, and then here on the tower we have a Velodyne pack, which is a Velodyne 16, but then we enrich the data by exploring motion estimation. So in the end, you get a very high resolution, very high density point cloud. And we also did a hardware synchronization, which actually took several months. The data set at the moment is 40 kilometers long, and it was recorded around Zurich, but not only in urban environments, but also on the mountains, in the Swiss mountains. Here you see also what our high-quality LiDAR maps look like. Overall, at the moment, the data set contains 1 hour of driving data, split into 53 sequences, but we are updating it on a weekly basis. So check it regularly because it might contain new scenes. I wanted to point out that this is not the first event camera dataset recorded from cars. There has been other datasets from Toby Delbruck, from Kostas Danielidis and Vijay Kumar, and many others that you see here. However, this is the first event camera driving dataset that has a higher resolution than all the previous ones. So we provide 3 times higher resolution than the one from UPenn called the MVSEC. We also have very accurate calibration and time synchronization between all the cameras, which was lacking before. We also provide the first wide baseline, and we also provide a color stereo for global shutter cameras. Now, the question is, what can you do if you want to start using event cameras and you are not very familiar with them? So there has been plenty of code, which I will show at the later in my presentation where to get it from. But in general, what I want to show you with this slide is that event cameras contain all the visual information that is also conveyed by standard cameras. So event cameras are typically only sensitive to the varying component on the visual signal. But we have shown in previous work that you can reconstruct the full grayscale intensity from event camera output. This is also what Andrew Davison has been working on. And what we did here differently is that we trained a recurrent neural network to solve this task. All the data sets, the training model, and the training code was released already 2 years ago, and you can find it here. So basically, we have an algorithm that takes as input raw events and output grayscale intensity frames. Now, the beauty about these grayscale intensity frames is that they enjoy all the key advantages of event cameras. So they naturally have very high dynamic range that you see in the middle. So the image in the middle here was reconstructed only from events. And as you can see, does not suffer from saturation when you, for example, have a very high dynamic range scene, which instead would be the issue if you were using standard cameras on the right. Here is a night sequence, and you can see again on the left that by reconstructing images from events, you can get very good quality grayscale images in comparison to standard images. You can use also event cameras to, for example, do slow motion. Here you see on the left a slow motion sequence reconstructed by a Huawei P20 Pro phone. And on the right, you can see our reconstructed frames using only events. And we rendered this video at over 5,000 FPS. So the video on the right was reconstructed fully of events. And here we were shooting a bullet to a puppet, and we were able to render this scene only using events. Here, what I want to show you also is that you can use then the reconstructed images as input to standard computer vision algorithms. So basically what we did here is that we take the reconstructed frames and we feed them to a monocular depth estimation algorithm like MegaDepth. And you can see, at least qualitatively, that the reconstructed depth maps look reasonable. So this is to tell you that it is possible then to apply standard computer vision algorithms to event cameras. Here is another application where we take the reconstructed frames on the right and we feed them to YOLO version 3. So now YOLO is working directly on reconstructed images, and we can show that basically it's working perfectly fine, like if it was working on standard images. But now remember that YOLO here will benefit of all the advantages of event cameras. So it will work on very high dynamic range scenes, very rapid scenes, because there will be no motion blur, and also in low light scenes. Of course, this doesn't mean that this is the best way to use event cameras. There are many other ways to do it. However, at the moment, at the current state of the art, we have shown, and many other people have shown, that if you first reconstruct frames and then you apply standard computer vision algorithms trained on standard frames, you can actually get the maximum performance. Now, the big challenge of today is to go end-to-end from events directly to the output of your algorithm. So ideally, you want to go from raw events to object labels, or from raw events to depth prediction, from raw events to, I don't know, to SLAM. Okay, so now the big challenge of today is to be able to do this end-to-end very efficiently without having to use this intermediate reconstruction. And I will get to this later. So this is basically a recap on the DSEC dataset. So it's already available, it is online, and we are organizing a competition at CVPR. And we encourage everyone who would like to participate to actually download the dataset and submit your results by the deadline, which is set on the 11th of June. The competition consists of doing a stereo reconstruction using events, and we provide the ground truth so that you can actually benchmark your algorithms. The winner of the competition will then be invited to deliver a keynote in our CVPR workshop, which is scheduled for the end of June during CVPR. So this concludes the part on the DSEC dataset. Now what I want to talk about is other work that we are going to present at CVPR about video interpolation. So we have been working with Huawei over the past year for computational photography. So there is a lot of need of the possibility of improving the temporal resolution of standard cameras for smartphone applications. So what we are doing in this collaboration with Huawei is that at the moment we are using, for example, an event camera paired with a standard camera. you see here, it has a very small baseline. So it's a dual camera setup. It has a baseline, but by knowing the relative position between the two cameras, you can actually fuse the two informations together. So this is what the sensor provides. It provides a high resolution frames at over 4K resolution, and then we have a VGA event camera. Sorry, a 1 megapixel event camera, so 1280 times 720 pixels. Now, what are we doing in this project? So this project is called the TimeLens, event-based video frame interpolation. And what we are doing is the following. So we take low frame rate input on the left, we add the events in the blind time between the two frames, and we can reconstruct high frame rate video. So the video that you see on the right was actually reconstructed using the last available frame and all the events generated until the time on which we wanted to reconstruct this frame. As you can see, we are generating arbitrary frames in color. Okay, so we basically pick the color from the last frame, and then we use the event camera to compute basically the motion, the moving components or the optical flow. Let me show you some cool application of that. So I'm going to animate the video in a moment. On the left, you're gonna see a water balloon popping recorded with a Huawei P40 Pro phone, which is the best Huawei phone currently available. This Huawei phone is very cool because uploads upsamples the frames from 2000 FPS up to 8000 FPS by a factor of 4. On the right, what you're gonna see instead is our TimeLens algorithm to upsample in a low frame rate video at 160 Hz up to 8000 FPS. So a factor of 50. So much larger than the Huawei phone. So let's see how it performs. I hope you can see the quality of the video in very high temporal resolution, but you can see it's very smooth. It's in color, it's very, very, very smooth. And we can do this by using events. Now, what is the advantage of using events? First of all, low power, because you actually need many less frames in order to do this. Second of all, much less data to store. In fact, the maximum number of seconds that you can actually record with the Huawei phone was actually 125 milliseconds, while using an event camera, you can actually extend this time to several minutes. This is possible because events occupy much less storage, okay, because they only sense the varying component of the visual signal. So this concludes the part on video frame interpolation. And if you're interested in using this work, we released fully all the data sets and the code, open source. So check out the link here provided if you want to play with it. I think this is going to be very important work for everyone who works on slow motion video, and especially in video frame interpolation and optical flow. Now let me move on a little bit to robotic applications. So some time ago, we started using event cameras for robotic applications, and we have shown in a paper at RAL 2019 that using event cameras, you can allow robots moving at speeds up to 10 times faster than with conventional cameras. This is made possible by the fact that event cameras have a very low temporal latency. So what we showed in this science robotics paper published last year is that we can use an event camera to allow a quadrotor to dodge moving objects thrown at the quadrotor. And we can do this with very low latency of only 3.5 milliseconds. And this is actually remarkable because with standard cameras, you would actually need at least 2 frames in order to compute the position and velocity of the object. 2 frames for a 30 Hz camera, it's already 33 milliseconds. So we can actually do it much more efficiently, much faster with an event camera. And we show in this work that we could actually fly with relative speeds up to 10 meters per second, which is 36 kilometers per hour. So watch the video. Now in slow motion. So here the ball is detected 40 centimeters away from the drone, and here you can see what the event camera sees. Okay, so we are only using events for detecting the ball and then to trigger the evasive maneuver. And now the question is, how is it possible to just use events to estimate the ball, to detect the ball and also its position? This is possible because remember that event cameras stream information continuously in time and not at regular frames like standard cameras. What you see in this illustration is actually a space-time visualization of all the events that have been produced during the past 10 milliseconds by a car moving in a city. And how is it possible to detect objects in this space-time visualization if you know, both the robot and the objects are moving? This is possible because each object will generate events that depend on both the depth and the relative motion. And this signature can actually be captured very well with event cameras. The way to do it, and the way we do it, is so-called contrast maximization. Look at this animation. What you can do with events is that you can warp the space-time volume according to the direction of motion that generated the events. So here, for example, we were able to see that by warping the volume according to a certain direction, we were able to identify a bicyclist. But depending on the different objects that are present in the scene, we can do this individually for each object, and then we will be able to identify the pedestrian, the bicyclist, or the facade of the building. So that's the same type of algorithm that we also used for the drone to detect the ball. So we call this algorithm contrast maximization. And we have different variations of these algorithms that have been published in 3 different papers. So we believe that this is actually a direction to go, for example, for motion segmentation and also for enabling, for example, self-supervision with event cameras. So here I end my part on motion segmentation. I want to advertise that we are also continuing to work on visual inertial odometry with event cameras. We have released a dataset 2 years ago. It's called the UZH FPV drone racing dataset, where we have stereo RGB frames, event camera, inertial measurement units, and ground truth from a Leica total station. And this is a dataset that was recorded with a drone flying very fast, because current VIO datasets are actually pretty slow. And so we wanted to encourage the community to actually work on very fast behavior, so enabling VIO for very fast motions. There is also a leaderboard available, and there you can actually upload your code, and you will be able to see how you rank with respect to state-of-the-art algorithms. This leaderboard implements the famous Common Task Framework, by the way, which I invite you to use. Other more recent work that was published at ICRA and RAL this year is how to use event cameras for enabling autonomous flight despite rotor failure. So typically when a quadrotor experiences a rotor failure, the quadrotor starts spinning on itself. And previous works like by Raffaello D'Andrea and Mark Mueller have shown that the only way to avoid the quadrotor from crash, the only way to prevent the quadrotor from crashing is to have a very accurate position information. What we did in this work is that we showed for the first time that you can use onboard sensors to provide accurate position information when the quadrotor starts spinning on itself, and therefore we can prevent crashing. We did this both with standard cameras, which are shown on the left, and with an event camera, which is shown on the right. So here we are simulating a rotor failure. So the quadrotor starts spinning on itself, but is not crashing. On the bottom, you can see what happens with a standard camera on the left and with the event camera on the right. What can we see? Well, you can see that when the illumination drops below a certain threshold, like 50 lux, then the standard camera suffers from motion blur and the quadroder eventually crashes. On the other side, when you use an event camera, you can sustain much darker environments. So we can go beyond 50 lux. In fact, we can go down to just 10 lux, and we can still sustain, you know, the very rapid motion of the quadroder. Here on the bottom, you can see how the algorithm works. So both the raw events and the features being tracked. So I'm going to finish soon. I have one last slide. We are now collaborating with the NASA Jet Propulsion Laboratory to explore the use of event cameras for future space missions. So these are a few images from the moon and from Earth. As you can see, when the orbiters pass over craters, it's very difficult to look inside. And also, when you try to enter caves on Earth, there are very abrupt illumination changes as well as very high dynamic range scenarios where standard cameras actually fail. So now with JPL, we are exploring event cameras to solve these two issues, and this to potentially enable future space missions, both for rovers and helicopters. So in 2030, 2031, NASA plans to potentially send drones and other robots on Mars or other planets, and we are seeing whether we can actually use event cameras to improve the operability of these robots on other planets. And with this, I would like to thank you for your attention, and I welcome questions if there are any. Thanks.
Thank you very much for your talk. So we have a few questions from the audience. The first question is, well, I guess I will start off with a question which I had, which is, I think one of the nice property about event camera is this high dynamic range and how it can cope with a lowly lit environment. Why is this the case? Is this because of the hardware of the event camera, or is this the nature of is it due to the fact that we're integrating intensity over time and the event is only triggered when we accumulated enough?
The reason why they do not suffer from motion blur is because of the nature of the event cameras. Basically, they look at the visual signal every time that the difference between the intensity value at the current moment and the intensity value at the previous event passes a threshold, then that pixel will trigger an event.
Yep.
Okay. So there can still be motion blur, meaning there can be multiple, you know, events that can be generated in the same within the time interval that you are recording the event, so within the same microsecond. However, the entity of this motion blur is much more negligible with respect to the that we have in standard cameras. Okay,
I see.
So that's why we actually say, although incorrectly, that they do not suffer from motion blur. They still suffer, but you need to be actually moving really, really, really fast. So just to give you an example, in the past we installed an event camera under a train, and still we were able to see all the scene very sharply.
I see. I was actually wondering, would it suffer more from motion blur under poorly lit environments then, because it will take longer to accumulate enough intensity for the event to trigger?
I didn't understand. Sorry, the sound is
sorry.
not very good. I didn't understand.
Sorry. So in a poorly lit environment.
In what?
In a poorly lit. So in a poor light condition. So a dark room. In a dark room.
In a dark room. Okay.
Yeah. Mm-hmm. Would it suffer more from motion blur because you need to integrate more light?
No, there is no motion blur. There is no motion blur. Just to give a very short answer. So even in low light, standard cameras suffer from motion blur. Event cameras do not suffer from motion blur. Okay, so it's a different type of motion blur we are talking about.
Okay.
There is no motion blur for event cameras.
I see. Thank you. And another quick question is: so it's a question. So how do we design an algorithm that are robust when there's an influx and lot of events which are coming at once? So
I didn't understand. I'm sorry. The quality of the sound is really bad.
Sorry, I can send you it by the message on Zoom if that helps.
Yes, that would help.
Sorry, I don't know why my sound quality is bad.
How do we design algorithms that are robust when there is an influx of lots and lots of events all at once? So we have this problem, but it's not a problem. Again, so look at this, for example. So we can recognize when this happens. It's only limited by the type of algorithm that you're using. For example, look at this here. Here the quadrotor is spinning, okay? And it looks like all the events are actually, all the pixels are spiking events. But this is not a problem for our algorithms because basically we have a very fast corner detector. So we use the event fast corner detector that we open sourced in 2016. And that basically reduces the amount of data produced by the event camera by a lot. So in the end, what we are really processing are only corners. Okay. So the only situation that the user is describing is when you turn on and off the light. And so all the pixels at that time is, spike events. However, this will be recorded by the event camera as, suddenly a huge amount of events coming all in in a very small time interval, or like less than a millisecond. So you can recognize it, and typically we skip it. But again, this happens very rarely.
Thank you. Thank you very much for the talk. And yes, I'm sorry about the sound quality. I will try and fix it. So thank you very much. Next up, we have a talk on event-based asynchronous sparse convolution network by Nico. And yes. So if you're ready, if you can start, that would be great.
Okay, perfect. Can you see my slides and can you hear me? Okay, nice. I'm happy to present our paper with the title Event-Based Asynchronous Sparse Convolutional Networks. I'm Nico Messekommer, and I did this paper together with Daniel Gehrig, Antonio Loquercio, and Davide Scaramuzza. With this work, we show that it's possible to use the sparse nature of events to make neural networks more efficient. But let me first show you why to use events in the first place. So, as Professor Scaramuzza already has shown you, event cameras possess several amazing properties, such as high dynamic range, low power consumptions, and high temporal resolution. Because of this high temporal resolution, they also do not suffer from motion blur. Event cameras also discard redundant visual information because they only output a signal if the intensity at a pixel exceeds a given threshold. So that means they only capture the motion in the scene. Because of these benefits, events are used in several tasks, such as flow estimation, depth prediction, or for frame reconstruction, as shown here on the bottom for typical HDR scenes of a tunnel exit. Moreover, the high temporal resolution can also be used, for example, to track the camera post in a fast rotational motion, or to capture a high-speed video, which is capable of capturing the destruction of a gnome hit by a bullet, which was fired by a rifle. Event data is intrinsically sparse and asynchronous due to the working principle of event cameras. This is nicely visualized here on the bottom left in this time-space volume. You can see here in this volume that this is quite a sparse volume. However, state-of-the-art event-based neural networks usually discard this sparsity And they do this by converting the events first in image-like representations, for example, voxel grids or event histograms. This has the benefit that they can leverage existing deep learning techniques and thus use several years of research to achieve state-of-the-art performance in the specific task. However, as I mentioned, they ignore the sparsity of the event data, which leads to a lot of wasteful computation, for example, in regions where there are no events present. With our work, we now want to leverage explicitly this sparse nature by formulating two steps or approaches. First, we want to, we formulate local update rules which process a single event in the input. So we basically update a neural network based on the input location. That means only the neurons are updated which have the input location in the receptive field. As a second approach, we propose to use submanifold sparse convolutions. So you can see here on the bottom left, standard convolutions, on the bottom right, submanifold sparse convolutions. You can see here nicely that the standard convolution computes for each pixel in the event frame the convolution operation. In comparison, on the right, you can see that sparse convolutions only compute the kernel weighted sum for active output sites, which means in our case for sites or pixels where there are events present. Let me first show you the local update rules with standard convolutions. So you can see here a single new event in the input marked here as red, and then the layer propagations. The regions in green represents the neurons which need to be updated based on this location. So basically it's includes the neurons which have the input or the new event in the receptive field. You can see here that as the depth grows, this region grows quadratically. In order to reduce this exponential growth, we propose to use submanifold sparse convolution. So we can see here again in green the output location which we need to compute the convolution operation. So we can see this is less than quadratic. In our paper, we also shown this theoretically, that this growth reduction is or can be defined by a fractal dimension. This fractal dimension basically defines how much the computational complexity grows with network depth. For dense convolutions, this grows with a factor of 2 or exponential to 2, but we show in our paper that the fractal dimension of events is strictly less than 2. This is also shown here in this plot where we have in x is the network depth and in y-axis the number of computation. The green line represents the normal convolutions. The red line defines or represents the upper bound which we found by introducing the fractal dimension, and the blue line represents the effective computation needed by our network. And you can see here that the fractal dimension is always lower than 2, and that also the upper bound on the effective computation complexity is valid. Okay, now I've shown you that our network needs less computational operations. I also want to now show you that it performs still comparable to dense neural networks. For that, we have tested our framework on 2 computer vision tasks on 3 different data sets. For the task of object recognition, we can see, based on our experiments, that our framework uses up to 50 times less flops, so floating point operations than dense CNNs. At the same time, it also achieves a 4.3% higher accuracy than state-of-the-art asynchronous methods. For the case of, or for the task of object detection, we show that our method uses up to 18 times less flops while still performing 24.5% higher mean average precision score than state-of-the-art methods. So in conclusion, we propose a new framework which directly uses the sparse nature of events to reduce the computational complexity. We have shown theoretically that this is related to the fractal dimension, which is strictly less than 2, which is needed for standard convolutions. And finally, with our experiments, we show that we achieve a complexity reduction up to 20 times and also achieve a similar performance as dense neural networks, and at the same time outperforming state-of-the-art asynchronous methods. We made our code public, so if you're interested, please go check it out on GitHub on the link displayed here.
Thank you, Nico, for the great presentation. And we would like to open the floor for questions. And I guess I'll start. So to use the submanifold convolution, do you need to modify the training process, or do you apply some changes to the actual convolution, which is already trained?
So for the training process, we can use dense learning methods. The one thing is that we need to train a sparse convolution network, so the submanifold sparse convolution. But the training does not have to be asynchronous, so it can be done like normally.
So you still need to train a sparse convolution, but you can just use a general framework to do so.
Yeah, exactly. So we can train it dense and then apply it asynchronously, basically.
I see. Thank you. Another question is, so I think the computation, you showed that it's computationally more efficient to use the submanifold convolution. However, is this easy to parallelize, or do you need to do it? So can you easily parallelize this kind of operation on GPU, for example?
So it is not easy to parallelize. The main reason because of this is that we need to access the memory dynamically, so we don't have a dense memory block stored, right? So what we can do densely is, in the end, the effective multiplication. So like from one layer to another, like multiplying by the weights, we can do this densely.
I see.
But the memory readout, for example, is not, yeah.
I see. So you need some, so do you have any, do you imagine are there some existing hardware which you might be able to implement this efficiently on, or do you reckon there's not any yet?
Yeah, this is what we currently look into it. So we try to find some suitable hardware which can especially support this like random memory lookup. So basically this is what currently is the bottleneck, but we have not found now the right hardware yet.
I see. So one last thing which I would like to ask is, when you did the evaluation, was this against a actual reading from event camera, or was this from like a simulation?
So basically the experiments were done on actual data sets. So this one here is released by Prophecy. So they captured a large scale automotive data set. So it's a real data set, as well as the two others. So NCARS is also captured from with a real event camera, as well as NCaltech 101.
I see. And I guess the noise from the event camera didn't affect the result too much.
It did not, like especially like this salt and pepper noise. Like if you have a single location, the sparse convolution actually helped to reduce this, because it only stays, like this information stays locally there, so it does not spread if there is no neighboring pixels.
Okay. Well, thank you very much for the presentation. And
thank you.
Yes, if you can join us for the poster session, which is in 15 minutes, that would be great, so we can ask you more questions.
Sure.
Okay, next up we have Edward, who will be presenting superpixel compilation for pixel processor arrays. So Edward, if you can share the screen.
Just getting there. Moving around on my windows. There we go. Is that up?
Yep.
Cool. So yeah, thank you for coming to listen to my talk about superpixel compilation for pixel processor arrays. It's by me and Paul Kelly, Department of Computing, and we just want to thank straight off Riku, Piotr, Stephen, Jingyang for their support and collaboration with practical stuff with the Scamp 5 device, and yeah, all that sort of help. So really, this is a story more about compilers than division systems. Basically, the idea is that we want to make it easier for people to take their convolutional kernels and actually get them running on focal plane sense processors, in particular Scamp 5. So a small quick recap of what Scamp 5 is. We have a 256 by 256 array of processing elements, and each one of these elements has its own little pixel. And so this is a massively parallel SIMD design where every processing element is going to be receiving and executing the same instructions at the same time. What's one of the limiting factors here, though, is that on the digital side, at least, we are working with 1-bit binary registers. So this means everything we're doing is got to be in bit serial, which for doing convolutional networks can be complicated because we want to be able to add up lots of values and multiply them and things. And the second problem is that we only have 14 binary registers, and only 7 of them are actually general purpose. So one of the big key things we're trying to do is allow us to leverage more memory by making compromises on things like resolution. So superpixels aren't new for us, by us. So Laurie Bose et al. Just showed that you can make a 4x4 square of these processing elements, and using this sort of squiggly pattern, you can fit a 16-bit value. So one of the main differences that we're proposing is that in Laurie's work, they use ternary weighted convolutional kernels, and they put those ternary weights into the memory of the Scamp processor. Whereas what we do is we encode the weights, not just ternary weights, but any quotient weight really, into the instructions instead. And so this means we can actually run much deeper networks because we're only limited by the number of instructions, which there are a few quirks around, but in theory, we're not limited to just those ternary weights. So one of the main points is that it's an extension to Kane. So Kane is a compiler that we built to effectively do the similar compilation job, but on the analog side of Scamp before. So what it does is it takes a convolutional kernel or multiple convolutional kernels, and it finds common subexpressions that then we can use to more efficiently implement the filters on Scamp 5. So the idea is that we extended Kane to use an alternative instruction set, which is based entirely on what digital operations are available. And then we can use that for superpixels using the digital side of the Scamp 5 architecture. So really, this is the main process. We want to take, we want a system that allows anyone to supply a convolutional kernel, run it into Kane, and they can supply what the actual data layout will be. So in Laurie's work, they had that 16-bit system. Here in this example, you can see there are actually a 4x4 superpixel with 4 different 4-bit values at every register. And so what we're able to do is make this trade-off between what resolution we want the whole image to be, what bit depth we want, and how many computational registers we want at every superpixel. And so there's a 3-way trade-off that we're trying to enable people to explore and find the right solution for them. And by putting it in an automatic tool, we hope that people are able to find the correct one that works for their situation. So the big point here is that there's data layout flexibility. So you see there's lots of different ways you can lay out bits. One of the key ideas here is that everything's done in a bit serial fashion. So every processing element is responsible for one significant bit of a number. But what we can do is we can have them all in one, like a 4x4 there with a 16-bit, or we could break that into two 8-bit sections. And so we call each one of these a different bank. Because of course you have 7 digital registers. So every bank, say, has 7 computational registers. And in that 8-bit post-photonic design, there are 2 banks. So that gives us a total of 14 computational registers, which is obviously a lot better than we get when we just have 7 1-bit registers. And of course, you can scale this this flexibility up for any sort of size superpixel, from 2x2 to 8x8 to 16x16. And of course, some of the problems grow and get harder when you get larger. Some of the problems actually get easier because there are more registers, or because you've got larger values, and so you don't overflow the numbers as much. So what's next? There's always more optimization work to be done. There are lots of things that could be made faster and more efficient. We could co-optimizing for the instruction memory size. So there's a problem we have at the moment where the amount of memory, of instruction memory it takes to store these long sequences is a big problem on the current devices. And so while we think this shouldn't be a bottleneck for future designs and future microprocessors, it is one for current sizes. And so there's some work to be done to optimize that. And then there's the whole spectrum of work about thoroughly evaluating different designs, and with the instructions that we have, which ones are more efficient and worth looking into more. And then there's also the question of what we can do in the hardware to make what changes we could do in next generations of Scamp-like devices that would enable faster and more efficient use of these data layouts. So if you have any questions, you have to answer them.
Thank you, Edward, for the talk. Well, I'll start off with a question, which is, you talked about being able to support different data layout, data bank layout. Is that optimized, or is it something which the user feeds into the system? And if it is, do you reckon it can be extended to automatically choose which layout is the best, for example?
So at the moment, what you can do is you just specify which processing element you want to be in each bank and which bit position you want it to be in. And what Keynote will do is it'll try and optimize the various high-level instructions like addition and moving based on those based on what you design. So for example, when we do addition, we have to do, because it's a bit serial, we have to do a sequential carry addition. So you select one PE at a time and go round to do the carry bit. And we can optimize that, and Kane will automatically find a somewhat efficient route to doing that. As far as in the future optimizing for the user, I think that's a whole nother design space. There's a lot of work, there's a whole other design space, because you've got to think about whether or not your values are overflowing, if you need saturating arithmetic or things like that. And you need to know what sort of values you're putting in to know. So there's a whole world of pain there if you were trying to automate that process as well.
I see. So the next question is, I think Kane used to only support analog instructions, and now the superpixel idea mainly is about digital register manipulation. How much of the heuristic from the original Kane is used to optimize the superpixels?
So as far as the infrastructure goes, it's basically the same infrastructure of the compiler that does the common sub-expression finding and the fastest routes. But instead of just being able to have an add instruction like we have in the analog side, we have to make an add instruction out of like many NOR and OR instructions, because that's all that's available for the digital side. So in that phase, Kane is working on the high level instruction of adds, and then it converts that into the lower level instructions of NOR and OR, and it tries to optimize those separately. So the first half is pretty similar, and but in none of this work we actually changed the heuristics needed, because we decided that would be too much while we were developing it.
So just to make sure, this means that this idea can still support multiple kernel filters. So if I feed the system like 3 different kernel filters, it will try and find the common sub-expression.
Yeah, so one of the big ideas here is that because we now have more registers, then we can definitely support more and more kernels all being compiled at the same time. And that should help, because there'll be more registers, it'll be able to find more efficient solutions.
I see. I guess another thing to ask might be, so currently we are using this idea of superpixel because the number of registers is limited. Let's say, for example, we just 4 times the number of registers available on the chip. Do you reckon this idea of superpixel will be still valid then, or do you reckon it's just easier to use the available registers?
So I think if you only 4x it, then it'll still be valid. Because if you think about this, in a 4x4 superpixel, you're sort of 16xing the amount of memory per pixel.
Oh, yeah, of course.
If you manage to 16x the number of binary registers per pixel, then yeah, you might start thinking that actually it's not worth it. But by the time you've got that much memory, you might also be thinking that why is there not a built-in arithmetic sort of 8-bit or 16-bit add?
I see. Well, I think thank you very much for the talk. And yes,
thank you.
Now we'll have the, I think, 30-minute coffee break, where again in GatherTown we'll be doing the demos and poster session. So if people can join, that would be great. And yes, our next session would start at 10 past 3 in UK time, and it will be chaired by Paul Kelly.
Hi, we have 3 really exciting keynote speakers, invited speakers coming up, so I hope you will join us. I hope you will also take advantage of the GatherTown option. If you haven't tried it before, it's well worth a try, to actually participate in the proper workshop discussions that we would be having if we had this meeting in person. Give it a shot. Look forward to seeing you there in a moment. Hi there. Yushin, are you there? Hi, Sajad. Hi, Yushin.
Hey, hello.
Hi, wonderful. Thank you for joining us. I'll be your session chair for today. I'm Paul Kelly at Imperial College.
Thank you.
I wonder if you've met my colleague who's leading this workshop, Sajad Saidi.
Yeah, nice to see you guys.
Do you have any questions, or are you all set?
I think I'm all set. So later on, I'll just take over and share the screen.
That would be great. So we expect to have questions typed by the audience. We have currently 16 people watching the YouTube view stream. So there's a YouTube live chat. But what I will do is read questions and select questions from there.
Okay, sounds good. Hello, Yusin. I hope this is not too early for you. Is the time okay? Yeah, it's 7 here, so it's okay. Okay, it's good to have a start the Friday early. Right. Yeah, absolutely.
It's very much appreciated that you're here. Sajad, you haven't slept all night, have you?
Yeah, yeah. It's once in a while, so it's not too bad. Yeah.
Mm-hmm.
Yeah. Now you have participants from any place, right? Right. Yeah. It's challenging to manage, but yeah. Finally, we find a schedule that works for everyone. That's yeah. That's pretty tough. Yes.
Turns out to favor the Europeans, it turns out, yeah.
Yeah.
Hey, Walterio, good to see you.
Hey, good to see you. Good to see you.
So do you know each other, Walterio, Yusin?
Well, I know half of the people here, perhaps, but no, I don't think I have spoken with the rest. So looking forward to see your talks and learn about what you're doing.
Yeah, sure.
You are in Facebook, is that, do I understand correctly?
Yeah, I'm currently at Facebook Reality Lab. So we're working on the AR VR devices.
Cool.
Yeah.
Is that in California or?
Yeah, the majority of people is in California, but right now everybody just working from home.
Yes, of course. Yes. Yeah, and Riku, I'm not sure we have met before, but great to meet you.
Nice to meet you. I'm a PhD student of Paul and Andy.
Excellent, excellent.
So
And,
just maybe one sentence about Rico. He's the author of BitVO, 300 frame per second
yes.
visual odometry, and Yusin is the author of Iris, the popular on-camera, on-chip neural networks. I think he's planning probably talk about that today.
Super.
We'll see. Yeah.
Super. Oh, and thank you very much for the organizers. I think this is great to have. I really hope that we can continue with the series, because there is much more to come on this space, and so it will be really important to see how we can preserve that. I think it's certainly the first time I see a workshop like this, and maybe the momentum is getting there. So I think it's super important. So thank you so much.
Thanks for your attending this workshop. So I think the time is the right time to start. Paul, is that
right? So it's my pleasure to bring you to the final session of the workshop. Well, I say the final session, but we have a discussion session planned for after this, and I hope that that will be an opportunity to do something different and to make it really worthwhile participating. So I hope you'll stay for that. Our session today, the final session, is three fantastic speakers. And what is exciting for me is how these three speakers span the interdisciplinary, multidisciplinary nature of what this workshop is about. So our first speaker, Yuxin Chen, has a prize for his PhD in computer architecture. This doesn't look like a computer architecture venue, but I think he's going to tell us that it kind of should be understood as such. We have later on Walterio and later on Boris covering different aspects of this subject area. So Yuxin is currently a research scientist at Facebook, working in augmented and virtual reality. He's most famous for his thesis work on Iris, which I imagine will feature a little bit in your presentation. Please, may I invite you to share your screen and tell us what you'd like us to hear.
All right. Let me start the presentation. So hopefully everyone can see the slides.
Yes, looks good.
Okay, awesome. So thanks again for the introduction, and good afternoon for our friends from Europe, but also good morning and good evening for everyone around the world. It's really a pleasure to present in this workshop. From the talks today, we can see that there are many interesting topics about different sensing and compute techniques to enable vision processing near the sensor. So in this talk, I'd like to approach it from a application and system angle to talk about where we are building at Facebook Reality Lab and why I believe there are many exciting research opportunities in this area. So specifically, I'll dive into our efforts on co-designing the hardware and software stack for AI to enable augmented reality or AR. So first, let me give some quick introduction on our vision for AR and what it can do for us. Consider this glass that we are wearing. It helps us to enhance our vision. But what if it can also enhance our perception of the world as well? So today, we rely a lot on laptops and smartphones to get information and stay connected with each other. But we believe in the very near future, AR devices such as glasses are going to replace them and provide a lot more value. The glasses can offer virtual reality, augmented reality, and everything in between, so that we can take advantage of mixing virtual and real worlds according to our needs. We will be able to wear them all day and interact with it in several very intuitive ways, such as using our voice and gesture, so that it can benefit many different aspects of our lives. So let me give you some examples. So imagine you're walking in the dark outside and it's very hard to see clearly. What if you can brighten up the scene you see with just a gesture? and it will look very natural without being very noisy. And imagine you're away from your loved ones that you want to spend time with, which is especially true for many people in the past year due to the pandemic. What if you can spend time with them virtually anywhere in the world in a way that it feels just like they are right next to you? Also, imagine that the glasses not only can give you 20/20 vision, but way beyond that, so that you can see like a superhuman. With AR, these are all possibilities. But we don't have to stop there. We can also build a glass to help improve our memory and cognition. Imagine you are in a business meeting and the device can automatically show relevant data based on the context of your discussion. Or if you're traveling, you can have the translation seamlessly right in front of your eyes to help you explore more places. Or when you're doing some grocery shopping, the glasses can send you reminders and directions based on your habit. But we don't want this technology to be dumb. We don't want the glasses to just show notifications all the time. It can be very annoying while you're driving or just chatting with friends. What we really need is for AR to be context aware, and what it would take is always on context aware AI to make that happen. To this end, you can think of AR as a personalized assistant with a perfect memory to answer your questions or requests when you need it. This is our vision of what AR will look like. And what does it take to get us there? First, we need really high resolution displays to overlay high fidelity virtual information. We also need eye tracking to help recognize what we're focusing on, which also requires the capability to do image recognition and semantic segmentation. There are also a whole lot more technology that needs to happen. For example, we need world locking and depth sensing to attach virtual information to a real world objects, even if you or the objects are moving. So all of this is to say that even for a very simple use case, it requires a lot of technology to come together at once. Many of them do not exist, and many of them exist in a different form factor that can be very challenging to port onto a device like a pair of AR glasses. So to deliver the best user experience, really need to deeply understand the user context. And that is a very interesting research area requiring efforts all the way from algorithms to the sensor designs. So if we look at the characteristics we'd like to see in AR glasses, it has to be socially acceptable. Basically, it has to look like the glasses you and I are wearing right now. Also, it has to be lightweight, so we can wear it all day without discomfort. At the same time, it also has to have the battery life to last for an entire day, so we don't have to charge it during the day, which could be a deal breaker for many people. Also, because it is a device that sits so closely to your face, you really have to be really careful about constraining its thermal dissipation, so it won't cause any discomfort. In terms of technology, these are the ones we've talked about already, and we need all of them to come together. But there's one component that stands out. Basically, AI is going to play a very critical role for all of the other components. It's already pretty common for us to use AI to enable computer vision or speech processing. But it is also very important for things like the physical design of the glasses. For example, we can use AI to compensate the quality and the quantity of the sensors on the glasses, which can eventually help us make the glasses lighter and even more efficient. Now, we not only have to enable AI on AR glasses, we also have to run those models locally on device. And there are several reasons why we need to do that. The first and foremost is privacy. because these glasses are constantly collecting data and looking the world as the way we're seeing it. So we really need to make sure that the data it collects only stay on the device instead of being shared externally without your consent. The second is latency, because we want the device to react very quickly, especially in many AR applications, even a few milliseconds matter. The third one is connectivity. Sometimes you might be in places where you don't have internet connection, and you would still like the AR glasses to work for functionalities that only require the information around you. And the last but not least is energy. This may sound surprising to many people, but processing data locally in many cases can save a lot more energy than sending data to process in the cloud. This is because wireless connection is not cheap, and sending raw data itself sometimes can be too expensive. So those are the reasons why we're investing a lot in making sure we can do the majority of the AI processing needed on the device itself. But AR applications are not homogeneous. They come in different shapes and sizes. I'm going to show you a list of example AR applications that have very different requirements. And we are going to focus on the 4 different axes here, including memory bandwidth, latency sensitivity, and how frequently we expect to run those applications and their compute intensity. As I go through the list of applications like speech processing, video understanding, eye and hand tracking, and many others, you can see that they all have very different requirements. Some of them, like video understanding, may be very demanding on compute, while eye and hand tracking are very sensitive to latency and are used much more frequently. This brings us a very interesting research problem, which is how do we enable all of those different applications that show very different requirements on a single piece of hardware. So here is a summary of challenges we faced to enable on-device AI in AR devices like glasses. So this is a quick takeaway of what we've talked about so far. From the application side, we need to support heterogeneous applications, which can stress the hardware in many different directions. Also, we need to provide the experience that there will be no user perceivable latency. Last but not least, we need to be able to process very high resolution data, which is very critical to a good AR experience. However, from the system side, we are also extremely constrained. We are looking at delivering the efficiency that is 1 to 2 orders of magnitude better than where we are right now. We also need to deal with a limited amount of resources like compute, storage, and memory bandwidth. Now, for most of the time, if we need to process high resolution data at very low latency, we will expect to have relatively beefy hardware. Or if we have very constrained systems, we will only do very simple tasks or only process very lightweight data. But to enable a good AR experience, we really need to achieve both at the same time. So the question is, how do we do that? In the rest of the talk, I'll give you one example and walk you through some of the research we're doing to enable it. So specifically, let's take video understanding as an example. Video understanding is an AR experience that helps you to understand the user activity and environment. It takes continuous frames, oftentimes at a very high resolution, as the inputs and try to reason from it. At the course level, you will try to understand the user's environment, such as if you are surfing, playing basketball, and many other different activities. At the finer grain level, it also digs into localized details in the frames, such as activity of different people and objects as shown in the figure on the right. Based on this information, video understanding pipeline can help provide personalized, proactive, and context-aware assistance for the user. So say you're out with your dog and you say to your AR glasses, take pictures of my dog playing with ball. You not only want the AR device to recognize the dog, you also want it to recognize your dog instead of other dogs. That's why it has to be personalized and context aware. Even better, the system may recognize something interesting you care about and automatically capture that for you. That's why being proactive also matters. However, enabling on-device video understanding is not trivial. First, we have a very limited amount of labeled video data. Second, a video understanding requires taking continuous frames as input, which can lead to very high system cost for sensing and data transfer. Last but not least, the compute and memory costs of processing high-resolution data are also very high. So to deal with these issues, we have looked into the following directions. On the data side, we study techniques like data augmentation and self-supervised learning. To reduce the system cost for video modality, we propose to leverage different sensor inputs on the AR glasses. Also, to reduce the inference cost due to the high resolution, we focus on hardware-aware model designs. So today, I'll focus on the research we do on the deployment side. Mainly, there are two deployment bottlenecks for video understanding: the camera cost and the ML model inference cost. A typical camera sensor has the power overhead of around tens to hundreds of milliwatts. If we were to run it continuously, it can easily become a huge overhead, and we cannot sustain all-day battery life. Also, not to forget that we are capturing high-resolution data, and the data transmission cost itself between the sensor and the SoC can also become very substantial. On the model inference side, typical models for video processing are very expensive. It can easily take hundreds of gigaflops in order to understand the environment and the actions around the user. So how do we go around those different bottlenecks? One of the ideas we have is to take a cascaded approach. Basically, we use cheaper sensor modalities as the trigger, such as audio data from the microphones and motion data from the IMU sensors. And when something interesting happens, we can then initiate the camera to capture and reason about what's happening around the user. And because capturing and processing audio data is usually orders of magnitude cheaper than images, on average, we can reduce the amount of processing by several orders of magnitude. Not to mention that we are saving on the camera sensing and data transmission cost for the majority of time. So let me give you an example. When you are walking around town and you choose to enable the video understanding functionality, for most of the time, only the microphone will be on, and it will detect the transitions in the environment and actions that's happening around you. The data at this stage is quite small, maybe in tens of kilobytes, and the model is also quite small, only in tens of megaflops. If the model detects something interesting might be happening, it can turn on the camera to capture a few frames. Now the input data becomes much larger, in hundreds of kilobytes, and the data is also a bit larger. But it can understand more precisely what's happening. In this case, for example, maybe there's a basketball game. And if this is something that the device thinks you'll be interested in based on your preference, it can go into full action where it starts taking continuous frames and combine that with the audio inputs. This is when we are going further and doing multimodal AI to further improve the accuracy. The inputs get very large here in tens of megabytes, and model is much, much larger as well. But now it can detect much more fine-grained actions and maybe capture the interesting moments for you. This is an example of how we can use a cascaded approach to achieve the balance between system energy efficiency and usefulness of the applications. So far, we've talked about solutions at the algorithm front. Now let's switch gear to the hardware front. Here, I'm showing a cartoon picture of what a typical SoC looks like. We can have many different components, such as an application processor and different IPs for things like speech and vision processing. Nowadays, it's also very common to have ML accelerators in the mix. All of those components will sit on a system bus for communications. So this is a typical way to do it. But a better way from our perspective is on the right-hand side, in which case we'll have dedicated ML accelerators being distributed into individual IPs. First, because of the heterogeneous nature of the different applications, we can have ML accelerators for each of them to be tuned to the needs of different applications, instead of just using one very beefy accelerator, which will sacrifice efficiency for each of the application. Second, it also saves a lot of energy on the system bus data transmission. By distributing ML acceleration, it keeps data local, reduce contention for bandwidth on the system bus, and overall can achieve a much better overall system efficiency. So now we've talked about using cascading approach on the algorithm front and doing distributed processing on the hardware front. Where this naturally leads to is toward near sensor compute. Similar to the cascading approach, we can offload some of the processing from the SoC to the near sensor compute. This has two benefits. First, it works just like other cheaper sensor modalities. We only turn on the main processing units in the SoC when something interesting happens. This is beneficial because sometimes using audio or motion signals may still not be accurate enough. Second, when we turn on the SoC, we may not need to send the raw data to it. Instead, we might be able to only send the preprocessed features or even the inference results, which could be much, much smaller. And this can further simplify the system design to use a cheaper physical link between the sensor and the SoC. Next, because we have the processing very close to the sensor, it also opens up the possibility for sparse processing and sensing. For example, we can use the near sensor processing results to skip capturing a few subsequent frames, or even just capture a subregion in future frames where we think the object of interest locates. So you're saving a lot on the actual sensing cost. However, this approach also comes with its own challenges. First of all, the form factor of sensor is a very critical variable to the design of AR glasses, which means that we usually will have a much tighter area constraints for logic at the near sensor side. Also, unlike the SoC, which is usually built on the most advanced process nodes, sensors might be a few nodes behind, which means that the efficiency of the processing might be compromised. This means that going to a near sensor compute setup might reduce the performance or energy efficiency for the overall system. So this is a previous study from Facebook, and it shows that it really takes a certain combination of algorithms, system design, and technology nodes to make the switch to near sensor compute worthwhile in an AR system. Basically, if the compute is too heavy compared to the data transmission cost, or if the technology node of the sensor is too much behind the SoC, then the total energy consumption of the system might be even higher in the near sensor compute setup. So to summarize, there are two key enablers for sensor compute. First, we need to enable cascaded ML models to leverage the multi-stage and distributed compute. This means even for the same modality like vision itself, we need to think about how to divide the task into multiple stages. Second, as compute intensity is really a key here, we would like to design a model that could take the full advantage of the hardware we have, which means doing hardware-aware network design is extremely important. So to optimize a model for a particular hardware, neural architecture search has been widely studied. Unfortunately, I don't have time to talk about the specific innovations we've been doing in this area, but this figure gives you a high-level idea of the approach we're taking to use NAS for software and hardware co-design. Basically, we use NAS to feed a hardware profiler, which can provide a direct feedback on how the model performs on our hardware. This can include things like latency, energy consumption, memory bandwidth requirements, and more. The information is then used to further guide the search process of NAS along with the accuracy results. Together, this loop continues until you get the results you want. So for example, as you can see on the right, we can use this approach to either keep the same hardware processing latency, but improve the accuracy of the model, or keep the accuracy the same, but instead improve the processing latency of the model a lot more. And we have been using this approach for almost all of the models we're building at Facebook. And this brings me to my last slides. I talk about the challenge we face in AR and the hardware software co-design we're doing to improve efficiency. But there are still a lot of different future directions that could be interesting for research. One is using the ML framework to achieve the network and hardware co-optimization. Right now, we are using a more iterative approach between updating the hardware and algorithm. But if that's possible, maybe we can put the design parameter of both sides in a single loss function so we can optimize them together. The second is lifelong learning. We say that the models really need to run the class in a highly personalized manner. They need to understand the nuance of each user because each of them are different. So having the capability to do some learning on device can be very important. This is also an important area that we expect to see interesting works in the future. And with that, this is the end of my talk. I think this is a very exciting area for research, and we still have a long way to go. But I'm looking forward to working with all of you in the community to bring it into a reality. Thank you very much, and I'm happy to take questions.
Thank you very much. We're a little short of time for questions, but I think we should nonetheless do so. Firstly, let me emphasize that if you have a question, please, you're invited to type your question into the YouTube live chat, and I hope you'll do so. There's some not yet any questions, but my job as your chair is to try and provoke some of those questions. We have a number of people around the panel today in the Zoom call who might also have questions. But while you think of them, let me ask you a little bit about some of the kind of fundamentals here. So you talk about the energy cost of running a camera. And if we have an always on camera, we've already trashed our battery for the day. Obviously, we might think about activating a camera occasionally. We might think about having a low power camera and the high power camera that you turn on when you need it. How much of the energy cost of a camera is to do with the sensing itself, and how much is to do with moving the data off the camera when you found something of interest?
Yeah, so this is a very good question, and we've been studying it. Also, it's a question related to the specific sensor design. In certain applications, we're seeing maybe the data transmission cost can be much higher than the sensing cost itself. But in other scenarios, we're seeing they may be half and half. So I think having some compute near the sensor give us the opportunity to reduce a lot of those data transmission costs. But what we're really looking at is also to enable some sparse sensing. So you use the compute to determine how much actual sensing you need to do a sparse sensing. That way, you cut down both the sensing side of the energy and the transmission side of the energy as well.
Thank you. Well, Terry, I wonder if you'd like to just speak up and tell us your question that's in the chat.
Yeah, sure. So a very interesting talk, Yushin. Thank you. So I guess my question is more about you can potentially have multiple models that you want to be working on processing your input signals. How do you balance this? How do you balance efficient implementation versus general hardware that can cope with multiple models, especially when you're bringing a NAS search into the mix?
Yeah, so there are many different applications that can happen at the same time on the glasses. So we have a mix of first-party applications that we definitely want to optimize for, and we're taking a more heterogeneous approach. So for a few of those really key applications that we expected to run very, very frequently, they might have their dedicated hardware, and we might even use NAS to just tune for the specific characteristics of the model. Of course, we have to reserve some flexibility for some future models, but we will have to prioritize the quality of different applications like eye tracking, hand tracking. Those are definitely the very, very important applications that we need to deal with very well.
Okay.
Thank you. I think we need to keep to time. However, please, there will be a discussion session at the end of this session, and I hope we'll follow up with more questions for Yushin and around these general topics. Thank you in a virtual round of applause for a fantastic presentation. Let's move swiftly to our next speaker. So Walterio Mael Cuevas is a professor at the University of Bristol. He's also a principal research scientist at Amazon in Seattle. He has a nice connection to the previous talk. I wonder if he'll recognize this or dispute it. His PhD was actually on wearable visual robots. I think you've moved on to a broader spectrum of things than that, Walterio. Please, and you may wish to go into display mode with your presentation.
Yes, I think I am presenting already. Can you see my slides?
We see your slide, but you could be in slideshow.
Okay. One question I have, which maybe the interface changed here. I think there is a way to optimize for videos.
We investigated this earlier. Video looks okay to me, actually.
Okay. It's just that when I play the videos, I just wonder if they will work, but you will tell me. Thank you very much, Paul, for the nice introduction. And let me just go into indeed display mode. And indeed, today I'm going to talk about some recent work that my team and I have been working on that have to do with how to actually put decision and potentially learning in this new class of sensor processor devices. And everything that I'm going to talk about here is with my university hat, just for full disclosure. And this is this is a picture of part of the team that I've been working on, and you will recognize some names here. Yana, and I believe already presented in the workshop. Piotr, of course, we are using his excellent architecture Scamp. And just for the benefit of those that may be hearing this on their recording, let me just reframe the problem here, where essentially traditional division systems have been composed by a amalgamation of modules that have to work together. And they start with things like cameras that have been designed for recording images, not necessarily for visual processing. And this these sensors often clog our data channels with lots of information. So there is a huge amount of bandwidth that is required to transmit video signals, as you will be aware. And usually what happens is that this enormous amount of data goes into a processor device. It can be a CPU more often, and because of the type of models that are being used for inference nowadays, we need external processors like graphic processing units, which again may not have necessarily originally been built for vision. They have moved significantly into the direction of handling things beyond graphics, but still we're talking about multiple components that are being used in order to process the significant amount of data that is coming from the conventional cameras. Eventually, you might make an inference, and this inference is sent to another processor that then conditions a signal that eventually leads to an actuator. So we're talking about vision for action. You have to go through a number of modules that send all this information, consume significant amounts of bandwidth, more energy consumption because of all the devices that are involved, and also system complexity, which complicates things. At the advantage of being able to just simply replace one of these modules if it is possible within your algorithm. But what we are really interested here in this workshop and the work that we've been looking at is how can you actually go from perception to action in a much more efficient way, so that we have the image sensing in a way that allows us to, at the point of image capture, extract high-level information, perhaps the direction of motion that we're moving, maybe the speed at which we're moving, maybe the identity of the objects or the location where we are. And we only output this high-level information, which is all you need for taking an action and potentially even directly connecting into some actuators. And what the advantages are, and as Yushin already mentioned, there are significant advantages for being able to do this type of close to the image point of capture processing. And they involve low energy consumption, low latency, you reduce system complexity, you can improve potentially privacy because you're only sending high-level signals. Of course, from high-level signals, you can still try to reconstruct and attack such a system in the encryption sense, but you're already not sending a lot of irrelevant information that otherwise you will be doing with a conventional vision system. However, I also want to add that there could be new opportunities here, apart from the ones that we're traditionally interested in. And that opportunity is new ways in which we can do the signal processing itself. And I will be hopefully talking a little bit about that today. But it's always good to take a step back and ask ourselves if some of these ideas are new. And I always make reference to this early work back from the 1950s when Levitt, Maturana, and McCulloch, three significant figures in the neurophysiology field, put a paper where they were talking about how the frog's eye processes information. And this is meant to be a frog that my 70-year-old drew for me. And what they discover in this paper is that the eye of the frog already does a significant amount of processing. Actually, a frog that is surrounded by food, but where nothing moves, it will starve to death. And this already tells you that the eye is not sending just wasteful amounts of information to the brain to act. It's actually deciding what relevant information needs to be sent. And we're not really talking about that the eye is able to detect things like black dots versus a contrasting background. What they discover is what they later called as bug detectors. So this is beyond just being able to detect black dots versus a nice clean background. These detectors behave to detect how these objects move in the visual field. So it's beyond just the visual appearance, it's how they are moving. So these are sophisticated inferences that are happening at the eye of the frog. And of course, the frog is interested in doing this so they can actually eat and trigger an action. The curious thing is that when Ledvin and his team talk about when they tried to publish this paper, they were essentially laughed at conferences because no one believed that the eye was doing more than just capturing images. And to some degree, we're still living in a world where we assume that our cameras are there to capture and record images and record detail. But the reality is that acting systems do not need to record wasteful information. They only need to record or actually process the information that is relevant for the tasks that they need to serve. So I think it's always interesting to talk about what is out there. However, I'm not arguing that whatever is out there in nature is the only interesting thing that that can happen. I believe there is a new opportunity here, something that, as far as I'm aware, does not happen in the natural world, and that is the ability of potentially learning and modifying the inference based on what is being perceived. So this can be very powerful because then we can have systems that can automatically learn and become efficient and process the information at the point of image capture without having to involve more sophisticated processing parts. And as a recap, you might have come across the Scamp before in the workshop, but as a recap for those hearing this in the recording, essentially we're using a pixel processor array, which is the Scamp developed by my colleague Kurt Dudek and his team at Manchester University. But essentially in the Scamp, what we have is that every light sensing unit has a processor. It has an ALU, it has multiple registers, it has flags, and it is able to connect, this processor is able to connect to its neighbors. So essentially you have a massively parallel architecture that allows you to do computation at the point of image capture. And then you can bring all these sort of things that we mentioned before about more energy efficiency, lower latency, and so on. The things that we've been able to do with this type of device involve several things that have to do from low-level signal processing to more high-level tasks like visual odometry, for example, or object detection. And let me see if this works well for you all. This is a very simple demonstration, but interesting. This is by Yan and Liu, who will represent you in the workshop. And he put together this demonstration where what we have is a car that has a Scamp device and is able to move around a place, recognizing from a potential universe of possible gates through which it can go through, which ones are the ones that it actually needs to go through. So as the vehicle is moving, is making decisions about which are the gates that you have to go through. And it's able to do this at relatively to the vehicle high speed. So let me just go to one of these other sessions. But by the way, are you able to see this video well over there?
It looks okay to me.
Thank you.
So
this is 3.8 meters per second on this small car, and is making decisions. It's like a slalom test that based on the pattern that is in there, it's making a decision to go left or right. So this is a basic demonstration of the type of things that you could be doing with this device. More advanced things, we have also done things like visual odometry. And because we're able to do processing at the point of image capture, we can, and actually important thing, this device is a general processing unit, because you can essentially upload different programs at any point and you can execute them pretty much with little lag in between. You can be running things like low-level image processing, like HDR image capture, and then later you can be using the PPA to do inference on a CNN. Or as in this case, we are calculating HDR images and then able to compute visual odometry in relatively simple ways. The way in which our ICCV, we have a Laurie Boss is a lead author here, but we have an ICCV paper where we do very basic processing to calculate visual odometry. And essentially what we do is we calculate HDR images as they arrive, and then we perform distortions of motion. Essentially, we are applying a motion model, and based on the best matches, we're able to make an inference about how this camera has been moving. And then we can put it together in a way that allows us to have an understanding of how the visual odometry is working. So let me just go to this other part, but essentially here you see the camera moving around and the system estimating where it is. There will be a better visualization here where the camera is moving in a courtyard and you're making turns, and the system is estimating how you're moving and when you're turning and so on, based on extremely simple vision algorithm here. And everything happening at, in this case, it was working around 1,000 frames per second. So we have also been able to connect this processing with other tasks, such as drone racing. So in this case, you might be familiar with drone racing, where essentially what you have is these gates in the environment. And in this case, we have a Scamp system that is detecting these gates, is detecting these frames that are in there, and is able to decide that which one of these gates is the closest one, and therefore it goes through it. And then we have been able to also develop algorithms that implement CNNs on the Scamp device. So essentially what you have here is a camera that is making inferences, and it's outputting only the identity of the objects that is able to see. So in this case, for example, this is using, again, a relatively simple data set, the MNIST data set, where we're able to detect in faster than usual real time what the camera is observing. And this is using a CNN in there. And the way in which we're able to do the CNN with a massive parallel computation that is in the PPA is, as an example, what we have in these recent papers. We have one paper in ECCV and another one in BMVC. They use slightly different ways in which these CNNs are implemented. One has more emphasis on speed, and enables us to process at tens of thousands of frames per second, depending on the classification challenge and task. But the way in which this works is that when we have an input image, we, in order to benefit from the parallel processing, we duplicate this image, which then allows us to multiply the different convolutional kernels. From which we can get an output that we can apply an activation function like ReLU, and then do auto processing like max pooling, all in parallel, before we also use a fully connected layer also implemented within the PPA. So essentially, we can have a CNN that is in the device at the point of image capture, performing inference. And we can update the CNN with different tasks in real time. The way in which this works in slightly more detail is that we have the image. Here we have an example of a basic kernel that we are duplicating. And because we're duplicating all this, we can, in parallel, thanks to the way in which the Scamp works, we can apply this this kernel filter in order to be able to go to the next step of the network. And in order to increase the speed, we can also apply strides. So we can have strides of stride 4, for example, or other levels of stride, depending on if we can afford to do this mostly for the reasons of increasing speed of inference. And all the details of these are in the BMBC and ECCP papers that we have on this work. And then the same for the activation function. We can indeed perform the activation function in parallel thanks to this duplication, and eventually do max pooling, which after we do the max pooling, we're able to then apply the fully connected layer, where we can also store all the weights for the fully connected layer in our digital registers, which are then multiplied by the max pooling image to obtain a final result, which eventually leads to our classification. So this is a massively parallel application that we have on the Scamp with the CNN. And this is a demonstration that Jan and Lou in the workshop already spoke about, but I want to emphasize again, because apart from the speed at which you can be doing inference with CNNs, with the Scamp and these algorithms that we have, there is another important thing here to highlight, which is the very low latency that we can have. So in this case, even that the system is not implemented with the best possible technology for the Scamp, and the actuator that we have here is fairly slow. Essentially, we can have from image capture, passing through inference to image class, and sending the signal out to the motor directly from the actual device. Nothing else is put in between, in 120 microseconds, which of course is a very good number for fast reaction. We have also worked on other data sets, for example, classifying plankton or MNIST numbers, and depending on the classification challenge and task, we can achieve different frame rates. The other thing I want to talk about is we have spoken about inference, but most of the inference, essentially all the inference that I spoke about, happens on the Scamp. However, the training and the learning happens offline. So we train offline, and then we port into the Scamp the model that is then executed. But what if you actually want to learn as you're processing signals and then do inference at the same time? So this is not full SLAM, I will say, because we actually have distinctive steps in terms of mapping and localization, but this is perhaps one of the first, if not the first, on-sensor mapping and localization work. And it has been presented here in ICRA 2021, and is a work of Hector Castillo Elizalde. And essentially what we have is a topological navigation framework where we have nodes, which are pictorial nodes. So these are images that have been represented with small images or with descriptors, and then we use this information in order to know where you are. And we have in the paper explored two different ways to represent this information. One is to use descriptors for the images that we're observing, and the other one is using small images like 8x8 pixel images, which other systems have been shown to be able to do fairly good and robust detection, even with small images. So essentially what we have is a mapping procedure where we capture all these nodes, we put them into the Scamp registers, and then here's an example. As the camera is moving, we have actually tested two methods for mapping here. One is based on the difference between the previous image and the incoming image. If we see enough difference, then we actually create a new pictorial node into the system, which is probably hard to see, but it's growing here. So these are the nodes that the system is capturing. That's one way. The other way is just every temporal interval, we add a new node. And then we test these two different approaches for the image representation. But what you essentially end having is something that allows you to do mapping and localization in a way that is reminiscent of a particle filter, because we have nodes, we have weights, we improve the likelihood, and we have a motion model that allows us to know where we are. And in the interest of time, I think I am going to play the video, which is here, and that in a minute summarizes what we're doing. Let me know if you can see and hear well.
In this work, we present a method of visual localization performed directly on the focal plane of the pixel processor array sensor. PPA sensor incorporates processing and memory into each pixel element, allowing visual data to be stored and processed on sensor.
So it's very quiet, we'll tell you.
Our approach involves first capturing a visual database onto the focal plane from a sequence of select images.
Is that better?
Select image is encoded as a node in this database.
I think we could go a lot louder.
The PPA is used to directly compare each new image with every node in the database simultaneously. This comparison is used to update the weighting for each node based on the visual similarity between it and the new image. When combined with a motion model that transfers weights between nodes based on camera motion, this approach allows localization to be performed over a sequence of images, effectively by determining the best matching sequence in the database. We test our approach on a number of video datasets. Here we see the Nordland train dataset with a database of branded descriptors generated at a different time of year than the video sequence used for testing. Despite the visual differences between seasons, our method is able to localize along many parts of the dataset. We also tested our approach on both urban and simulated video sequence datasets, testing both databases constructed of binary descriptors and low-resolution images. It has demonstrated results comparable to similar methods, while conducting all significant computation on the focal plane of the PPA sensor, rather than using external hardware for this processing.
And full details on the ICRA paper for this work. Okay. So essentially, with this, I will close my presentation, and essentially, it's a reaffirmation that the notion that we have to split the sensor decision making and action is overly simplistic and highly inefficient. So as we want to move into systems that are better for IoT reasons or for robotics, then clearly we will benefit from different ways in which we want to create these visual pipelines. And so redefining the way in which we process visual signals is very important. And a significant component of that is the type of hardware and the frameworks that we're wanting to develop for this. And just as an open question, one of the things that I believe is coming from the point of view of this in this space is trying to understand where can we do what processing, and trying to understand what are the best places in which we can and we should be doing what visual processing. Okay, with this, I finish, and I don't know if we will have time for questions, but if not, as Paul mentioned, we can also talk about that in the discussion panel. Thank you.
Thank you very much, and let me lead a round of virtual applause. Let's take a moment for a couple of questions if we can. The YouTube people are a little bit lagged. You can still type a question in the chat there. I'd very much like that. But meanwhile, perhaps there's somebody on the Zoom call who has a question. while you think of that, I'd like to ask you, Valterio, this question, and this is a question you asked me, so it's a little bit unfair. You touched upon it a moment ago. What tool support do you imagine might help us map the computational pipeline onto a system with multiple layers of processing, from in the focal plane to near the sensor to perhaps in a visual processing unit and so on? What do you imagine that programming model should look like?
I think this is indeed a very important question, Paul, that I don't have the answer. I mean, at a high level, you can imagine that you can formulate everything as an optimization problem. So it should be possible to formulate an optimizer. So like network architecture search is doing, right? So where you will be able to formulate a problem as an optimizer, where you have your constraints, maybe you have things that you're able to measure relatively easy, like the energy consumption, if you have a decent way to simulate that, or the lag that you are going to achieve, or the bandwidth that is going to be crossing the different modules that you have. So you can formulate some of these things as an optimization process, and I believe that is like the most obvious thing to start with. However, there will be other tasks, like we have touched on. Are the systems better for privacy? How do you formulate things that are more subjective like that into a mix that you likely, especially when we talk about vision processing, likely will need to be considered? So this is what I think still needs quite a lot of research. But in very general terms, I can imagine something close to an optimizer, maybe close to natural architecture search.
Thank you. Is there another question quickly? In that case, let me thank our speaker again, and we should move swiftly on to the final speaker of our workshop. So let me remind you before we start with that we will have time for discussion and to meet socially in the Gather Town after this. And I hope that you will stay for that so that we can actually meet each other properly. So meanwhile, it's my pleasure to introduce Boris Merman. So as I mentioned at the beginning of this session, we are spanning multiple disciplines in this workshop and in this session. And we've talked about wearables, we've talked about neural architecture search. Boris, I don't quite know what you're going to say, but I think you're going to push that envelope a little bit for us. Thank you. Please take it away.
Yeah, thank you very much, Paul, and thanks everyone for inviting me. This is my first time at this venue. So I'm an analog circuit designer, and I'm only dabbling a little bit in computer vision. I'm not a pro, but I want to show you some of the work that we have done in the last few years, and it actually relates quite a bit to some of the things that I've seen in these presentations. Just a little bit general background. So I am interested in general in finding efficient ways of bridging the physical and the digital worlds, innovating in the cracks, building better interface circuits, and building better circuits that facilitate better back-end processing and kind of trying to fuse things together. And the end product in my group is very often a custom chip. So we're in the business of designing chips for many different applications, and computer vision is just one of them. So I want to start by giving you a quick outline. I want to highlight two of our previous works here. The first one was an attempt at near sensor processing that we did and published a couple of years ago. And then the second one has to do with an attempt of accelerating deep neural networks. And really what I'm interested in ultimately, and what I'll get to in the end, is how do I connect these two efforts in the best way? How do you actually get efficient computing and the right amount of near sensor processing combined? And hopefully we can have a good discussion about this. We start with the first topic. So really, I think from today's perspective, this is a blast from the past, because we started out by looking at handcrafted features, right? This was a common way of doing machine learning decades ago, but it turns out this is still attractive when you're thinking about hierarchical decision makings and always on type, low-end tasks. But even when you resort to handcrafted features and build relatively simple systems, one of the problems you have is this need of pixel-wise A to D conversion. So you take a lot of raw data, dump that through an A to D converter, and it goes into memory where data movement is very expensive on the other side of the A to D converter. So the question is, and of course we didn't invent this, many other people have been working on this, is can we do the feature extractor before the A to D, right? And save some data movement energy in the back. As I'll say later, this may not necessarily reduce the total analog energy, but it is meant to prevent this deluge in the back of moving redundant digital stuff around. So the particular feature that we looked at was a histogram of oriented gradients. That was actually state of the art not long ago for handcrafted features. So we snapped onto this for this little study. And I don't have to explain that to you folks. I think you first make a gradient image and then you turn that into histograms, and then you do inference based on these histograms. So one of the things you need to do here is you need to compute gradients, for example, a horizontal gradient and a vertical gradient between adjacent pixels. And one of the issues that comes up, and this is something that we have been zooming in particular, is that the gradients themselves have a high dynamic range if the image has a high dynamic range. So in a bright patch, the difference between two pixels may be a large number, may be represented by 300 millivolts. In a dark patch, right, if you multiply all the intensities by a quarter, say, that same gradient may be only 75 millivolts. So this is sort of visually shown here also. So if you have a scene like this, there may be a person in the dark, and the gradients around that body have a different magnitude than the gradients of the person on the bright piece of the image. So what it means is that you actually need to represent these gradients with relatively high resolution, or you will lose the information. And so the idea that we had and wanted to implement was to say, can't we do something more ratio-based? And this goes back a little bit into Weber's law and some of these fundamental ideas of perception actually being more logarithmic and ratiometric. Instead of computing the gradients as differences, shouldn't we compute them as ratios? So if you compute the ratio of two pixel intensities, you can actually, at least to first order, I mean, I'm not getting into noise issues and things like that, but to first order, the illumination actually cancels out and you become illumination invariant. So you may ask why this is a good idea. Well, the whole point is to drop the dynamic range that comes from illumination variations across the image. Because once you calculate these gradients as ratios, what you can do is actually quantize very aggressively. You can, for example, quantize these gradients now into 1.5 bits, where you say, well, there's either an edge or there's a negative edge or a positive edge. And it doesn't really matter what the illumination is, because that canceled out before you hit the quantizer. So the high dynamic range of the image itself actually doesn't require extra step in these quantized ratio. So we experimented a little bit with 1.5 bits, which means 2 levels, and 2.75 bits, which means 6 levels. And I'll show you some results on this. So the other nice thing is that you not only now save bits in terms of what you need to express these gradients, you can also compress the histograms now, because the histograms have a much smaller library of entries, and they can be compressed in a very efficient way, it turns out. So we found out at the end of the day, the net benefit you get from this ratio feature is that you get about 25 times less in hog feature data compared to a standard 8-bit image for which you would take linear gradients. So here I want to show a little bit some of the experiments that we did on the effectiveness of this coarse quantization. So this is just the baseline. When you take a linear 9-bit gradient of an image and you vary the illumination, that's what I did on the x-axis here. Well, the average precision, this is an object detection task, It's relatively stable within a range, but then as expected, it would drop off if you get too dark or if you get too bright. And here on the right side, you see the illumination changes. At some point, you just saturate the image or you lose some features. And so with 9 bits, you're doing reasonably well. So now if I tried and I aggressively tried to quantize these linear gradients, things look very bad because, well, the range over which this works goes down because of what I discussed previously. You're losing a lot of edges in this image that have a different exposure and so on. But now if we drop in the idea of using these log gradients or ratiometric features, the features become illumination invariant, and you see here the gradients actually look the same no matter what the illumination is. And yeah, lo and behold, you actually get a very good performance across the illumination. When things get too bright and you saturate, everything dies, but that's to be expected. So there's a small difference here between 1.75 bits and 1.5 bits and 2.75 bits. And that just has to do with the fidelity of the gradient. So it depends a little bit on the application, on which one is good enough for you. So we always build chips out of these studies in the end to make the rubber hit the road. So what we did here is actually not as fancy as some of the things that I've been seeing here. We started out with a vanilla 40 pixel array. So these are regular imager pixels, 40 structure, 5 micron pixels. And then whatever we bolted on actually sits in the periphery. So we have a 3-row buffer. You need an analog buffer if you want to calculate analog features. So we have kind of a 3-rank memory that allows us to store these and then do computations with them. I'll show you how that's done in a moment. And then we mux this out, and then instead of going into ADCs, we call these RDCs because they're ratio to digital converters. And we also, just for debugging, we had a raw image output just to see if this whole thing works before we do any computations. Here's some of the circuitry for the analog designers. Of course, in an image sensor, you have very skinny columns. So these readout amplifiers, they're very minimalistic. And so the way the computations are done is that for each row that you want to process, there's a separate storage capacitor. And then, you kind of average between these to do your computations. And then we have a 4th row to allow for some image pyramid computation. So this is a little bit beyond the scope of this talk, but I just wanted to mention it as an aside. Snapshot of the ADD converter for people who design ADCs. This looks reasonably familiar. It's basically a successive approximation structure, but instead of subtracting the converted result from the input, you're actually dividing the input. And this is actually a very easy way to build kind of a ratio ADC. Log ADCs in general are pretty difficult to build. Try to build a 12, 14-bit log ADC. That's very difficult to do. But this 1.5-bit or 2.75-bit log is actually easy to do because it's just a couple of successive divisions that you can implement in this feedback network. So here's a summary of this. We can chat about more details if you're interested, but we have this chip. It's a normal CIS process, 5 micron pixels, like I said. And this imager per se is not setting any record performance numbers. The energy or power dissipation is what you would see from a vanilla imager with a given dynamic range. This was kind of a 60 dB dynamic range design. It's not extremely large, but decent. And so that runs at a couple hundred microwatts. And so the benefit really that we wanted to demonstrate is that the data that this thing pumps out can be highly compressed and save you in computation and memory access. And so we quantified that one in just the raw hog feature data compression, which is 25x. And then we tried to estimate this. We didn't build this deformable parts model detector at the end, but we think that you get at least a factor of 3 in power savings because there is less data coming in. There's more compressed data coming in. All right, so one thing that inspired us ultimately about these 1.5-bit log gradients, it seems like they're preserving information really well. And here, Julian, he's probably watching, helped us a little bit with this. you can take an image and then you make 1.5-bit log gradients, and then you can actually try to reconstruct this image based on the gradients with a simple algorithm. It's remarkable how much information you actually preserve in these log gradients. Of course, you lose some. This is lossy, but it looks very, very good. And so we're wondering, hey, why don't we ditch this deformable parts business and hog and so on, and really try to connect this effort now to deep neural networks, which are clearly winning the race nowadays in terms of classification accuracy. And so ongoing work in my group now says, what would it be like, or what would happen if we dumped these log gradients into a CNN? And so here's a little Mickey Mouse experiment that we did some time ago. Instead of using a regular image, we take a log gradient image and we train a neural network. We can train it in different ways. Here's an example that just says, train it such that at higher levels of the CNN, the L2 distance between the high level features are minimized. Train these new filters that act on the 1.5-bit gradients to minimize that. And we get remarkably good results. And so this has now motivated me now to launch a deeper study. Unfortunately, I do not have conclusive results on this yet. But what we're trying to essentially get to is that we want to get into a position where the first layer of the neural network is heavily quantized, right? This is not possible in a normal neural network, for data and energy savings. And also, and this is also something where I'm still collecting data, is that it seems there's a complexity reduction possible in the neural network. So we have some results that showed that a neural network that is shown log gradients may need fewer filters in the first couple of layers, simply because you have the whole dynamic range collapsed of the image. So I don't have hard data on it yet, but I'm sort of dying to establish this thoroughly and publish on it at some time. Okay, so now I want to shift gears a little bit and want to show you the second line of work that I really want to get connected to the first one, and this is the work in progress. All of you know how CNNs work, right? It's a massively parallel compute operation. The computer architects call this embarrassingly parallel. What's a little bit annoying, and I just said that, is all but the first and the last layer can be aggressively quantized. And so people have been looking at ways to make these operations lower power. There are definitely digital CNN people here in the audience, so I want to make fun of them a little bit, right? I mean, the digital approach, and we've seen that on the previous slide as well, is you're shuttling a lot of data around between different memory hierarchies, and then you have these processing elements that give you a good amount of parallelism, but not enough to do all the computations in one shot. So every time you compute something, you're hitting some piece of memory, let it just be a register file. You can very easily show that there's a strict upper bound that you get from these architecture just based on data movement. Forget the energy it takes to multiply or add, it actually doesn't matter. It's moving the data to these multiplies and adds is what limits everything. And so we see in current, even highly optimized digital accelerators, crossing 10 TOPS per watt is actually very difficult because of this. So my group asked the question, well, if we make something that's probably not as programmable as other things out there, and maybe a little bit smaller, right, for direct processing of small image sensors, always on type applications, can we just unroll this whole thing and just eliminate most of the data movement? And this is what the idea that we had in building what we call a mixed signal binary net, where we unroll all the input activations into a long vector, say 1024 wide. We unroll each filter completely, and then we have heavily quantized implementation, 1-bit multiplication with XNORs, and then accumulation with switched capacitors. And so here you basically have input volume, filter volume, and here you get that dot product pixel out. And everything happens in one shot in parallel without any data movement. And the weight is local, so it's a weight stationary architecture. So this is a fully unrolled circuit, mixed signal that performs all of this in one shot and with very little data movement. So we made a chip out of this. So this is not as of now. I mean, we are working on more sophisticated prototypes now, but this wasn't good enough for ImageNet, but it could handle CFAR10. This is kind of an 8-9 layer network with 2x2 kernels. And really the contribution here was to show that you can get to energies for CFAR10 as low as 3.8 microjoule per classification. So this brings you under a milliwatt, even for hundreds of frames per second. This was done in a reasonably advanced process, not extremely advanced. So even by today's standard, I haven't updated this chart in a while, but this is pretty much one of the most low energy implementations there is at the CFAR10 level. The accuracy is a little bit held back by the 2x2 filters. We made a mistake. These really should have been 3x3. But you know, this number of a handful of microjoules per classification is much lower than whatever you get from other custom processors. We built a digital version of this as well, which came somewhat close, but still isn't quite as good. So now here I want to maybe start sort of the discussion a little bit. So clearly my objective, I said it in the beginning, is now to join these two efforts. I'm actually interested in bringing the physical image closer to the DNN computation. And I just want to highlight the way this is done right now is actually somewhat ridiculous in my mind. And the previous talk pointed this out already. Someone takes pretty images for a few years. They go through this ISP that does tone mapping and all these things. And it spits out these beautiful JPEG images that have nothing to do with what the sensor actually detects, more or less. And then we take these visually appealing images and we let go a few million DNN designers, and you know they're trying to squeeze these DNNs until nothing is left in the lemon, right? And I think we've reached the end of this pretty much, and I don't know what the benefit is anymore. You now actually start seeing papers where people say, oh, we have these super optimized DNNs based on this flow, and now we connect that stuff to a sensor and it seems to be falling apart. Well, this is not surprising because you're not training with real sensor data. You're training with these images that have perfect angles and illumination and so on. In a real world application, you don't get that. So I really want to get more into this flow below where you have real sensor data sets, not pretty JPEG images, but actually raw images or log images of some sort that are more physical with varying amounts of illumination across the images, occlusions and so on, different angles, something that a real sensor would see. And that's where a lot of these things would be used, maybe on robots and so on. And then we should engage in a joint optimization of this. And definitely it's not going to be a general ISP that makes beautiful images. It should be something else between the image sensor and the DNN. Maybe a log is enough. I think maybe some of you have some good thoughts about this, but you clearly need something between this and the DNN. But this should be jointly optimized based on real data. So this is sort of where I am. You know, based on my first couple of exposures to this field, this is where I want to go. So I'm going to sum up with that. So I have dabbled in feature extractors that are near the sensor, not really in the pixel. And then we played with low power mixed signal DNNs, and these two things have a clear connection point. But for me to make more progress, I want to get to a more holistic, less siloed view of this whole processing pipeline that doesn't run on pretty JPEG images. I'm actually working right now on making a data set if someone has ideas on how to best do this for real world images. It would be fun to chat. And then I want to encourage kind of the deep learning community to stop optimizing this DNNs based on artificial data sets. I mean, it's great for winning competitions and things like that, but we should ask what happens in the actual application and see what is needed to perform well in the real world context. I think we've learned enough about the fundamentals now to kind of think more about the real world. All right, but this is all I had. Thanks again for having me. We'll be happy to chat with you folks now.
Thank you very much. That was really exciting. Please, another round of virtual applause. Listen. Thank you, that was great. I'd like to remind anybody who's watching on YouTube, please, there's a YouTube chat and I invite your questions there. In the meantime, while you think about that, I hope perhaps that there are colleagues around the table in the Zoom call who have questions for us. While you think of that, I think it's my job as the session chair to think of something. And I was really inspired by your talk to wonder what happens if we push it a bit further, almost to the pre-sensor processing. So very commonly in an image sensor, we have things like a Bayer mask. We can also think about the properties of the photodiode, including dynamic properties. I wonder if you have thoughts on how we would optimize at that level for, well, understanding rather than image capture.
Yeah. So this is not really my domain. I agree with you. This should be looked at, and I think several people are, right. Gordon Wettstein at Stanford, Julian's advisor, is working on this, and I think it makes a ton of sense to explore this and basically make it a part of the whole deep learning training pipeline, right? If you have such filters available before the image sensor, you can probably train them very nicely. And yeah, that is a zero power first layer, basically, right? That's the attractiveness of it. And yeah, I think the jury is out in terms of what will this look like cost-wise and so on. I think scientifically, I think it's a no-brainer to pursue that. We'll see if the industry will adopt it. I guess that's where I have the most questions. How economically feasible is this? And I don't know enough about the technology to judge it.
Thank you. Yeah, absolutely. Well, Terrio, I think you have a question. Would you like to speak up?
Yeah, no, thank you so much for a super interesting talk. I echo what you're saying about being truthful to the actual applications and using real signals. My question is, what are the actual applications that you are looking at that will be informative enough for us to show to others that this is the way to go?
Yeah, I think robotics is a domain that seems appealing. I don't know if this will really be the ultimate killer app, right? Who knows what they are in 10 years, 20 years. But I have found that, I have a reference here. There's this paper on OpenLoris. These are some robotics people that actually developed a very nice sensor data set with the kinds of features that I like. So I find that the robotics people are the most open to this problem right now. I don't find enough people in computer science who want to look at this. So I'm kind of clinging on to the robotics myself a little bit as an application. I mean, I bet there are applications in the commercial world, right? Putting these sensors on AR type devices and so on. But these are still emerging a little bit and are abstract and kind of owned by the Facebooks of the world, right? We had a talk about this, but I think it's going to be robotics for me.
Okay, that's great to hear. Thank you.
I mean, in a way, I think that's more or less what you're doing with these little autonomous cars and things, right? I mean, that looked very nice to me actually as a good example as well, right? You get real signals and they're vibrating and the illumination is all over the map, right? I think this is the way to go to make this stuff work.
Thank you.
Yeah.
Thank you. I think we have another question which has been typed in the chat, but Edward, you're on the call. Perhaps you'd like to speak up and explain your question.
Yeah, I guess the question. So you had these fixed function convolutional kernels processes that you were doing. I was wondering how difficult would it be, or are the kernels that you can run changeable dynamically? And then how difficult would it be to have the output go back into the array?
Oh yeah, it does that. So this is a very cartoonish schematic. The output activation. So we basically compute one layer, and then the outputs, they feed back as input activations again. We actually sequentially compute a number of layers with the same neuron array, basically. And inside the neuron array, these weights are programmable, and in fact, they get reloaded from layer to layer. So here you see SRAM. So we do a bunch of computations So there's basically this weight stationary memory, or sort of quasi weight stationary memory in the center. And once we've done a number of computations, we reload these weights from the SRAM. So I think it does everything you asked. And it is actually kind of semi-programmable, I would call it. We can run a varying number of layers, and we can change a few things. It's just not a super programmable processors as the CS people would normally be used to. It's a little bit limited in terms of what you can.
Yes, my theory is that the Scamp device, the analog side of the Scamp device, every instruction can be thought of as a convolutional filter.
Mm-hmm.
So perhaps if you can encode the same filters into this, then you are actually working with parity in terms of computational ability. But perhaps you're doing it in a more efficient or different way that gives us other benefits.
Yeah. I mean, except that this is not integrated in the pixel, right? So that's the difference. Yeah. And I think I'm very interested in pushing some of this stuff into the pixel as well. I mean, the main issue here again is this thing is power efficient because we squeezed it down into binary computations. But when you're in the pixel, well, you have a high dynamic range signal. You can't just binarize that. You've got to do something before that. And this is actually where these log gradients may come in again, right? I mean, maybe this is something that really helps us. This is kind of the hope that we can get a feature that can be highly quantized for this type of local processing, so that we don't have to slush all these bits around and make the pixels bigger than they may need to be. Yeah.
Thank you. Is there another question? In that case, I think I want to try and ask another, perhaps off the wall question. Back in the dark ages, analog computers were really popular. But typically, they were continuous not only in terms of the signals, but also in time. You would actually solve a differential equation by setting up a circuit that actually implements the differential equation. And you could do this in a sensor array with the signals as you capture them. I think there is some work by Chua and Yang on this kind of thing. I wonder if, Boris, you've thought about this kind of thing and what you think the opportunities might be, or why perhaps this work has been neglected.
Yeah, I think the number one issue is the accumulation of noise and other non-idealities. As in all large, this is why we do digital VLSI, otherwise there would be a blooming field of analog VLSI. This is really the problem. In fact, it's funny you mentioned it. I'm actually working on such a system right now, but it's not used for this application or for some other meaningful signal processing application. It's actually more used like a random number generator because of its features. Because of its features to mix up all kinds of random issues. So it comes for a hardware security problem I'm working on. So I think this is really what killed this idea. It's mathematically beautiful. And there is some interesting work out there you may have seen from Yanis Tsividis and others, where they use systems like this to get a rough solution for a differential equation, and then they let a digital computer refine it. So I think whenever you have a low fidelity application, I think there's merit in these approaches. But once it's high fidelity, it should not be analog. I should point out here, there's one important feature about this structure that we built, and that is there is very limited analog here actually. So we just accumulate in the analog domain, and then we slice this result. It gets regenerated. This is actually important in any computation, that after a few stages, you want to regenerate. You don't want to propagate the noise, accumulate the noise from stage to stage. So yeah, I think this is my message to everybody in analog computing. You gotta, at some point, you gotta slice it, regenerate it, and then move on, right? So that you don't do analog noise accumulation.
But when we regenerate, we have to classify.
Here it's really quantization. So so if you get by, and neural networks are okay with that, right? We know that even in relatively sophisticated neural nets, 2-3 bits go a long way. So yeah, that's been the general approach that we're taking here.
Thank you very much indeed. I think that probably takes us to the end of the time. Another round of applause for all of our speakers from this session. And we should move swiftly to the next part of the agenda. Before we do, I would like to remind you to stay on the call because we plan some discussion and of course some socialization afterwards as well. But I would like to hand over to Sajad and in doing so, thank him for his initiative in making this whole workshop happen. Sajad, please.
Thank you, Paul, and thank you for the great talks for invited speakers. At this point, I think, as we promised, we will announce the award winners. So we have 2 awards. The first one was for best paper presentation. That was for best presentation. And the winner of this award is the paper by Niku Mesikomer and his co-authors titled Event-Based Asynchronous Sparse Convolutional Networks. I'm not sure if they are on YouTube or they're not on the Zoom, but congratulations to them. They will receive their prize from Wiley, the sponsor of the prizes. The next award was for the best poster and video presentation, and this award goes to the paper written by Yanan Liu and his co-authors, the titled Bringing a Robot Simulator to Scamp Vision Sensor. Walterio, the supervisor of the work, is here, so congratulations to the team. That was a great work. The merit that we considered primarily was the novelty of the work and also the value to the community. So that was these were the main criteria to decide these awards. And the award again will be is sponsored by Wiley and will be communicated for the details. And now time for discussions. We have selected several topics. This is open discussion, so anyone can participate in that, including people who are on YouTube. They can type their questions in there, and we will repeat their questions here. The first topic is about what should the next generation of vision sensors for robotics should look like. There are 2 shoulds there. Do we need more computation on the vision chip? So this is the first topic, and I encourage you to participate in this. Any icebreakers?
I guess first thing which we should say is probably for robotics, one of the most successful vision chip so far has been the event-based camera, right? And that compared to other vision processors such as Scamp or more complex devices has much less computational or reprogrammable ability. And I guess it would be interesting to think whether events are enough. As we've already seen by some of the presentation, they can give us a super stunning result, or whether we can push it much more by moving more processing to the device.
That's a good point, because yeah, I think there are maybe other factors into that, and that's kind of like the availability of the sensors as well. I think that's kind of like if you want to do research on these like event cameras, there's a lot of support to start this. So that's I think maybe kind of like also a deciding factor in here as well. I'm not sure what others think of this.
Well, it seems to me there are 2 reasons why you might want to do more computation on the vision on the sensor device. One of them is perhaps because it will enable you to reduce the data volume moving downstream. The other is potentially that you have access to information that is hard to capture otherwise. So, for example, the work we've seen on high dynamic range to some extent does that.
Right. In other words, most of the works, most of the sensors, they show things that they show very cool demos that it's usually impossible to do with conventional sensors. So maybe that's the final answer. Basically, we should be able to do things that are not possible to do.
I guess there's also an issue of what does it mean to have a computation on a vision chip, right? So whether we are computing in pixels, whether we're computing next to pixels, whether we are computing on the chip, but somewhere outside of the array, and what is the kind of, how does the whole kind of pipeline look like? So I think that's an important question here, which I'd like to know answer to, but work needs to be done to find the answer to that question.
Yeah, I mean, I think what drove me into being interested in these things is mainly about efficiency, and I guess mainly that comes down to power and this argument that if you can do more on the sensor chip and therefore send less data to a main processor, I guess either do everything on a chip that's right there next to the processor, or yeah, do a lot of processing and then only send something abstract to your main processor. Yeah, we just need, massive, for some of these applications that we are interested in the long term for embedded vision. I just think we need orders of magnitude of improvement in efficiency, power usage, such as the sort of things that Facebook were talking about, always on vision. They're talking at the moment about switching it on and off and so on, but of course you'd really want it on all the time. How are we going to get down by that thousands of or whatever it is factor of efficiency that we're really going to need? So that's the main driver for me. And it was interesting what he Yusin said in the talk about some of these decisions were maybe not so obvious. I hadn't quite thought about that. I'd always assumed that pushing more to the sensor chip, if you could, would always be, or almost always be, the right thing to do. But some of the things he said about, if the process node technology wasn't quite as advanced, for instance, and therefore it might actually be less efficient to do some things on the sensor chip than moving that data to another processor that might be able to be more efficient because, for instance, it didn't have to be so compact. That was quite interesting.
I mean, it kind of almost depends on what we mean by chip. I mean, it's always better to do things on chip than somewhere else. But whether I mean, what about a stack, for example, where you have different technologies that are kind of vertically integrated? Is it still a chip? I mean, to me, it's still a chip, but you can think about it as 2 or 3 different chips. But clearly, then you can optimize different technologies for different types of computation. So we've done some designs where we had a sensor tier, which was image sensing technology. Then we had a second tier, which was an analog processor, and a third one, which is a digital processor. Actually, ours was kind of uniform stack, but you can imagine a heterogeneous system where you have an optimized image sensor technology for the sensors, an optimized technology for analog compute if you want to do some analog preprocessing, and yet another tier of digital compute for digital logic, and perhaps another one for DRAM or flash or whatever else. So keeping things compact will be always advantageous, but how the system should look like, I think that's another question.
I think going back to the always on idea, I think there's the more computation we can push onto the chip, I think we could probably say the more secure we can make it. as in that is to say that if you have dedicated hardware for doing this sort of small first steps and encoding more interesting features, then it can make it harder for malware or something in the application layer to put out information that we don't actually want them to see. So we can pick better, these are the number of faces in the image and not these are particular identities.
Right, yeah. Paul, you're mute. Yeah, if you.
I think you have to be really careful with that reasoning for two reasons. One, because, so for example, we've experimented with only sending edges off device. Can you really promise me that you can't reconstruct privacy breaking information from just the edge stream? I think you probably can.
As we've seen with the histogram of gradient stuff, there's a lot of reconstruction you can do.
Absolutely.
So I think the question is, if we're going to put more computation onto the vision chip, can we get all the way to something where we aren't just sending edges, we're sending feature vectors that can be trusted, as it were, because we've stripped out all the unnecessary information.
So the other pathway for vulnerability is that if this device is programmable, I just have to hack its code.
Yeah, but I mean, that's always true. Access to the hardware is access to the hardware.
Right, yeah. I think just in the interest of time, we can move to the second topic, which is, I think for me as a roboticist is kind of like important. And that is, what are the technological challenges in bringing novel sensors to robotics? Yushin mentioned a few challenges, including heat dissipation, the weight of the sensors, and all those sort of things for smart eyeglasses. But in robotics, we face similar challenges. So I'm not sure what's your opinion about this? And it obviously depends on the application domain, right? So for example, for drones and things like that, it has to be very lightweight, just like eyeglasses, smart eyeglasses that Yushin was talking about.
Yeah, isn't one general challenge just the whole system stack complexity, right? So, I mean, whenever I talk to people who develop algorithms, they don't want to hear about my stuff. They want something very general. They don't want to be restricted by the way I produce data or how I represent it. They want to program everything, and they're going to change their mind every week, right? So if you give them something customized and optimal, which is a novel, that this is where most of the novelty goes. We squeeze performance out of customization these days. I think that's, in my mind, one of the biggest challenges, how to get that accepted by the higher levels of abstraction and the people running these layers of abstraction.
I think that's an important point, right? So I think you can almost always build a circuit that is better than a general purpose circuit that more efficient, but that doesn't necessarily mean that it will be better in the sense of being used by more people, right? So I think that is I mean, even with the work that we've been doing on Scamp sensor, I mean, I was always out for 20 years. I was saying these are programmable chips, but really no one could program them. It's only when we started to develop this very, very detailed sort of programming environments where you could actually program them in C and you could sort of compile your programs and so on. It's only then that we started to see people, doing things with the system that we I thought was impossible. So there are kind of new applications coming up, and I think that kind of issue of providing the software frameworks so that people can use systems is important. And I think the more customized the hardware is, the harder it gets. And definitely this issue of we can spend 3 years thinking about circuits, how you develop some optimized neural network architecture, only for people to decide that the nonlinearity that you're using is not fashionable anymore, and no one wants to use it. So yeah.
Speaking of the customization sort of route, I wonder how sci-fi an idea it is to sort of get to a point where customizing a chip is like how now people have 3D printers at home. I mean, 10, 20 years ago, people didn't think that they could make their own products and their own 3D objects at home. And now you sort of can. I wonder how long it'll be until every research lab can do a bit of chip fabrication in the corner of the office and make what customized or partially customizable chips they need.
I think it's certainly hard with the state-of-the-art silicon technology. It's just too expensive. You cannot afford this. But there are other interesting technologies on the horizon. We've been working with plastic electronics, printed electronics, where you can, at a very low cost, customize your circuit and have a very quick turnaround and get them fabricated and tested in a matter of weeks. So and these are not, this is not 7 nanometer CMOS or 5 nanometer CMOS. But you can end up with your, customizable circuits in that way. And things like programmable logic devices and so on, again, these are the ways in which you can end up with a custom silicon. And there is some sort of pathway, semi-automated pathway from your application to what we call silicon. Yeah.
Thank you, Boris. So some of you will have heard me already say that the fundamental business of computer architecture is reducing the interpretive overhead, is having your cake and eating it, having programmability without having to pay the price much.
Mm-hmm. Mm-hmm. Yeah, exactly. So actually, I think that brings us to the next topic, which is basically what exactly we're looking from these on or near sensor processing system. Is it just low power, high performance, or are there any other things that we're not considering yet and might be an issue in the future?
I guess something interesting to think about might be how we can feed back from the algorithm side back to the sensor to try and do more adaptive sensing. Just like how AI work, we might be able to move the sensor in the direction we want to, and that should feed back off the algorithm side. And maybe if we can bring this kind of active selection towards the sensor, we can make more efficient algorithms or efficient hardware. Like having a bit more smartness near the sensor might be quite beneficial for robotics.
Right, a bit more like high-level decision making. That's what you're saying. Yeah, and also there is another interesting thing that most of the sensors, the direction of data is in just one way. It's from sensor to the kind of like maybe downstream to the actuators or whatever is there. There are applications.
Yeah. Sorry, did you call my name? Sorry, my Zoom crashed.
Oh, welcome back.
Yeah, that's good. Yeah, so there are maybe, so this is the third topic that we're talking about, Ontario. And yeah, so some of the applications, maybe we just need to send data to the sensor. Maybe. I mean, we talked about this a while ago about doing like on-chip localization, doing some sort of rendering, sending image to the chip and doing some process on there. But at the moment, at least on Scamp, we cannot do that easily. I mean, the recent paper that Hector's work is kind of like moving in that direction. But I wonder this would be something that we will need in future.
There's a whole reliability issue as well that one of the submitted papers was trying to talk about in terms of if we have these on and near sensor processing systems, can we ensure that they're also, doing accounting for bit flip errors or, interference and all those sort of things. And if doing it on the near the sensor actually is a benefit rather than doing it on a larger CPU or something and trying to fix those errors there.
coming back to the question, perhaps to me, one of the big opportunities here of these sensors is that we can open again the discussion about how to best process visual signals. So how to better understand the visual processing pipeline is something that so far we've been extremely not advanced and not very challenging, and challenge ourselves because we assume that these components exist, and to Boris' point, people prefer generality, and there are of course big gains on that. But as we move into applications, then you really need to start considering how best to do signal processing for specifically for vision. And I think so far we really don't have good frameworks for visual processing that are efficient. And this opens that discussion. This is part of that discussion that needs to happen. So to me, actually, that's a very good opportunity for us to revisit how to think about how to process visual signals. And sometimes one of the things that I struggle, it can be as basic as in our Scamp research, we don't capture images. We actually struggle to show our results because the Scamp is not designed to capture images. And this is counterintuitive to the notion of a camera that doesn't capture images. It cannot be a camera. But actually, this is what we need. We need visual sensors that work for the task at hand. And that task at hand may have nothing to do with recording images. So just rethinking what you're going to do with these visual signals is a very important discussion to have. And this I think, is a big opportunity for this type of sensors that we're discussing here.
Yeah, I mean, I agree with that. I mean, as you say, we're trying to figure out how to best process the images, but I think we're also trying to figure out how to best sense. So it's not necessarily that that the way of sensing, capturing frame is the best, and we see with event cameras work that actually, the different way of sensing is advantageous in some situations. We've done some work with Julien Martel where he's capturing every pixel with a different integration time, and that allows you to reconstruct both high speed images and also high dynamic range images. So we have this all flexibility that people are just dismissing because we normally deal with these images that are captured in a very orderly way. So I think is the optimization of the entire pipeline from light to action that we have an opportunity to do with being able to process very near the sensor, because we can affect not just how what we do with the information that we capture, but actually how we capture that information in the first place.
Absolutely.
Yeah, exactly. I also think it's kind of like we have to think about end to end, like from photon to action. That's how I think eventually it should be.
Yeah, that's right. And maybe I think another aspect of this is that having this ability to process things very fast, perhaps at a very high frame rates, or processing during light acquisition and so on, just allows you to rethink the algorithms themselves, right? It's not just a way of efficiently implementing the algorithms that already are there, but pointing to the new ways of solving problems that you would not think of applying, because there would be a completely non-economical in the conventional vision pipeline. Mm-hmm. So I mean, doing things like we've done, for example, with the depth from focus. It really doesn't make a lot of sense to capture 7,000 images just to get the depth information. And yet it's not that expensive if your processing occurs as you're capturing those images without ever transmitting them out. So that sort of things where the thinking about the algorithms is really affected by the way that the compute substrate is organized. I mean, another simple thing is, if you capture key points and you have several key points, if you do this really fast at tens of thousands of frames per second, then those key points never really move a lot, right, from frame to frame. You don't have to do key point matching. The matching is just by local proximity. So it simplifies a lot of things. So doing things fast, you can be pretty stupid and appear smart, right, just because you're quick. So I think that's quite interesting. So we really see the kind of different algorithms can be developed because of a different compute substrate that exists.
Right, yeah, exactly. A global sum is also another good example. I mean, on regular images, no one does global sum because it just doesn't make sense. But it shows its advantage with, although it's a very simple operation, but it shows its advantage on applications on Scamp or similar sensors.
Yes. I mean, another example was in Boris's talk, this very nice kind of log gradients by division. It's really driven by the fact that it's easy to build a circuit that will do that kind of division, right? So it kind of have, that's how the circuitry drives the algorithm and not the other way around. And you know, it may well turn out that that's the way to capture images, and that gives you some other advantages somewhere else. So I think that really opens up the opportunities. And we've been sometimes when we are discussing this thing, sometimes thinking something like a Scamp, not the ultimate solution, but a vehicle for exploring the space of solutions.
Yeah, great. Sounds great. So, I think it's time to move to the fourth topic, which is about interfacing from sensors to actuators. We have seen a few nice works, emerging new works that are moving in that direction. But in general, like, is there new needs? Do we need to develop standards or protocols for signaling and things like that?
So what are you trying to get at here, Sajad, with what aspect?
So
with regard to like speed or what would be different?
Right. So now, for example, if we want to send signal to a servo motor, so we have to send some information to the microcontroller, and then the microcontroller sends the PWM signals to the servo motor. We might as well just output like PWM signals directly from camera. I'm not sure. I'm just thinking out loud. It's not maybe well equipped to do these sort of things, but we might as well rethink the interfacing and how the data is being passed down to actuators in terms of like, yeah, how they should look like. Yeah.
I think there's a lot of interesting stuff in that area in terms of like Riku said earlier, telling the sensor what to look at.
Right.
And you can do all sorts of sort of stabilization, image stabilization, and all that sort of stuff really quickly, and with the really low latency that you need for high frequency vibrations and things. If we can have yeah, actuators that are controlled directly from the focal plane. But I do wonder if that is always going to end up being a custom design, though. It's possible to have a standard there, or you're always going to have to co-design your actuators with your sense processing.
Yeah, or are there certain standards that would be so kind of generally important? I mean, like a kind of, you know, pan-tilt capability of what a camera is mounted in, I guess, like an eye moving around, or like Waltera's wearable robot from the old days that just, and yeah, you think of Professor Ishikawa's, you know, just so many demos of how if you can track something at fixation, tracking just becomes so much easier. I don't think I'd seen that table tennis ball one before that. That's incredible. I didn't know they'd managed to do that. But yeah, you can imagine that you've got this intelligent eye, and then having that mounted on a pan-tilt unit just may be such a common thing you might want to do that could almost be co-designed as a standard feature, the kind of interface to a pan-tilt unit, and it's almost like this optokinetic reflex or whatever, the vestibulo-ocular reflex, and these kind of things that a human eye has.
Do you have to do that physically?
Pardon, Paul?
Do you have to do that physically?
It's more efficient, Paul. Otherwise, you actually have a lot of high resolution. There is well, we can talk about that, but there is like a calculation of if you actually wanted high resolution everywhere around your visual field, you will need an eye the size of 2 meters or something like that. So
sure. I think we might have talked about this before. I mean,
yes,
it's not so uncommon these days to see a 100 megapixel sensor. We don't want to be doing low-level image processing on 100 megapixels every frame, but we might use a perhaps separate sensor to select which.
To your point, even if you have 100 megapixels, but you actually have processing there, you might decide what you're deploying where, which will be still okay. So I think there is a path. I don't think we should discard any ideas at this stage, especially when we're trying to redefine the visual pipeline.
In terms of the interfaces with the actuation, Paul's mention of doing it digitally made me think: could we actuate the eye, the camera motion, pan tilt or whatever, with analog signals? Could we, bring it closer with I mean, we already in Scamp we already have sort of negative charge, positive charge analog signals. Could we convert that directly into something that moves an actuator based on the charge?
I think you probably could, but then I think there's very limited, I mean, none I can think of applications that actually call for that sort of, closing the loop at that speed. I think we're talking about a single or a few actuators, and it's not a lot that you need to do along the line. So I don't see bottlenecks there in terms of actuation, unless there's some really extremely fast closed loop system. But I can't think of any that you couldn't do with a microcontroller.
I mean, I guess how fast is biology in moving your eye from the input, and are we matching that, or have we got ways to go before we're as fast?
The eye actually has a closed loop frequency of about 1 hertz, which is very fast. And you think 1 hertz is this, you can track that. But it's not overly fast. It's not overly fast, at least humans. I mean, bees and other flying insects have a much faster reaction time, which of course is very important to them. And so, yeah, again, there will be a range of requirements in terms of how fast you have to move. I will be worried if we just want to process things fast because we can. I think that will be the same as saying, let's just put more pixels because we can. I think, again, this opportunity that we have in front of us is how you can rethink what the visual pipeline actually requires. But going back to your point, Edward, about analog processors, I agree, and we have discussed with Peter a lot of times. We will love that the processors that are in Scamp, for example, are all analog and powerful and suffer from no noise or any degradation, because that is potentially a much better organic signal, let's say, towards connecting it to actuators. So yeah, I'm just still waiting for Peter to develop that perfect analog processor that we can use.
It's not going to happen.
Oh.
So one of the ironies about that chain of reasoning is that we know biological vision systems are not clocked synchronous binary circuits. How is it that, why is it that we can't somehow retrieve or overcome the noisiness? I think this leads you to some kind of spiking structure, I think. I think I may have dug myself into a hole of ignorance already, so I should shut up.
I don't know the answer, I think, but I would love to understand better what is needed in order to improve analog processing.
I think Boris has hinted at the property of neural nets, which is that you're doing some sort of analog compute, and then you have a nonlinear operation, and that nonlinearity restores in some way the state of the system, right? So you can't have a very long chain of analog operations. I think you always lose something in the noise. But as long as you have this, nonlinearities in between that somehow, don't require you anymore to have the kind of linear or kind of remove the accumulation of the error, because they do some sort of decision, right? So it's always being selective in terms of maybe spatial and temporal selectivity, and then being selective in terms of making a decision and making some kind of, and that then feeds into the next layer, and that's that's how neural networks networks, artificial ones work. Perhaps that's how the networks in the brain work. We don't actually know, right?
Right. Yeah.
Well, that's essentially an argument that with the right neural architectures, we can make the problem go away.
Oh, with the right architecture in general, right?
I think somewhere in
I think analog computing. I think analog computing is it's efficient, but exactly it's not a solution to everything. It has to be interspersed with this kind of this digital or nonlinear stage where you can restore, and then you can keep going on for a long time doing this.
Right.
I think somewhere in there, there's the need to have a training process or learning process either on the chip itself or having a better simulator that we can use for training offline, so that we can so things can learn the noise patterns properly, rather than these sort of approximations to noise that we're able to give them at the moment.
If you want to learn, I mean, if indeed the way that you want to build your system is through learning, but it may not be the most practical approach to learn everything, within the hardware that is operating.
Everything's learned, even if you're making up the algorithms by hand.
Yeah, good discussion. Let's move to the. We don't have much time, so and I understand it's Friday and evening for you guys. So let's finish up the discussion by the last topic, and it's kind of like interesting and challenging topic, especially when we talk about near sensor processing, Scamp particularly. So the question is, do we need better evaluation and benchmarking methods with focal plane sensor processors? Especially like you're doing processing right when you capture data. So if you want to reproduce data or someone wants to reproduce that, basically it's going to be challenging because the scene is not there. It's no longer there. You're not able to capture the scene. If you want to capture the scene, you're not going to be able to process at that speed that you want to do. So this is always a challenging problem. And maybe we should look for better metrics, such as like figure of merits that we use for ADCs or similar metrics. I'm not sure what's your opinion about this.
What does figure of merit mean?
I think Peter probably knows that better. Maybe if I define it, probably I'm going to make a mistake. But that's something they combine multiple terms together to kind of like give a ballpark number. Yes.
So you have multiple objectives and you kind of weight them all and add them all up. Is that what it means?
Correct me, Peter. I think you're the best person to answer this.
Yeah, I mean, I think, okay. I mean, yeah. Figure measure would be something that captures the performance kind of multiple parameters of performance and into a single number. I think given that even a single, we cannot really agree what a single number means, like giga operations per second. And we know it's difficult to define that. I think defining even more complex figures of merit is a minefield. I think it's hard. I think in this field because every sensor processor is different. Everyone works with slightly different principles, and it's really extremely hard to compare. I mean, how you compare an optic flow computed with events on sparse event data with an optic flow computed, on frames. If you have two sparse flows which are at different points, essentially. I mean, at different points in time and at different points in space. So you can try to adapt the kind of common metrics to fit that, but it never kind of genuinely compares to different approaches. I think that's really hard. I think the best benchmarks are kind of task-oriented benchmarks. If you have in this field, so if you had a task and if you say, I can track that ping pong ball with with a particular speed and acceleration, that tells you what the whole system can do. And I think that is kind of the fairest benchmark. But of course, these are also very difficult to set up. So I don't know what the answer is, but it's very hard to understand often, what the system is capable of just looking at the tables of numbers that people publish. It would be nice to be able to do it straight away, but it's essentially impossible. Yeah.
Right. Maybe investing more on simulation would be maybe reasonable. Just, I mean, that's also kind of like doing good simulations is very hard as well. But I'm not sure doing like high fidelity simulations would make sense.
Yeah, it's not what would excite me. I'd rather just work on the real systems and try and make demos. I think.
I think there is an issue with just making demos and trying to make a science argument about what's working and what's not. I appreciate.
Yeah, but very often we're kidding ourselves. I think with these metrics, I'm just stick to the back teeth of papers full of tables at the moment in this field. The world is wide open. We've got orders of magnitude of improvement to be needed, and we're already defining benchmarks in far too many places. It's my little rant at the moment.
I think I echo that. I think the challenge for us, Andy, is, however, what are those demos that are going to be groundbreaking and that are going to say, yes, I don't need metrics because you're showing me this, right?
Yeah.
I think that will be the challenge.
No, sure. I mean, that's always the challenge, isn't it? Yeah. But yeah.
Yeah.
I guess we've done it before. We've done it before. We'll try and do it again.
Yeah, let's do it again.
I think part of the subtext for Sajad's question, in my mind at least, is that within a sufficiently constrained and conventional environment, you can see how to make benchmarks, and we've done it with things like SlamBench, and such things are much more common in other parts of computer science. What we might imagine trying to do is to do this in a way which doesn't constrain the design of the solution. And at that point, you start confronting things like, if you wanted to study, do reproducible experiments on the per pixel exposure control, you can imagine a simulator that would do this, but it's not what you wanted. What you're actually looking for is something more like an agreed experimental protocol.
Yes, yeah, exactly. That could basically, that could kind of like put us in that direction. Maybe we need, say, for example, repeat one experiment 50 times and report the average, for example. I mean, things like that. If it's not really possible to reproduce exact same experiment. And I totally agree with Andy that like if the demo works, that's pretty good, and that's going to work only for the first paper. And Andy has a lot of papers like this that the first paper in the field, and so it's everyone accepts it. But if someone comes and wants to compete, they're going to refer to the previous paper and they're going to ask like, yeah.
There's also a tension here between innovation and technological engineering.
Right.
So ideally, we have academics like some of the people around the table making shiny new things, turning them into engineering products, and making good engineering decisions about A versus B. Actually does involve doing repeatable experiments. They don't have to be public benchmarks. They actually need to be things of business value.
Right. Yeah, and this is still a challenging for Scamp. So I think we need to come up with a protocol or something like that. And now, for example, just for Scamp, we have 4 different techniques of doing convolution. We have OK framework, we have Kane, and we have 2 papers that Laurie authored them. So we have 4 methods of doing, at least the 4 methods that I know. But comparing them is quite difficult. So if a 5th paper comes along, so we have to be able to kind of like say what are the pros or cons. And this is more challenging with this Scamp.
Yeah. I guess if it's just a composite, maybe the semi-simulated environment, which was proposed in the poster, would be quite nice because we can load a known image and just apply the convolutions on the Scamp. Again, it's probably not the same as having a moving camera and trying to capture something.
Right. Yeah, exactly.
It seems like the golden standard would have to be a robot arm that everyone can get, and you can put whatever camera you like on the end of it and have it shake around in a particularly drawn out scene that's very well specified. I mean, but the idea is that you're making your benchmark task based and like real world rather than simulated, or rather than so you can allow for different cameras, you can allow for different processing examples, but what you're actually constraining is the specific task, the movement of the camera, or localization or something, and the scene itself.
Yeah. And that's only for one application. If you change the application, say for example, maybe driving in a crowded like streets, or it's going to be very hard to repeat that.
Yeah.
Yeah, I think that would be one of the challenging problems, and we need to come up with a solution.
I think there's an interesting benchmark that seems to be implicitly seen so far, I think, throughout this day, which has been the can you reconstruct the original image benchmark.
Mm-hmm.
And if that plays into how we benchmark or decide how to evaluate different techniques for doing this on focal plane sensor stuff.
I guess the main purpose of trying to do more computation near the chip is that we cannot construct the image back because we've already handpicked or selected the most important information, such that there's basically nothing to squeeze out anymore. And I guess if we make the benchmark to be that, can we make an image back? People would be, I mean, the best one would be to just send all the images. So
I guess more broadly, the question is, can you actually complete the task with just the data coming out? Could you, can you give that data to a person and ask them, right, from that data, has it told you what you need to know? obviously you're sort of defaulting back then to making a pretty picture that humans can see. But there's yeah, I guess it's task dependent, isn't it? There's no one single solution.
Well, I guess another way to benchmark would be to just make the tasks harder. For example, we might imagine like a tracking task, which is can we track 100 kilometer ball or kilometer per hour ball? The next one would be 200 kilometer per hour, and then we solve the problem of, well, we sort of solve the problem of not having to benchmark, and the next paper to be good enough to be able to solve a harder problem. And I think that's enough to justify why the successive papers are good.
Exactly, 0 to 1 demos. Do something for the first time. That's what, yeah, that's what I like to try and do.
Mm-hmm. Great. So I think we're 10 minutes over the scheduled time. I think I really enjoyed the discussion, but if there's nothing left, so we can finish this here. Thank you, Andy. I really appreciate you joining this talk. And Peter, Walterio, I know that you have to go to work, Walterio, probably. And also Paul, Riku, and Edward for chairing the sessions and helping this. Thank you very much. If there's anything you want to say, or.
Oh, thanks to you, Sajad, for this great first step on putting this community together. We're a small community. We should not be afraid of that. We should not be ashamed that this is a small community. This is the beginning. And echoing what Andy and others have said, taking the first steps is never easy, but this is one of those first steps to get this community together. And I think we believe that we are right, and we now need to prove it and enjoy the ride.
Right.
Thank you, everyone. I really enjoyed the talks, and I will be watching and sending the link to my team as well for them to watch the rest of the talks that I missed.
Great. So most likely we will edit the videos so that we break them down into smaller pieces so that it's easier to manage. So, but I will send you the links definitely.
Yes, please. Yes, please.
Yeah, but I think the YouTube is up there for anybody to just scroll through right away.
Yes.
So while it's fresh in your mind, you can pass it to people to look at. Absolutely.
Yeah. So that link will be stable, right? So the video will be recorded there, and we can watch the whole thing in a single video there, right?
Yes, for 10 hours. Yeah,
10 hours.
Sit down for 10 hours. Yeah.
If anybody makes an index, that would be appreciated.
Oh yes.
I'd like to add my thanks to Sajad for making this work, and also appreciation, because I think the program of talks was just spectacular. We had the most incredible quality of people here and exciting things being talked about.
Yeah, it was great. Thank you. Thank you very much.
Thank you, everyone. I think Julian also was quite helpful organizing everything. He's not here, but many thanks to him as well. So we'll finish here. I will go back to GatherTown. I'll be there for a while just to finish up everything there. If you're interested, you can join GatherTown.
Sajad, you've been up all night. My guess is there's nobody there. I'll just go and look now, and if there's nobody there, if there's somebody there, I'll talk to them. Yeah. But let me release you and take the day off.
Sure. Yeah. Thank you. Great. Okay. Thank you, everyone.
Thanks very much.
Thank you.
Thanks a lot for organizing.
Oh, we need a. Oh, yeah. Thank you. Stay well. Bye.